Hi, hello everyone, welcome back. Please let me know in the comment if you can hear and see me well, because we just changed the link, so people are going to join soon, and we already waiting for our next speaker who is ready to join. Meanwhile, I would like to announce that we have a giveaway of tickets for questions. If you were with us previously, you just saw the first 5 winners of those tickets, so don't miss your chance. Use the hashtag question for ticket. I'll share it with you in the comment. And at the end of the summit, we'll randomly choose 5 lucky winners to provide with the ticket. Be active and let the luck be on your side. Please let me know if you can hear me well. Great. Now we are ready to welcome our next speaker, who is Juan Sanchez.
Hello, Victoria. Nice to meet you.
Hi, Juan. Nice to meet you too. So, I can tell that I really like your bio. For all the attendees, so you know, in his bio, he mentions that Juan always strives to learn more, looking for challenges and enjoying the journey of overcoming them. And currently, he's changing from .NET world into the JavaScript era and combining this with an architectural point of view. And Juan is going to present us his talk, Driving a Bus, using the event bus pattern of your ETLs. So Juan, tell us, how are you doing today? How is your mood?
Pretty good. So far, actually, the weather is looking nice. The day is starting, so I feel fine today.
Oh, that's great. So before you start, I would like to ask you just a quick question. How did you decide to move from .NET to JavaScript?
Well, I think that it was a little bit of when I was changing jobs between 2 companies, and actually I saw that there was some opportunity there in order to grow a little bit more on the JavaScript. There were a lot of more opportunities within the new company, so I decided to do that switch. It's been over more than 3 years now, or almost 3 years. I don't know. I lost count. So that's pretty much it. That's what I decided to move there. I still do .NET development work within the company and some freelance. But it's more JavaScript now.
Okay, thank you. It's really interesting. And I'm sure you're gonna share some valuable information with our attendees. So please be active and leave your questions right there. So Juan, you can share your screen and start your speech.
Okay, thanks a lot. Let me start sharing my screen. Let me know when you can see it.
Yes, I can see it. So please, the floor is yours.
Okay, thank you. Well, welcome all. Hopefully you will find this talk useful and that you have been enjoying all the presentations so far. For my case, as Victoria said, I'll be sharing a presentation called Driving a Bus using the event bus pattern for your ETLs. In this presentation, I would like to focus on how to use some AWS services to simplify the process of extracting data from different data sources and injecting them into a new destination. Also, since all of this is about case studies, I'm bringing an example of how this could be included in a real-life project. So for our agenda, we have the following. We'll start with a small introduction about myself. Then we will review some basic concepts about the event bus pattern, as well as what is an ETL. We will continue with the basic scenario that I consider that this approach should work best, which AWS services I recommend on using for this. And finally, some considerations that I evaluated to be important. As well, I'll do a demo towards the end. So let's talk about myself. My name, as Victoria said, is Juan Daniel Sanchez, but you can call me JD. I'm the development manager at First Factory, where I lead multiple projects. I'm in charge of both the management as well as the architecture for them. I got certified as a solutions architect associate from AWS a couple of years ago, and I hope to get some other certifications around AWS in the next couple of months as well. So let's start with some concepts. Who doesn't love theory? The first one is the event bus pattern. This is one of many architectural patterns and can be divided in 3 major components. The first one is the event source. This component is the one where the information is going to come from, And normally, it's the one that will trigger any process that will start. The second one is the event listener. It is tightly integrated or associated to the event source. In our example, the event listener is going to be the one in charge of processing whatever information is coming from the event source. The third component, and last but not least, is the bus channel, who is in charge of actually transferring information between the multiple parties. There can be various implementations adopting different data structures. All of these components can be mapped to a specific AWS service, but we will see them later on in the presentation. So now let's change gears. Now we're going to talk about what are the ETLs. So ETL stands for extract, transform, and load. In general, it is a procedure, let's say, of copying data from one or more sources into a destination system, which represents the data differently from the source. Extracting information could involve multiple steps like encoding, sorting, doing aggregations, changing formats, and combining information even. Also, the information could come from different sources, and that not only means that it should come from the same type of data source. Instead, we can combine different options like microservices or web service in general, text files, databases, and much more. Among the most common tools that you can use, you can find SQL Server integration services and other tools that are popular in the market like CData Sync or many more. However, for this, we won't be using any of them. So moving on, let's talk about the best use case that I consider this approach would be most beneficial. So it's possibly a common situation that you have faced before, or maybe something that you will face in the future. So let's imagine this use case. You are working on a complete new project rewrite of an existing system. In this project, there will be multiple sources like web services, as I mentioned before, XML feeds, or text files even. It's important that the data that it's being used for development is as close to the real one, because it will provide a much better picture, panorama, etc., of how the application is going in comparison to the previous one, particularly for the business, as they are going to be the one who approves your project to be successful or not. As it is standard in the industry, nowadays we are working on a phased approach to this. So let's say that we are working on an agile methodology like Scrum. Now, if you ask me why this is important, the whole idea of this process is to pull information from the source as needed. So if in the first couple of sprints, we are working on a couple of modules, that's the data we need to pull and nothing else. Optionally, this could be used as well in a complete new build from scratch. So let's say like a startup, for example. So it's possible to fake data for this as well. However, I think that the previous conditions are the ideal ones to this to be quite successful. Also, this separation helps to manipulate data. So as I mentioned before, one of the main core concepts of an ETL is to transform information. So if we have a limitation, for example, on the information that the developers can see, we can use this separate process to change some values for testing purposes as well. So now that we have described the environment that we are going to work in, let's start by designing the ETL to pull the information and design the ETL from a conceptual point of view. The first step is to select that trigger that will execute the whole process. This could be an action done by a user, or maybe a cron expression that will determine when the process will start, either once a day or once a week, even once a month, for example, etc. That depends on the business. The second step is to define what is going to be the routes and the route in singular, and which stops this route will have. A stop can be a new data source to pull information from. That means new passengers in the bus, or a destination data source where the information will be dropped. The third step is to define what are going to be the passengers. That means which passengers or data points will be fetched in the starting point, which ones will be dropped in a specific stop, or new passengers that will be picked up along the way. The fourth and final step is more oriented with the design of the system. So we are getting a little bit technical here. Exceptions, concurrency, and other topics that are common to any system that will manage big sets of information or sets of information in general. For this particular step, I have prepared a list of these considerations, but I'll talk towards the end of the talk. So now that we have defined what our ETL will look like, let's dive a little bit into what AWS provides for us. The first service that we will use is SQS, Simple Queue Service, which is a message queuing service that enables you to decouple and scale systems as microservices or serverless applications in general. The second service is AWS Lambda, which lets you run code without provisioning or managing service. So basically, you pay only for the compute time that you consume. That will reduce a lot of costs. The third and final service is CloudWatch, which provides you with data insights in general to monitor your applications. It can help you optimize your resources, debug problems in the future, and it will give you a unified view of the overall health of your systems. I'm not going to dive into more details for each service since that's like a separate talk. So let's say that we now have this defined. Let's combine the concepts of combining everything. So let's combine the services that we mentioned before with the parts of each of a stop. So this will be the composition. The top section will be the data coming from the event message queue. Then we will have the code handler, which is Lambda, that will be in charge of processing this data. And finally, we will have all the outside resources that there will be any interaction with. This could be databases where we put information into, or the different sources where we pull information from, including microservices. So now we are talking about microservices. The whole process helps to facilitate the interaction of the data between all of them. So by having a mapped process or route of how the information is managed, then we can have a clearer understanding on how to interact the services between them. Some important considerations that I strongly recommend to take care of are the data integrity. It is important to map what data points will need to be processed first in order to maintain a sequence of events. The whole process can be understood as a database transaction. So let's use that metaphor for the time being. With each step or stop, we assume that the previous ones have been executing successfully. But then what happens if a hard problem happens or exists? We will get an exception. And now we need to be able to handle that gracefully. For this, there are multiple strategies. So for example, a complex one will be to do some sort of rollback. But in this scenario where everything is distributed, that might be a little bit complicated. However, that's one strategy. The other one can be as simple as a retry policy. So maybe the issue that happened is just a network problem or a latency problem. So a retry policy will help to overcome that. Now, this takes us to the second consideration, that is detailed logging. Since we are moving to a serverless architecture with microservices, it is important to have logging information that can provide as much as possible meaningful details. This will help developers to debug any problem that will happen in the future. And here is where CloudWatch steps into, since that's the service that will become one of your allies to solve any problem in the future. Now let's talk about concurrency problems. And this is possibly the most difficult part in the whole process, because you will need to think ahead of which scenarios can happen where the same resource can be accessed by multiple data points or multiple stops within the execution. An example is actually calling other Lambda functions more than 100 concurrent times, for example. There are some limitations in this service around this area. Another example is CloudFront. If we have a microservice or a service that uploads images to S3 and serves them to a CDN like CloudFront, through a CDN like CloudFront, it might be possible that invalidations will be required, where there are also special limits according to that. So basically, depending on the service or on the third party that you're using, you should consider what are the limitations for them and manage them properly. Access restrictions. This is a general consideration in every software development process, I believe, but it is important to validate that the system have the right permissions to access all of the information that it is needed. So just validate for that. Either it's the IAM roles or just a user for an external system. Okay. That's all for the presentation. So let's start with a small demo that I have prepared to show how this system would work. So I will stop sharing for a moment. And I will change the screens. Bear with me a moment. Screen. So this will be the new one. I think that it is visible now. So this is an empty database. What I'm going to show is a process where I'm going to pull information from sports in general, particularly with MMA. So we are pulling information from different APIs, from different feeds across the internet, and we are going to store them in a database that is empty so far. What I have created for now is an HTTP endpoint that will be the one to start the process. So in another scenario, I might use a cron expression so that the job runs every day, for example. But for this particular demo, I'm going to use an HTTP endpoint. So I'm going to send a request. This won't return anything. It's just for the purposes of the demo, but it's going to throw the 200 status code to show that it is now working. So I'm going to bring this here, and I'm going to show the SQS queues. As you can see, I have 4 different queues that are running. The first one is the new events. In here, we are going to have batches of events or whatever entity that you have decided for your system. And they are going to be processing batches of an amount of events. So for example, in this case, I put 10. So for this scenario, for example, there's being processed 3 sets of events. Then each one will be processed individually on the second queue, which, as you can see, there are 81 messages available. In SQS, messages available means how many events or entities are pending to be processed. These 116 are the ones that I grab at this point that were being processed at that moment. Then for each one, we are going to process the images for each event and the fighters for each one of the events on that particular entity. So as you can see here in this one, 5 pending messages available, 7 and 88 and 7. However, this is just a snapshot at that moment. If I refresh, I'm going to see that there is nothing pending to be processed. So as long when I was speaking, everything was processed. So if I move back to the database, now what we are going to see is that all of the events have been populated. There are 99 for this case. Fighters, and we retrieve 395. Fights, there was 452, and the same amount of records as fighters for the fighter history. Besides that, the process also pulled images, and it uploaded them to an S3 folder. We populated 395 images, and for the events, we populated 99. So it's high resolution and low resolutions. So in our example, as I mentioned before, I'm actually using different microservices. The one that uploads the images, it's actually doing a couple of steps. Like for example, downloading the images, resizing it to have a low resolution and a high resolution image, uploaded them to S3, and then inserted that into the database. So this might be a process. This is just an example, but in general, this can be a process applied to different other business or companies. For example, in another case that we implemented this similar pattern, let's say, we did it for a financial company that we populated information as well that we were migrating a system. So as the development progressed, we show real data as it was required to the customers to see how the application was going. Okay, that's it for the presentation. I hope that it was useful for everyone. That's it for me. Victoria, are you there?
Yes, I'm here. Thank you, Juan. And we will see you soon on our Q&A session. So the attendees, don't forget to ask your questions, leave them in the comments, and Juan will be able to answer them on our Q&A session. Thank you, Juan. We'll see you soon.
Bye.
Bye. Okay, and now I would like to present our next speaker. This will be Tanjinder Singh. Tanjinder Singh is a software engineer at Capital One. He is passionate about distributed systems, cloud computing, AI, and scalability. He enjoys mentoring others to be successful. During his free time, he likes to joke and enjoy some chai. So Tanjinder was not able to come and present his session live, so we will show his recording. So I'm sure it's gonna be amazing and very interesting. So get ready, we'll show it in a moment.
Hello everyone, welcome to this talk on architectural patterns for cloud native applications. My name is Tajinder. I am a software engineer from Capital One. This is an intermediate to advanced level talk, so I expect the audience to be familiar with the basics of virtualization, containers, Kubernetes, microservices, cloud native applications. But I'll definitely go over the basics real quick before we dive deep into the patterns, which we will be demonstrating how we can use those patterns. In terms of agenda for this talk, we're going to start with discussing the basics of virtualization, containers, microservices, and Kubernetes. Then quickly, we're going to deep dive into some problems and looking at some problems and how we can use patterns to solve those problems in the context of cloud native applications and in the context of Kubernetes. With that, let me get started with looking at the traditional model, where you can have like one computer and that computer is tied to hardware, and this hardware can be CPU, memory, disk, or some kind of network, right? So this way, like you can run some applications on your computer, and those applications will be managed by operating system. So this is a traditional model, like how every machine comes with a set of hardware attached. Another way to look at this kind of approach to use the hardware resources is virtual model. In virtual model, you have an abstraction layer which sits in between your hardware, and you can spin up multiple virtual machines. Those machines are sharing the underlying resources. So this concept is called virtualization, where by introducing a layer in between your computers and machines and your hardware, you can utilize these resources in a better way. So you can have a better resource utilization if you are utilizing the concept of virtualization. This abstraction layer is called hypervisors. There are two kind of hypervisors available. One of them is called type 1 hypervisor, which sits directly on hardware, and you can spin up a bunch of virtual machines on that hypervisor. This hypervisor sits close to hardware, so it's relatively faster in terms of performance, and this hypervisor is also called bare metal. Um, then we have another type of hypervisor called type 2, which sits on top of operating system. And then you can also spin up multiple virtual machines on top of this hypervisor. This hypervisor is also coming closer to hypervisor 1 in terms of performance. So most of the hypervisors used in the industry these days are type 2 hypervisors. Now this idea of virtualization is clear to us now. Let's look at two important concepts and the difference between them, like virtual machine and container. Virtual machine is also used in virtualization, and containers are also helping us to use virtualization technology. But they are little different, and they are doing it in a different way. In virtual machine, it's using called server virtualization, where you have to have hypervisor installed, and that hypervisor will enable you to spin up multiple virtual machines on top of that hypervisor. Each virtual machine has its own operating system copy, which we call guest operating system. And if you look at containers, containers do not require any hypervisor. They can use operating system virtualization, and they just need a container engine so that they can run on that container engine, and some container runtime. Docker is one example of container runtime. And if we can see, like, containers do not have their own operating system. They're pretty lightweight, so they are natural fit for microservices and cloud native applications in these days. With that being clear, let's quickly take a look at what actually are cloud native applications. Cloud native applications are comprised of a set of smaller components, specialized components, which work together to achieve a common goal. For example, it might be an e-commerce application, which might be cloud native application, and the e-commerce application might have like smaller components. One might be payment, another might be checkout, another one might be adding to cart. These components work together to achieve some shared goal, and that goal might be placing an order online, right? So that's just an analogy to when I say cloud native applications comprising of multiple specialized smaller components, right? And the natural fit for deploying these components is containers, and the architecture style for deploying these smaller specialized components is microservice based. So that's why, like, you can have cloud native microservices, right? the problem with large number of containers, for example, you may have millions of containers running, right? So you cannot manually manage, start and stop all those containers, right? So you need some kind of container managed platform. Kubernetes is one example of open source container management platform. So for the remaining of this talk, I think it will be required to have some basic knowledge of Kubernetes. I'm going to quickly review 3 important Kubernetes resources. One of them is called pod. Kubernetes pod is a set of containers. You can have one or more containers running within a pod, and these containers may collaborate with each other over network or via some shared volume or shared disk. Um, Apart from pod, there is another Kubernetes object. In order to deploy these pods, you can use something called deployment within Kubernetes, and that deployment uses something called replica sets. So these 3 objects will be used again and again in the examples which we're going to talk about when we're going to talk about applying architecture patterns. Before we even talk about patterns, I want to quickly define the pattern. So there are some commonly occurring problems throughout in the software development lifecycle, and there are standard solutions repeatedly available. So you can use those solutions to solve certain kind of problems which are very common. These solutions are called patterns. For example, you have gang of 4 patterns in when you design your software, right? Similarly, for cloud native applications, you can use certain patterns to solve some commonly occurring problem. Uh, Let's take a look at a cloud native sample application. For example, this is a sample cloud native application might be deployed on Kubernetes. This has a front end tier, this has a back end tier. This front end tier might be running multiple microservices, multiple containers here. You might be running a separate set of containers here. Containers from web layer can talk to containers in backend layer on specific port, like if it's a database, might be MySQL database containers running here. And then there is a load balancer in front of backend, and there is another load balancer in front of front end, protecting basically your web front layer so that it can balance the load as it comes. And entire application is deployed in Kubernetes. So all these are Kubernetes objects. This might be ingress object. This is a deployment object. So that means it is deploying the set of pods on this layer. So this is another deployment object, right? So we're gonna talk about some problems, commonly occurring problems, which are applicable to this application. This is a cloud native application running in containers. And then we'll see like which patterns we can use to solve those problems. So let's start looking at those problems one by one in the context of this application. So one problem which might come across is like you have a lot of containers running on front end, lot of backend containers. How do you make sure if you have a new version of your microservice, if you want to deploy it, release a new version, or some kind of upgrades you want to perform on the database? How do you make sure your downtime in production is minimized so that your customers are not impacted, right? So this is a common problem, occurs pretty much everywhere, and there are patterns available which we can leverage. And those patterns, the category of those patterns is called deployment patterns. Let's look at some deployment patterns or deployment strategies to see how we can solve this problem using those patterns. First one is fixed deployment. What you can do is, if you are running Kubernetes pods using an older version of your Docker image, version 1.0, and let's suppose now you have version 1.1 available, you want to roll it out in production, and you have a service object in Kubernetes, and your service is currently pointing to your old version, right? So in fixed deployment, what Kubernetes does is it basically checks, okay, what's your target state, and then it will say, okay, the current state is 1.0, target state is 1.1, and something has changed. Then Kubernetes will check, okay, what kind of deployment strategy are you planning to use for this kind of upgrade or this kind of release. If it's a fixed deployment, Kubernetes will automatically scale down all your pods at once, all at once. It will tear down all these older pods running older code, and then it will spin up the new pods using the new version. And after that, the service will switch to the new version, right? So that's how the fixed deployment works. It is simpler to implement, but there is a drawback there. There is a trade-off there. By the time like your 3 pods are gone, your service is kind of down, like you don't have a new pods coming up again, because all of these happens in a sequential way. So there is a downtime until you switch to the new version and those new versions are ready, right? So there is some downtime with the fixed deployment strategy. In order to minimize or to have a zero downtime, there is another strategy which we can use, that's called rolling deployment. In rolling deployment, you don't actually turn off all your pods at once, and so that your service will be impacted. What you rather do is you do it one by one. you shut down your one of the pod and spin up another one with a new version. Kubernetes handles it for us behind the scenes. You just need to tell Kubernetes your deployment strategy is a rolling deployment, and this is your target state, and Kubernetes takes care of this, applying this algorithm, right, in a rolling manner, so that you don't have any downtime. So at any point of time, your service is pointing to both versions, version 1.0 as well and version 1.1, until your entire switch is completed, right? So this is interesting. There is no downtime, but there is a important point to mention here is your application itself should be designed in a way so that it can run your against the database with both versions, right? So if your database is not compatible with version 1.1, let's say, then your application will start erroring out, right? So you need to design your application in a way that it should run with both versions on a specific schema of the database, right? So you might need to think about some schema upgrades while upgrading from 1.0 to 1.1. Was there any schema change, and how you tackle that schema change? Like, it should be fully compatible, it should be backward compatible, and it should also be forward compatible. So you need to take care of your application design a little bit. There are two variations of rolling deployment. One of them is called blue-green deployment. It's a rolling deployment. That means there is no downtime. But the approach here is, instead of doing one by one, you actually stand up all three pods in advance with the new version, with the new replica set and new deployment object. And then you start testing your application here. And if you're successful, then you kind of switch your service to the new version that way. So you are running at full capacity, both old versions and new versions, and then you test out new versions. And then once it's all fine, then you switch the traffic from blue to green, right? So this is kind of strategy to split the traffic. It's a rolling because there is no downtime in this approach as well. Another flavor of rolling deployment is called canary releases or canary deployment. In canary releases, what you do is you kind of split your traffic, like 90% of traffic goes to the old version, 10% goes to the new version. You kind of start doing the rolling deployment, then you pause here, like you start testing just one pod. If your application is running fine with the new version, then you continue the remaining part of the rolling deployment, right? So you kind of start your rolling deployment, pause, test your application, then resume again, right? So this is called canary strategies, where you can run canaries, like smaller deployment, just to test out your applications for a certain set of traffic. This was basically all talking about the problem, how do we easily deploy releases, right, without much downtime. Let's look at now the second problem, which might come across on the same application, right? So you might want to enhance your application. You might want to add some logging, monitoring capabilities to your main application, but you don't want to touch your core business logic, right? So this is something similar to aspect-oriented programming, where if you want to add some new cross-cutting functionalities, you rather decouple that from your main business logic, right? So the intention here would be, okay, not to modify your existing container, but to basically use something, or maybe some other container, right? And that's right, there is a pattern exists for this problem as well, and that pattern is called sidecar pattern, right? So for sidecar, what happens is your main application, your core business runs in the main container. Let's suppose in this case, your main container is actually reading some data and serving the request from the disk. Now, if you have a requirement, you want to update this data from some other outside data sources, you can run a sidecar container within the same pod, Kubernetes pod, and that container will be responsible for updating the data, so that this main container doesn't need to worry about that aspect as well, right? So you can utilize sidecar pattern to solve this kind of specific problem set. There are two variations of sidecar patterns. One of them is called adapter pattern. Adapter pattern is where basically someone from outside wants to access your main container, right? So rather than allowing direct access to your main container or your database, you might run a separate container called adapter. One use case might be, for example, this container is writing some metrics to the database, but this metrics are, let's suppose, in some specific JSON format. And you have some external system, monitoring system, which wants to read those metrics, but that external system doesn't understand JSON. Let's suppose it might understand some other data format, right? So your adapter container actually can read those metrics and transform those metrics and give it to the external systems like Prometheus, export it to there, right? So that's another example of sidecar pattern. Another variation of sidecar pattern is called ambassador pattern. This is particularly useful, like if your container wants to go access some external systems, right? So rather than going directly to external systems, you can introduce a proxy or some kind of ambassador container here, which will actually, your main container will just talk to some port, and behind that port, ambassador container will intercept that request and actually will be responsible for writing the data to external systems, right? So your main container is only not worrying much about what's happening behind that port. It's only thinking, okay, I'm gonna send a request to this port, and behind the scenes, ambassador container will tackle everything, right? So a master container can also write to caches, right? So you can write some data to caches as well. So this is another way to decouple. So this was a nice way to decouple your separation of concerns from your main container using sidecar pattern. Let's look at another problem where you have like hundreds of microservices running on front end and many microservices on the back end. How these microservices, how do they talk to each other, right? They might need to know the IP address of each other, right? So that they can send some network traffic to each other, right? But as we know, like these IP addresses are always dynamic, right? So the servers go away, a new server comes up, it will have a separate IP, right? So this approach, having a static IP address to talk to each other for these microservices is not a good solution, right? So these services should be able to discover each other dynamically using some kind of service registry. There is a pattern called service discovery pattern, which allows us to basically implement or design the solution to this problem, where some of the services will register themselves to the service registry, and then the consumers will look up for these services using service registry. Service registry will give them a handle or address which they can use to invoke the service, right? So this way, service registry is taking care of all those concerns. Like if the IP addresses are changes behind the scenes, it might use some DNS lookups or those kind of strategies. Within Kubernetes itself uses this pattern a lot. Inside Kubernetes, there is a object called service, and you actually call that service, and that service will be able to identify which set of pods or which set of containers this request will go, right? So it uses something called label selector. But in order to invoke that service, you need to discover that service. And in Kubernetes, you can use DNS lookups to discover that service. So this pod can use some DNS lookup to actually contact this service. So this is one way within Kubernetes, internal to Kubernetes cluster, you can discover the services using DNS lookup. But sometimes you might need to access the service from outside the clusters. In those cases, you have a couple of options. One of the option is you can have if you're using some cloud provider, so you can use some load balancer, for example AWS load balancer, which can discover this service on your behalf. Another option is you can use Kubernetes ingress object. It will actually automatically discover these services, and it can also do some like HTTP path-based routing because it operates on the application layer, right? So these are the ways you can discover services like within the Kubernetes or outside Kubernetes using service discovery pattern. With that said, now let's look at a couple of more advanced problems which might occur in the context of these applications. You may have a use case where you might want to update your microservices or your containers based on some event, right? So you may have some event like you want to deploy a new version, and you are changing your Kubernetes config maps, and then you want that new version to get deployed, right? So based on some event or based on some metrics. Kubernetes itself does that for us because it takes care of all the deployments. We just need to specify the end state declaratively and takes care of deployment. But behind the scenes, Kubernetes makes use of certain patterns, right? So one of those patterns which can be used to solve this problem is called controller pattern. Controller pattern is effectively works on the three things: observe, analyze, and act. There is a controller application which always runs in the background, which will actually observe the events from the API server within Kubernetes. And then it will say, okay, what shall I do with this event? There is some logic here, and then it might act according to that logic. So this pattern itself can be used anywhere, not just within Kubernetes. So you may write your own controllers within Kubernetes, and those controllers might be doing some application specific logic, but the pattern itself stays the same. So you can make changes within to your microservices via Kubernetes using controllers. So controller is something you can write yourself as well, and there are a lot of controllers already written within Kubernetes which are handling the automatic deployments for us. So those are all handled by controllers. Kubernetes does a lot of state reconciliation or using a lot of controller watch loops to achieve actually a lot of use cases. Then there may be another advanced problem, which you might want to update your applications. Earlier, we were talking about internal events within the Kubernetes cluster. But how about if you want to update your microservices or cloud native applications based on some external event outside the cluster? For example, you may have a DevOps person, operator person who might want to do some weekly maintenance, right? Or looking at some other dashboard metrics, you might want to scale, or you might want to run a new version of your microservices, right? So that event, Kubernetes won't know about that event, right? Because it's external to the cluster. There we can use a pattern called operator pattern. Pattern is basically an extension of controller pattern. So that means it will utilize the same concept of controller pattern, basically observing the event, analyzing, and acting on behalf of operator in this case. So in this case, you can specify your own custom resource definitions within Kubernetes. So what will happen is, so these custom resource definitions will understand your custom domain, which Kubernetes won't understand. So you can specify the rules there, like for a specific event, you might want your controller to basically spin up a new version of microservice on a new pod, right? So you can define all those kind of rules, and defining these rules together with a basic controller pattern, it's called operator pattern. It's called operator because it's basically working on behalf of an operator or some human maybe who wants to do some operation on your microservices which are deployed in Kubernetes, right? So there is a pattern which you can leverage, and underneath you can use controllers for this as well. You can write your own controllers, which might be more complicated because they will be tailored to your custom domain, which Kubernetes may not understand. But this is possible using a plugin based architecture where you can plug in your own custom controllers. So if we quickly compare about these operator pattern with the controller patterns are a best fit. Like if you want to do some action within the Kubernetes cluster based on some events which Kubernetes understands already. For example, you might update some config maps within Kubernetes, which Kubernetes understand because config map is a Kubernetes object. And based on that, you can say, okay, within config map, you can tell Kubernetes, I want to deploy a new version of my Docker container. So you can also write your own controllers. So if you want to use the objects which Kubernetes already understands. But as soon as you have some more advanced use cases where Kubernetes doesn't understand something, then Kubernetes allows you to specify those in custom resource definitions. Then this adds more flexibility, but this adds more complexity as well. Now those rules will be very complicated and complex, so you have to do some engineering over those areas. So Kubernetes actually is pretty extendable. You can extend your controllers to your operators based on your use case. Let's talk about one last problem statement, then we'll wrap it up. There is a common problem which occurs in all the microservices in the cloud native applications which are deployed in containers. You are always willing to elastically or automatically shrink your infrastructure or expand your infrastructure based on the load, right? So you don't want to pay the money by running like 10 servers all the time if only one server is required, right? So it's to avoid overutilization and underutilization, right? So there is a pattern called elastic scale, which can be used to solve this kind of problem. Within Kubernetes, you can do like three kind of auto scaling. One is called horizontal auto scaling, where you can add more pods to the existing pods if your load is increasing. And the way it works is Kubernetes is using something called horizontal pod autoscaler. What it does is it will actually monitor some of the metrics, which you can define your own metrics as well here. And for example, if you say the CPU utilization goes above 90%, then spin up one more pod, right? So it will check those metrics, and if see the thresholds are exceeded, then it will actually trigger a new deployment which will add one more pod to your existing pod. So it will automatically scale horizontally your existing pods. When within pods you are running like multiple containers, maybe one container per pod, right? And those are actually your microservices or cloud native applications, right? So you can automatically scale your applications elastically using this pattern. And within Kubernetes, this is supported out of the box using an object called horizontal pod autoscaler. Another variation of autoscaling is called vertical pod autoscaling. vertical pod autoscaling, instead of adding new pods, what you do is you add more capacity to existing pods, right? This also works with using the same pattern, but the object here is called vertical pod autoscaler. It will also monitor your metrics, and you can also hook up events with this one. And based on these two, you can have some kind of logic, some kind of policy, and pod policy, and then scaling policy. You can say, okay, I want to add more resources, like add more CPU or maybe add more memory to the pods because of the vertical pod autoscaling. So this is also supported in Kubernetes using vertical pod autoscaler. So this all is good, right? So you can scale horizontally and you can scale vertically. But what happens, like, if your Kubernetes cluster itself doesn't have any resource? By that, what I mean is, like, you have, like, let's suppose 5 workers in your Kubernetes cluster, or maybe 10 workers, and those workers are running pods. But what happens if those workers themselves don't have any resource, so that they can't even spin a pod, right? So if you try to do horizontal scaling, it will fail because there is all the workers are busy, they don't have any resources. If you try to do vertical auto scaling, again it will fail. So how can you still scale in that case, right? So somehow you have to add more capacity to your cluster. So right there we have a pattern called cluster auto scaling, and this is supported by a different object within Kubernetes called cluster autoscaler. So what you can achieve here is based on some event, like event in this case might be if you are not able to schedule a pod, so it will be, say, unschedulable pod in this case, just because all the workers are basically constrained, they don't have any more resources. Based on these events, you can trigger cluster autoscaler, which can spin up new workers. Once those workers are ready, then those pods will be scheduled here according to whatever scaling policy you have. You might have a horizontal or you may have vertical scaling policy defined. So as soon as a new node is available, then these pods will be scheduled automatically. So that's how you can elastically scale your applications and also your infrastructure as well, using these objects within Kubernetes, which are using elastic scale pattern. With that, let's quickly summarize what we have talked. We talked about the basics of virtualization, containers, microservices, cloud native applications, and we took a look at a sample cloud native application deployed on Kubernetes and containers. We realized that there are common set of problems which apply to cloud native applications, and there are some specific patterns which we can use to design or solutions to those problems or solve those problems. So we realized that even a simple microservice, if you want to deploy it in production, you need a solid understanding of distributed system, and also you need to know some container management platforms. Kubernetes is one example which is worth to learn. If you wanna learn further, you can basically, I think Kubernetes and containers are definitely worth learning. Another thing we notice is that now engineers, apart from writing business logic, they also need to be a little more fluent, at least in terms of picking the right design and architecture styles when it comes to cloud native applications and microservices, because there are some problems which are common, and there are patterns available which can be utilized to solve those problems. These are the main takeaways, and using these architecture patterns, I think it's a good start when we start thinking about designing and deploying cloud native applications. And I want to thanks everyone who joins the talk. I'll be answering your questions. Please shoot your questions in the chat. I'll be answering them later in the Q&A session. It was great talking to everyone. Thank you.
So thank you, Tajinder. It was really interesting and valuable information. So don't hesitate and leave your questions in the chat below. And actually, you can leave any question related to microservices, because right now it is microservices blog, and later on Juan Sanchez and Orkhan Gasimov will be able to answer all of your questions. And right now, we are ready to present our next speaker, who is Fernando Harris. Fernando is a cloud architect at Oracle EMEA, working with SOA, microservices, and DevOps-related technologies. Before joining Oracle, he worked as a middleware project manager in the UK and as a SOA developer in Portugal, Cape Verde Island, and East Timor-based customers. So he has kind of international experience. He organized the Cloud Native Computing Iberia meetup and is a member of Vido Team Spain, a special task force team specialized in cloud native implementation. He could he holds a master's in information system management by the Technical University of Lisbon and bachelor's in computer science and business by the Polytechnic Institute of Coimbra. Fernando is going to present his talk, Microservices-Oriented Architectures, Cloud-Native Impact on Solution Design. Unfortunately, Fernando was not able to join us live, but we are going to present his recorded session, so we'll be back in a moment.
Thank you very much for the introduction. My subject today is microservices-oriented architectures and the cloud-native impact on solutions design. Just a few more words about myself. So my name is Fernando Harris. I'm Mozambican Portuguese, and I live in Spain, Malaga, with my beautiful wife and son. I love to play guitar. I love to play capoeira, not necessarily in this order. And I'm a cloud architect at Oracle Cloud. Okie dokie. Let's start. So I start working as a developer with 4GL, Informix 4GL, and then I moved to a role as an integration developer or integrator. So in this my first IT job, I was actually working as an Informix 4GL developer, as I said. So I was developing these dashboards and stored procedures to pull and push back and forth code against databases. But there was a day I remember that I had to develop a stub. Actually, for Mix 4GL, you could actually compile stuff with C compiler, and then you could actually use these, call these functions, these C functions from other things. So in this case, you would be calling this from a C++ stub, and this C++ stub was going to be consumed by this EAI platform. It was the first time I actually understood the importance of integration. It was the first time that I was actually involved in a project which was not only related with the app or the application I was playing around, right? Years later, I've actually joined that EAI team, the integration team, and I start working on this EAI platform, and I start developing services to call stored procedures, very much like those I would be developing a few years later before as an Informix 4GL developer. And this was my first perception of the importance of integration and IT as a business enabler through integration of systems inside the organizations. So let me just discuss a bit as an introduction, IT as a business enabler. Well, when in 1985, Porter and Miller actually as well said that information technology is changing the way companies operate, and that the entire process by which organizations create their value and products is being affected by that, right? So actually the organization value chain is a subsystem of linkages or interdependencies. Each activity in this chain affects the cost and the value of the subsequent activities in a sort of domino, okay? So linkages between activities create trade-offs in performing optimizable different activities, okay? So it looks a bit that Porter could be talking about software life cycle management. Of course not, I'm kidding. But he was talking about something much more wide, with a much more global importance, which is the organization value chain. What is cool about this is that the software life cycle is part of this value chain, organization value chain. Okay, so this is very important, and these linkages can also be identified in the software life cycle life cycle. Okay, moving to the architecture. Why? So, as IT enables business to change and to move forward, architecture is the visible face of the organization's ability to change. Okay, it represents the past, it represents the present, but it also represents the future state of IT, and is what we call the architecture. So it's a living and dynamic entity, which may seem static, but it's dynamic. And it has the objective or the mission to address these ever-changing needs which the organizations are always suffering. And we know that it is impossible to accommodate organizational complexity without a structural logic. Even with the structural logic is very complex. But this structural logic is what the architecture represents. And the architecture represents all the components, both technical and non-technical, which affect the supply of information to the organization, being the information the goal here, right? So it is also concerned, and this is what I would like to emphasize now, with how these components are linked together and they function as a whole, okay? This whole being the architecture. Each of the different boundaries, and some are present in this table you can see now in your screen, represent a different perspective of the end product. The end product being the organization itself, okay? So this is important to understand integration architecture evolution and complexity, okay? So systems development is about developing software, we know, and it's about also when we are doing this within an enterprise or within an organization, it's also about integrating these applications. So different applications will be composing the enterprise system, and they represent a complex set of functions which will need to communicate with each other. So in order to do that, what we need to do is to integrate, of course, but we know that this is very complex. Actually, Brooks, in his Mythical Man Month, addresses some of these aspects when he actually identifies identifies a really nice approach to measure relative programming effort. Okay, so Keenan Gambino revisited Brooks and presented this very interesting and already old graph where you can see that only 10% of the total effort is actually coming from coding. Okay, so moreover, if X is the effort required to write and test the program, 3 times is needed to make it into a product and 9 times to integrate it into system product. This is very clear, right? And this can be in part explained by the fact that the organizational reality contains information systems based on different technologies, different operating systems, and communicating in different and sometimes incompatible protocols. And some of the most famous and important application systems have emerged in order to integrate these heterogeneity or these heterogeneous systems. For instance, the EAI, which I already mentioned in my introduction of the enterprise application integration, saw its success largely explained by the ERP's inability to fulfill the plan of homogeneous integration of information systems. Okay, how? Leveraging workflow technologies, typically based on XML, and which then trigger the proliferation of XML techniques such as XPath, XQuery, XSLT, and they were actually typically working these frameworks on Java enterprise platforms and supporting directly protocols or standards such as ODBC, JDBC, RPC, message-oriented middleware, message brokers, Corva, enterprise Java Beans, database adapters, and web services. So EAI, or Enterprise Application Integration, was actually the first attempt to industrialize distributed architectures inside organizations and generalize a couple of concepts which are still very important. For example, the concept of integration patterns based on synchronous versus asynchronous, or tightly coupled versus loosely coupled, or concepts such as event, service, and messaging. Okay. So the problem, unfortunately, the problem of integrating organizations is much more than just technical. Okay, so as we cannot properly address the complexity of the organization or the communications between the organization resources without understanding the very nature of the impacts of those same communications on IT and the way the organizations building systems to support the organization's critical business activities will receive these impacts from the organization's structure, organic structure. Okay, this is something which is explained by Conway in 1967, and it basically says that systems designed and integrated by an organization will be a faithful copy of the organization's communication structure. As organization structures can be flat or hierarchical, these will result in systems which will reflect this. So if there are many dependencies between the different organizational functions and many layers of dependencies in order to take a decision, you'll certainly see that reflected in a more tightly coupled organization. Whereas if you have less dependencies and more autonomy to take decisions, you will have a more loosely coupled organization. Okay, so these attributes, according to Conway, will be reflected on the systems in the organization systems design. This is awesome because will takes us to our next stop, which is related to the fact that in order to build these systems and these architectures, which could potentially increase the organization ability to change more quickly and with more agility, not only technology is needed. Okay, you need something more than technology. And architects felt the need to define agnostic principles, best practices, and patterns. And this is what we are going to revisit in the next slides. And we start with domain-driven design. So domain-driven design was coined by Erik Wilde and presented in his book, Tackling Complexity in the Art of Software, Domain-Driven Design. And it's basically a design standard to develop complex software systems, okay? It simply states that whether from a technical or business point of view, people involved in the product development, or for the sake in the project organization, if you wish, should have a more than fine knowledge about the problem domain. They should also be experts on that problem domain. This should be complemented with proper quality assurance techniques, of course, and by using technical and strategic standards to achieve good modeling and development practices. Some of these good modeling uses as a baseline concepts such as entity, value object, services, repositories, or aggregates. Okay, but they start with much simpler concepts, which I would like to address here very quickly. It starts immediately with this interesting concept of language. And here we can see the Babel Tower. An ubiquitous language is needed, and is the first step towards a common and normalized vision of the domain. Okay, so it's the very first step in order to conceive the canonical perspective of the organization and its specific domains. It should be created by all teams involved in creating the system, whether business or technical. But it's a non-technical common language of communication, okay? And as I said, to be used by developers, by domain experts and architects. So for example, in a typical object-oriented approach, terms such as classes or polymorphism should be avoided, okay, if possible. And the terminology should reflect domain functional needs and not specific technical approaches, right? At the end, of course, we are trying to model software and have its concepts properly aligned with the business concepts. So sometimes it's probably impossible to it can happen, but we should try to avoid using technical jargon in this case. And then there is this other concept, which is the model, and having a common way to describe the domain ecosystem will then accommodate the design of domain models. Okay, so we can think in a model as a map, an abstraction to help people getting to know where they are. So these domain models can be designed under tactical, or strategical patterns, and can basically consist in sets of classes or entities with its respective attributes and dependencies. And these models and these classes and these entities will live in what we call bounded contexts, okay? Inside the domain, we will have different bounded contexts. And depending on the complexity of the domain, the more bounded context we might need to address. Each bounded context might need to have its own terminology, okay? Its own language, its own universal language, its own ubiquitous language, which it means that we can end up with multiple canonical models, as and according to Martin Fowler. Another interesting concept is the concept of context maps, and the relationship between different bounded contexts is called context maps, and it defines the way or ways that the different bounded contexts will communicate. We cannot forget that they have different ubiquitous languages. So, and there are many different communication patterns between bounded contexts. Okay, technically speaking, we can simplify these different communication patterns by reducing to 3 different implementation approaches: RPC, REST, and messaging. But of course, we can talk about many more patterns, such as shared kernel, customer supplier, conformist, etc. Okay. Let's now move to another very interesting architecture or principle, which is the event-driven architecture, EDA. Event-driven architecture is made up of the coupled event processing components that synchronously receive and process events. It can be used as a standalone architecture style or embedded within other architecture styles, such as microservices or SOA, right? Event-driven architecture is a software architecture paradigm promoting production, detection, consumption of, and reaction to events. Okay, I've used here this picture of Fire and Forget, a very old computer game, because it reminded me one of these the ways we could call this type of services or this type of patterns, which will be the Fire and Forget, right? Where you send the message and you send it to, you don't wait for a notification or for an acknowledge, you just send the message. Okay, so it's interesting to define event and message-oriented middleware, as an event can be defined as an important change occurring within a domain. It is not an instruction to make something happen, okay? It's not an instruction to necessarily trigger whatever. It's not even a message, okay? It's just an event. It's just something which happened, just that, okay? An occurrence. So this architectural pattern may be applied by the design and implementation of applications and systems that transmit events among loosely coupled software components and services. Its physical implementation is typically based on traditional components such as message-oriented middleware, okay? Now you know why we have message-oriented middleware here. So it's also, before moving to message-oriented middleware, it's also important to say that the loosely coupling and horizontal scalability are two of its most crucial attributes, and as such, they are highly resilient to failure, okay? The loosely coupling goes to the point that each of the different event agents and consumers are usually not even aware of each other. This is very close to related to what I've said the previous slide regarding the fire and forget concept, okay? So, and what is this message-oriented middleware? So in order to easily support all these communicating components of a client-server architecture with asynchronous calls between the client and the server applications, a type of specific application was born, was created. We are talking about message-oriented middleware, okay? And this type of software creates an abstraction layer within distributed and heterogeneous platforms, which reduces the complexity of developing applications that can span multiple operating systems and network protocols in order to send and receive messages, okay, in a loosely coupled fashion. There is a relationship between domain-driven design and event-driven architectures, and we just need to think about an event, and we think about the fact that occurred inside a domain or inside a specific modern context. These domain events must be designed and published according to its tactical needs, but would always be important at a strategic level as well. Okay, so for instance, in domain-driven design distilled by Vaughan Vernon, it says that the publishing bound context, as an aggregate that publishes a domain event. Okay, then the domain event eventually makes its way to a messaging mechanism, whatever it is. The messaging mechanism then publishes the domain event to the interested parties or the subscribing bound context. Okay, there is this concept of subscribing applications, or in this case, as we are talking about DDD, subscribing bound context. And those subscribing bound contexts receive the domain event and then react to them by updating an aggregate or multiple aggregates in the subscribing bound context. Okay, but there is a very important question to take in consideration when applying this tactical approach, and that is that the correct order of messages must be guaranteed. The cause is always before the effect, and as such, the principle of causal consistency must always be applied. Finally, SOA, or service-oriented architectures, a very famous term and terminology, which is not just an architecture, it's also a principle or a set of principles, right? It starts with this concept of service orientation, and service orientation, as you know, is the simple act of exposing a service and allowing other clients to consume it. Okay, so, and service orientation is often seen as the first step towards SOA or towards SOA. However, SOA is a much broader concept when applied inside the organization, as it has real enterprise implications on its design and philosophy. Okay, so It's service orientation is an approach to development, and service oriented architecture, as I said, is a global paradigm for enterprises. When we talk about services and in services oriented architectures, we mean pieces of software functionality that will be used and reused and shared by other pieces of software when needed. Service oriented architecture is a type of architecture and a philosophical principle, okay, that results from applying service orientation, which is basically the underlying paradigm. Okay, according to the SOA manifest, there are a couple of principles: business value, strategic goals, increasing interoperability, shared services, flexibility, and evolutionary refinement. Okay, and its topology, its conceptual topology is visible in this table here, and you can see that these at an enterprise level, services typically rely on the service bus, and it will span across different perspectives. We end up having enterprise services, business services, infrastructure services, and application services. Also important is to say that the principle of shared services is a simple purpose and well-defined function that is available under a contract to get consumed by service consumers and to get shared by service consumers. Okay, these services are governed through a global service directory in what we can call service discovery, and then each service must individually advertise its contract, which is basically the right way to get called, and these we can call service negotiation. Then one very easy way to define SOAs as the universal interoperability between components, regardless of operating system, programming language, network proximity. And this was typically and traditionally achieved through the usage of web services standards, which help shape what SOA is, and normalizing XML and SOAP in particular, okay, with XML for application integration. The relationship between event-driven architecture and SOA and domain-driven design is real, okay, and it's positive. I mean, in the case of event-driven architectures and SOA, you have event agents, whether emitters or receivers, and those can be perceived very easily and designed as services. In reality, any component of an event-driven architecture can be a service. Hence, we can design SOA and complement its synchronous integration requirements following event-driven patterns. And the SOA and the DDD also have these relationship. Services can also be perceived and designed as a concept, and they should, belonging to a specific context inside a specific domain. We can easily see a client modern context calling or consuming a service modern context. Okay. This takes us finally to microservices, and we saw that, and we are seeing that at some point, domain-driven design, event-driven architectures, and services-oriented architectures cross their paths, right? In some way, as I said, these three principles and architectures can be perceived as the direct ancestors of microservices. The same is to say that if we really want to understand what microservices are and where they're coming from, studying each of these disciplines is fundamental and advisable. However, they kind of share the same ancestor, but they are not the same thing. They are related, but they are not the same thing. So when we actually, for instance, discuss microservices and services-oriented architectures, and it's obvious a couple of similarities they have, but they are not the same thing, of course not, because actually, they both rely on the service concept and on the specialization and limited scope of that service. Okay, but for instance, microservices will use much less elaborate and simple messaging systems compared to SOA, and were not created to be part of complex service compositions. As we go through the SOA manifest, some of the principles could be easily applied to microservices. But for instance, the SOA principle of shared services is discussable under the microservice philosophy, as a microservice can share, but should avoid that. Okay, a service in SOA, for instance, is probably going to share its data storage, while in microservices, this pattern should be avoided, and for some considered an anti-pattern and avoided at all costs. Okay, so then microservices and event-driven architectures. Microservices are not necessarily event-driven, okay, but they work very well with message-based communication mechanisms. It's very easy to idealize a microservice implementation strategy based on event-driven architectures with a message broker, for instance, as the more loosely coupled, the better, right? So in microservices, independency and autonomy is very important, is critical, and that can be implemented through messaging systems based on queues and topics, and hence this relationship between microservices and event-driven. Finally, a microservices and domain-driven design. Microservices should be built with the concept of business capability on the architecture's mind. In order to identify and catalog critical business capabilities, the architect might get tempted to develop a global or unified model of the entire business. These would not be cost-effective or feasible. According to Martin Fowler, microservices should essentially be structured under a domain of multiple canonical models. This is, my opinion, this becomes especially important when addressing one of the microservices' biggest design and technical challenges, which is the fact that each microservice and within its bounded context should own and manage its own independent data storage. Okay. So microservices and the microservices architecture is a polyglot and protocol HTTP REST architecture proposal, which consists in composing systems with bounded isolated components. Each of these bounded isolated components or contexts should be designed according to DDD rules. Each bounded context can and should be exposed as a loosely coupled service. Okay. Each microservice is a model or a submodel within the architecture or within the domain and represents a translation of a very specific business capability. They should be built to fail and to scale and to be releasable as fast as possible. And this is actually where the business value comes in. Deployment strategy should be easier and less risky, as in theory, the microservices do not depend or should not depend on synchronization between different services or libraries, and they are managed in a decentralized way, right? So, and finally, they have as a working baseline this concept of team collaboration, as they are very closely related to DevOps and Agile and to infrastructure automation and continuous delivery as well. Okay. This takes us to cloud native, and we are very close to the end. Cloud native. So, what's the role of cloud native on this? Cloud native is a software architecture pattern for developing applications using essentially cloud computing principles such as scalability, elasticity, and agility. Okay. When we say that an application is cloud native, it means that it's designed to thrive in a cloud-based production environment. Okay. At least according to Ken Carlson in his awesome book, Cloud Native Java. So the benefits of cloud native are reflected in its principles: scalability, speed, and the cost operation model based on OpEx. Okay. So from a strategic point, point of view, cloud native takes advantage of flexible billing from cloud providers, as well as the dynamism of paying for additional resources only when needed. It allows you to dynamically add or remove hardware, instances, resources, cloud resources, without affecting the base performance of the system. The typical introduction to cloud native apps comes from the 12-factor app principle itself, which, if adjusted to the Agile manifesto, gives a perfect framework to establish other important ideas associated with it, such as continuous delivery, infrastructure as code, DevOps, and of course, microservices. So apparently microservices and its ancestors, and as we discussed before, event-driven architectures, SOA, DDD were already here for a few years already. And some companies started actually building microservices architectures under these principles even before cloud was cloud, okay? So what happens is that cloud native has the capacity to release microservices architectures and its ecosystem full potential by guaranteeing that its operational requirements are enforced in a dynamic and cost-effective way. Solution design creates the pillars to guarantee that the microservice is tolerable to failure, that is designed according to business needs and not too expensive to replace, deploy, or release, right? Solution design also helps us on scalability requirements and design the service in order to quickly scale, okay? However, it's the cloud native principles, technical, management, and operations, which will allow to achieve that in a cost-effective manner. This triggers the capacity inside organizations to make the decision, taking process less averse in terms of risk and cost management. Risk and cost are usually responsible for blocking and serve as an obstacle to companies trying to change, okay? So cloud native is the last chapter in this technical narrative, which is actually changing the way solutions are designed, not only for microservices as would be naturally expected, but also for other approaches based on SOA and event-driven architectures, okay? Other more traditional approaches, as cloud native is and should be agnostic to the architecture you are implementing. I mean, you don't really need the cloud native stuff to design solutions such as microservices, but the cloud native principles are what makes a difference when these needs to become more appealing for the organization, okay? Cloud native impacts are mostly operational, okay? They are mostly operational, and they can help shape the evolution, not just of microservices, but also of more traditional architectures such as service-oriented architectures and event-driven architectures. And actually a good example of that is Verrazano, which is an open source enterprise container platform based on Kubernetes, where you can manage and run everything in the same platform. So you are running, observing and monitoring your microservices, your service-oriented architecture, your event-driven architecture, your queries, all in the same place and monitoring all in the same way, okay? You have the link for the GitHub here if you want to take a look. Cloud native, in my opinion, can be seen as agility as a service, and it offers the organization more tools to effectively manage the linkage, which Porter mentioned in that very first slide, between added value stages inside the organization value chain. These linkages should be of dynamic nature, of course, and operationally and architecturally optimizable. They should be able to change if needed, okay? So maybe the most radical idea coming from microservices and cloud native, it's not technical at all, but organizational. In the beginning, we mentioned Conway law, which basically says that organizations' communications will be reflected in system design. IT has been always impacting the organization's architecture. And yes, we know it should be an enabler, and usually it is, but sometimes, too many times, it works as a constraint. And this becomes more visible if the industry or the market is more competitive or more aggressive, and demands constantly and systematically change. So when things go wrong, for instance, and DDD does not reflect real business needs, business will suffer a negative impact. This is typically true when change is reactive, okay, and not intentionally thought. So, but when change is intentional and proactive, that means that the model is flexible to adapt to change. The release, the concept of release is the event associated with the change and business value is materialized through the release, okay? So what threats a release the most is complexity to deploy, such as dependencies, integration testing, mostly because of interdependencies whose roots reside on organizations' communications itself. This is the Conway law working and affecting the whole process, right? James Lewis and Martin Fowler coined a really interesting concept, which they call the inverse Conway maneuver. And this theory basically says that, or recommends evolving your team and organizational structure to promote your desired architecture. Ideally, your technology architecture will display isomorphism with your business architecture. This is bold and is going a bit further than adding dev to ops, as implies the possibility of extreme change within enterprise and organizational architecture. Quickly wrapping up. IT is a transversal enabler regardless of business function, and as such should influence also the ability or need of the organization to change. Okay, IT is not a support function for business. IT is the business. This is even more clear as distributed architectures such as EAI, EDA, SOA, under principles of DDD, created the conditions to forge microservices. This architectural baseline has a lot of value, but it's the cloud native operational predicates and benefits which will allow microservices to release its full potential to the organization. Organizations are now finally migrating from a project-centered perspective to a product or service-centric perspective, where the product or the service is owned by cross-functional teams with a specific purpose. These cross-functional teams will own and manage their own microservices and respective data stores. That's it. I hope you enjoyed. And I don't know if we are going to move now for any questions. Thank you very much for your attention.
Okay, thank you, Fernando. And now we are ready for our Q&A session. But before that, I'd love to see among you, all of you among us at the QA Global Summit on March 2nd and 3rd. Either you are considering QA as a career move or have already started as a QA engineer, this event will help you get on top of practicing QA. I'm honestly really excited about it, mostly because I'm working on its preparation right now. So, a few more details. You'll get 2 days and 14 hours to learn how to build QA from scratch, what mistakes to avoid, how AI can improve testing experience, how to implement QA into development process, automated and manual testing in young QA career, past turns to take. So all this and much more valuable information, I'm assuring you, you don't want to miss this. And have time to register during a happy hour to get a ticket for only $30. I'll share the link in the chat, so go and grab your ticket. And now we are ready to meet our speakers for this Q&A session. It's Juan Sanchez. I think you remember him from the first talk. And Orkhan Gasimov, who I know is a member of program committee for this amazing event. And we are really thankful for your support in this and for joining for this session. So I would like to remind all of you that this will be a Q&A session dedicated to microservices. So thank you for joining, and I think we can start with the first question. Okay, so let me show it on a screen. And here it is. So, do you prefer to run only one application per microservice, and why? Who would like to start?
I have a question for this question. By saying to run on one application per microservice, do you mean running microservices in one instance, a single instance per microservice? Is it what was meant? Can we learn it?
I know in the morning, actually, I had to answer this same question, and we actually take a stab at it at two different approaches. One of them is that microservice, the one that I started was that microservice can actually fulfill the needs from different applications. So let's say that we are working on a service for invoices, and we have a dashboard for management and another dashboard, I don't know, for another group of users. So maybe that microservice can actually fulfill that need for both. Fernando in the morning took a different approach, that it was that they shouldn't serve two different applications. But I forgot the rest of what he replied. So I don't know if you have a different stake at it, Orkhan.
Okay, it's okay. Okay, then Orkhan, how do you think?
Yeah, sorry, I was on mute. So I will try to answer the question from how I understand it. I understand it like how many applications. I will try just a few options. So first of all, I understand it as instances, one instance or more. Well, that depends to how many of that depends to the load that you have in your system, how much the system is loaded. Well, I think it's pretty obvious that microservices are here just to be able to run in a few instances at least to enable more scalability. But then if the author meant one application per microservice, like is a microservice a single application or not, that's the second option, how I could understand the question. Well, a microservice is not an application. If you remember how we built monoliths, the application was a monolithic application. In some sense, monolith contained multiple services which ran in memory by reaching each other through, like, for example, object-oriented paradigm. When an object can be considered a service, or vice versa, a service is actually an object and it has some methods. So microservices, in some sense, are the same objects, service objects, but now they are simply split into but they are split between computers in the network, between servers. So in that sense, it's not one application per microservice, but many microservices per one single application. And there can be many applications, actually. So if you see what I mean, microservices are less than application. They can represent a single application, but they are not limited to. The main rule here is that we don't want a microservice to be a God service in a God mode which does everything. It should not. It should do one thing and should do it in a good way. So it's just a part of application, but not the application itself.
Okay.
That makes sense.
Thank you. Yes, I'm sure our listeners will be satisfied with your answers. And now the second question. So, when designing a backend architecture, how does one avoid creating a monolith or an unmaintainable microservices dependency nightmare? When is a microservice too small and when it's too big?
I can take it first. So it actually doesn't matter how small or big is a microservice. It's kind of in a joke. So when microservices can actually be macro services or nano services. What matters is that to avoid this unmaintainable hell of microservices, what you do usually, and it is what happens in projects with hundreds of services in bigger enterprise projects. The one rule is do not do a big microservice network. Create smaller contexts where you have like 5 or 10 services, microservices, and they are bound between each other because, for example, context of warehouse, context of finance or accounting, context of user account, for example, it may have a few services and it's a small context. Within single context, microservices are communicating each other independently. They know each other, they're reusing their APIs and so on, and there are not a lot of them. And then you may have many of these contexts. Between contexts, it is usually good practice not to reuse APIs of services from another context directly. Do not tie yourself to an API. Use, for example, event-oriented style or an orchestrator, like orchestration or choreography. And in this case, you will have many contexts within each context, like a few microservices, and these contexts can be split for development within multiple teams. Then you are not controlling hundreds or thousands of services. You are simply controlling a few, like tens of services per team.
Okay, thank you. Juan, what do you think?
Okay, actually, I think the same thing as Orkhan regarding the size of the microservice. I don't think that there is a way to classify something as too small or too big. Actually, it doesn't matter depending on the domain that you're working. As Fernando mentioned, there's a domain-driven design that actually is the one that drives like the size of the service itself. But again, there's no category to say that something is big or small. Now, regarding the interdependency nightmare, and actually that's something that is prone to happen when we are working with microservices. What I like to do, and is something that I mentioned on the presentation, is to have a layer that actually is the one that makes the connection between them. So, for example, the event bus or the message bus pattern is the one that can be the middleman that actually makes the communication within all the services, make that much more fluid. If you try to contact services directly, maybe that's a nightmare, and that's something that you should prevent from happening.
Okay, thank you so much. And our next question. A system with a lot of microservices, how can we find the root cause of problem?
Well, that's a hard one. Yeah, I'll start to see if I can decipher this one. Let's say that there is a problem with the flow, and imagine that there is one of the services that is the one that is causing the problems. Here, actually, we have to, as in every software development system, we need to have logging mechanisms and actually a way to define the status of everything. For example, with AWS, as I mentioned before, CloudWatch is something that I use a lot. Pinpointing the exact service might be the part that it's difficult. So maybe there will be some sort of alert system that will send the messages or the emails. And that's the way that I will find the way the service that is causing the problem. Some sort of alert system plus detailed logging in CloudWatch, for example.
Okay, thank you. Orkhan, what do you think?
Yes, I would add to that. Well, let me just try add something new to the answer. So, first of all, start with such things as distributed tracing and log aggregation. These are the places where you can find at least some pieces of information what was wrong and then where it was wrong. Log aggregation will help you at least to understand which type of service was wrong, and then using tracing mechanisms, you can actually trace exact instances, servers containing these services, so that you can find out which service was faulty, erroneous, and then the rest is just you have found it, now fix it.
Great answers, thank you. And let's come to the next question. So when there are too many microservices, how do you control the system and make sure that a single change is in a small service won't, I think it was, affect others?
I think that relates to, let me go first. So that relates actually to my previous answer. When you have logging aggregation and distributed tracing, which is more important actually in this situation, that's related to, for example, when you have fixed a bug in a service, and then it's okay, but then you have changed some logic, and it has break another bigger pipeline or a call stack where many other microservices were involved. Again, first of all, you should know which other services are calling the exact one which you are editing right now, which you are changing. First, documentation can help. Then, of course, you can employ some testing techniques like contract testing, other stuff, or integration end-to-end tests, but that's after the development. What happens before the development is actually when you have many services and when you have a lot of documentation, so you just don't have time to read it, or it can be outdated. Again, go to distributed tracing or similar tools that you are using in your organization. Find out which services are using this one, and just do that before changing the code.
Nice tip, I guess. Juan, do you have anything to add?
Yeah, I would like to add like a safety net. We like actually to make we rely a lot on integration testing and unit testing. So actually, what we have done for this scenario where we have a system with multiple microservices is to create a set of tests using Postman with Newman. So actually, we create a testing environment, and let's say that we apply a change and we thought that it didn't change anything. So we assume, as good developers that we are, that everything is fine. And then when we run the test, at least the set of flows that we automated with Postman and Newman, it will tell us if actually everything was fine or not. That's like the layer that I will add like a safety net, assuming that everything is doing okay during development, at least during testing, it will crack.
Okay, thank you both for answers. And here we go with the next question. How do you work on versioning in microservices? Who can start?
That's a tough one. I'll start on this one. Depends. For example, I have worked with REST services that actually versioning is pretty important. So B1, and then we throw whatever REST endpoints we need. However, that depends on what technology they're using. For example, if you go with GraphQL, there is a discussion whether it's needed versioning or not, because GraphQL actually allows you the flexibility to actually request for the information that you did or not. So it depends on the technology that you're using. If you're talking about a RESTful application, I would say that it's normal versioning with B1 and the rest of the endpoints, and you transition everything to the appropriate handlers. That's the gist of it from my side.
Okay.
Yeah, and I would like to, well, my approach to versioning. First of all, versioning can be a difficult part of the system, and then versioning can be, well, not mandatory part, the optional part, because you even may be just not in need of that versioning. So a few simple rules that I like to use usually is, first of all, think about which type of versioning you like. Like Juan said, is it REST or GraphQL? Are you using headers or are you using context path or in the URL? That's the, let's say, mechanism or mechanics. How will you approach this? Then versioning should be append only. If you are adding an API endpoint, that doesn't mean that you have to create a new version. It's not a new version, you just added a new feature. If you are changing or removing something, that may be, yeah, you are altering the system, then create a new version for that. After that, if you're okay with this rule, my second rule, that's not rule for all cases, but again, just a simple start or a quick start tip. Think about next schema. Start versioning at API gateway level, which doesn't which doesn't actually tell you to make another version of a service or an API gateway, or should be it a version, should the versioning be in the code or somewhere else? It doesn't matter. Start at the API gateway level, at the network or entry point level. If this will not help you, then add some kind of an experience level service, something, a man in the middle between the real service that you are going to version and the API gateway. And if this doesn't work for you, then go to the exact microservice which you are altering and version that one, specifically in the code. So kind of layered structure. First thing, append only, then start at the network or API gateway level. If you cannot route there, add some experience level microservice for a specific kind of users or clients. And if you cannot do it here, go to the end, to the microservice itself and version that.
Oh, thank you so much. I think those tips would be very valuable for our attendees, I'm sure. And let's see the next question. So, how do you maintain a large code base and manage DevOps?
Okay, so my perspective to these is about this strategy. I will take it to a higher level, to organization level. Even if you are a developer, you are a consultant anyway. Nowadays, all of us are consultants in the companies and teams we are working. So all of us can tell what to do. And if it's the best way or best practice, that's the correct way. So at an organizational level, if we see that the code base is going to be large, first of all, the strategy should be about what is the repository? How are we going to split it? So simple words like monorepo versus multi-repo, but it's not this way. It's about multi-repo, but how much multi-repo? So first, think about how are you going to split repositories? What we want to achieve is we may have many projects with smaller code bases, but not a single one with large code base. That's the key. And then branching strategies, your other processes within DevOps, the CI/CDs, and so this is the place where you want to also build another strategies that will bring you the most powerful, but in the same time, the most quickest way to build your code. If you have a large code base, the risk is actually it can be building for hours and hours and hours. Because if you even split it to smaller code bases, but there are again many projects, and within your CI/CD pipeline, how many hours or days will it take to build it? So these are two things. There is no silver bullet for this case. Just think about the repos. We want to work with smaller code bases, but there can be many projects. We can split it. And then think about how long will it take to build everything together? Can we do something to make it quicker? That's my opinion for that. But there is no golden rule, at least in my case.
Thank you. Juan, would you like to add something?
To add something, no, but I would like to emphasize in the part about having the separate repos, let's say, maintaining something that it's manageable from the organization point of view. So regardless of how big the code base is in a system, you have divided that in several repos, and each one of them have their own continuous integration system. But that's what will help the most in this.
Okay, that's nice. Thank you. And next one. So, what is the downside of microservices approach and how to mitigate them? What is the best microservices architecture approach with GraphQL that best fits with micro frontends? Okay, who will start?
I'll start on this one. Well, the downside of microservices, it comes from a understanding point of view of the business, because you will always need some sort of documentation to tell you exactly what each service does. So let's say that we divided everything really granular level. So as Orkhan said before, like you will need to have some documentation to tell which services talks to each other. And also you will have to have a context of which domain of the whole business is actually touching a specific service on it. that's like the downside that I see that most of microservices, it's a lot harder to understand. How to mitigate that, as I mentioned, documentation, or even, well, again, but Swagger documentation, or anything that could actually highlight what the service does. Now, regarding micro front ends, I gotta admit that I haven't worked with them, so I don't have a specific answer with how micro front ends will work with GraphQL. However, I have read a little bit about it, but I haven't seen much of the difference of how hard it will be in order to compare with each other. I don't know if you have an opinion on that end.
Yes, I have an opinion here. So let's answer one by one. First part of the question, the downside of microservices approaches. There are many downsides. Microservices is not the most comfortable architecture overall. If you want to go into comfortable zone, then just build a monolith and that's it. If you are going into microservices, then you have the downsides of monolith. You have some issues, I think so, I guess, with scalability, with availability, maybe with overall performance, and you have many bottlenecks. But if you are into microservices, then yes, you are going to have organizational challenges. You are going to require more development power, more people in more teams. So you have to control this somehow. And then you have to go into DevOps and operations. It's not going to be, the infrastructure is not going to be as simple as before. And well, it should somehow also align with your enterprise architecture at a higher level, because microservices are very good fit for a domain-driven or business domain-centric design. Depends on how large is the scale of your organization. So there will be issues anyway. And it depends to the company how large the project is and how you are adopting best practices. So you have to read a lot. And then there is no golden rule or something like that. Downsides will be different, depends on project and teams. Second part of the question about the micro front ends and GraphQL. It may be personally me, but I don't see a very big connection between GraphQL and micro front ends, because I see it this way. Like, micro front ends is the approach how to build a front end and not to build it a monolith, because you have, I think so, you have many modules. You want to organize them, you want to enable lazy loading of them, you want maybe to reuse some web components in a hybrid mobile UI setup, and so on. In this case, you are building micro frontends and connecting them to microservices at backend, and also you are building DevOps pipelines, CI/CD, and related stuff for the frontend too. And they have some connected services, the front micro app components that are used in the super app getting together. But then the GraphQL is actually just it's API. I think the connection is where in a micro app frontend, you will have a common foundation layer, a shared layer, which is actually responsible for communication between front-end components and maybe with backend, hopefully. In that case, that shared library or shared layer with a few of libraries will be bundled with the API like libraries that are reusing GraphQL endpoints. And GraphQL, on the other end, is reusing microservices. So I think in this case, with GraphQL, microservices and micro frontends should be totally split, because micro frontends, front-end components, are not talking directly to microservices. GraphQL is actually playing a role of a proxy between them, and it changes the API. So in that sense, again, I don't like to say that there is a best approach. There are various approaches, and that depends to the project. If you are using GraphQL, I think so you are somewhere near mobile development, I don't mean that you are there, but somewhere near. And if you are there and talk about micro frontends, I think so that you are using some web frameworks, also maybe a hybrid setup. So frontends are separate, microservices are separate, and there is GraphQL in between. So that's how I see I'm not sure that I have answered the question. I understand it, but at least just to clarify how I think about it, maybe some things in what I said was helpful.
Yeah, I'm sure definitely it was helpful for our attendees, for everyone. It was really interesting to speaking, but interesting actually to listening to your answers. Really, even for me, when I'm not into microservices, really. Okay, I think we actually have time for let's say this will be our last question. So, what things should we keep in mind when we design microservices for an application? So, let this be like an answer, a tips for our attendees.
That's an interesting one. Juan, do you want to start?
Yeah, sure. I think that one of the, for example, in a scenario that I have worked with several microservices, one of the things is that I care about is the authentication and some sort of a centralized layer that all microservices can connect to. Assuming that's the idea, right? That all microservices will work for the same system application. So some way of centralizing the authentication is something that I will consider. As I mentioned before, also the documentation, but from the technical point of view, like for example, a Swagger documentation for the microservice is something needed. I really like to take that into consideration. And the third one is, how are you planning to deploy all of the services? The continuous integration and continuous delivery needs to be really important and set up from the start. I really like to work on all of the infrastructure underlying the services earlier on during a development process, because it will help to find out build issues after a little sprints that have come through, and not at the very end that okay, let's start deploying this thing and it crashes everything. So those are like the three things that I can think of right now.
I agree with this, and I would like to add to this list also the bounded contexts. Split your services to domains at design stage, and communication. How will you communicate services in one single context, and how will you organize communication between services that are in different contexts? And if there is an eventual, or if there is an event bus or something like that, and hopefully between contexts there will be an event bus, think about transactional models. How will you maintain the consistency of the data overall the system?
Okay, thank you so much. I think this was our last question for today. So thank you so much for spending your time with us. Thank you for your contribution to this event. It was a pleasure having you with us. So I hope to see you soon on our next events. So it's
Thank
time
you.
to say goodbye.
Thank you.
Yes.
It was a pleasure.
Goodbye, Juan. Bye, Orkhan.
Bye.
Okay, so we are really grateful to our previous speakers and ready for our next. Now we will have a quick break, so you will have time just to, I don't know, make a cup of tea or coffee, whatever you like. And time flies, and my shift is going to end, and my colleague will take my place. So thank you so much for being such an amazing audience, and we'll see you soon.
Hey everyone, welcome back to Gecko Software Architecture Summit. I'm really happy to see you here at our second day at this career track where we discuss different things, approaches to architecture and software, to different technologies, different ways of cost-effective configurations and infrastructure on cloud-based, or the patterns that we could use in testing or programming. Different approaches, different meanings, quite a lot of interesting questions. Before announcing our next speaker, I would like to remind you that we give away tickets for questions. This is how it works. So take a chance to win a ticket. You write your questions to our speakers in the comments on YouTube or in the Pine tool. Use the question for ticket hashtag. And at the end of the summit, we'll randomly choose 5 lucky winners to provide with a ticket. Be active and let the luck be on your side. Now, let's announce the speaker. So the topic is about event-driven architecture on AWS. A developer from France, software craftsman, agile and DevOps coach, a cloud architect. Jerome is overall a builder and passionate about doing things well. Clean code and well architecture are key drivers in his day-to-day job at AWS to help his customers. Jerome van der Linden is a solutions architect from Amazon, from France. So now we are starting the pre-recorded video. Stick with us just for a moment and we'll be there. Here we go. 3, 2, 1.
Hi everyone, and thanks for watching this session. I'm very happy to participate to this summit today, and I'm gonna speak about message-driven architecture, and especially on AWS. So first, 2 words on me. My name is Jerome van der Linden. I'm a solution architect at AWS since a bit more than 2 years now, helping my customer to their journey to the cloud, and focusing in modern application, DevOps, serverless, things like that. I have 3 kids, which is my second job actually, and I love skiing with them. If any question, you can reach out to me on Twitter with the nickname Jerome PDL. So looking at the agenda, we're gonna introduce this session with 2 parts. So presenting the drawbacks of monoliths and microservices and why we want to do message-driven architecture. Then we'll see how to do this on AWS, leveraging AWS services, and which one to choose according to your need. And we'll wrap up at the end of this session. Okay, let's start with monoliths. So first, I'd like to say that monolith can be the right solution in many cases, actually. If you do it well, it can be a really good solution. But it's been few years now that we hear that monoliths are bad, monoliths are evil, that you need to build microservices. I tend to disagree with that, and I encourage you to read this post from Martin Fowler, the Monolith First. There are many advantages actually to build monoliths. It's quite simple to develop. It's quite simple to refactor, as everything is in the same place, in the same repo. Everything is shared with the team. It's quite easy to do some integration test, black box test, as you don't have multiple blocks to deploy to test. And yes, speaking about deployment, it's really more easy generally since you have only one package. And also it's easier to monitor because you only have one application to monitor. So yes, I would say you can definitely do good monoliths. And yes, read this post from Martin Fowler is very good. But sometimes, if you don't do them well, monoliths can have some troubles. Very often, what we see is a strong coupling in the code. Everything is depending on everything. Thus, when you want to change something, it has a lot of impacts, and you lose your agility. It becomes harder and harder and longer to add features and to deploy them. So I saw on projects that we could take weeks or months to release new versions. Monoliths are often stateful, which tend to reduce your capacity to scale out also. So we generally have one big database for the monoliths, and it can be also hard to scale out this database. In terms of reliability, generally one failure can bring down the whole system, so that can be a big problem. And yes, introducing new technology can be hard also because it implies a lot of change everywhere in the code. So it can be difficult to build some great monoliths. I'm not saying that all monoliths have this kind of problem, but when they have this kind of problem, we tend to say, okay, go to microservices and use some microservices. With microservices, there are a few arguments to help with the problem we met with monolith. So the first one will be to reduce the coupling. So each microservice is responsible of his domain. You should have less coupling in the code, as there are less code actually, and each one is responsible of its domain. Each one should have its own database, dedicated database, so you should not have coupling with the database. Then when you want to change something, there are obviously smaller impacts because you are focused on this microservice. You can deploy each microservice independently from the others, so giving you more agility and more velocity, the ability to deploy more often. And each service can scale independently. You don't need a big machine or several big machines. You can leverage VM, virtual machines, or containers to do the job. In terms of reliability, you can also expect some improvement, as you won't break the whole system if one service is down. And I think it's easier also to introduce new technologies. Our units of work are smaller. So I don't know if you agree with that. I'm not completely agree with that, because I would say there is the same problems than monoliths. If you do it well, that's fine. Okay, you will have those benefits, but you can have the same trouble as monoliths. If you don't do them well, you can have also some troubles. And the troubles that we see really often are those ones. Are you sure that you are able to reduce the coupling? Actually, really often what we see is that microservices are calling each other to get some information. So then when you change one service, you may need to change the caller and redeploy both. But maybe this caller has another caller which needs to be changed too. So you can imagine, and you build a distributed monolith, which is even more complicated and more difficult to manage, to deploy than a single monolith. In terms of reliability, same problem. If you don't implement things like circuit breaker, for example, one service failing will cascade to the other, to the caller, and so on. So it's not that magic. Both monoliths and microservices can have problems if you don't do it well. Now, let's make our microservices a bit better. Let's make them reactive. I will explain this reactive term in a few seconds. One reason, the problem of the reason we just mentioned, is the way microservices are communicating with each other. So here we have the order service calling the invoice service. If we have a look at this, it's a synchronous communication between those services. So the front end call the order service call the invoice service. And if everything is fine, then everything is fine, no problem. And the customer is happy. But if for some reason the invoice service is unavailable or through an error or maybe has timeout, then there are a lot of chances that the order service will have problems too. So the customer won't be happy. So what's the problem? The problem is you don't have isolation between services. They are still coupled because one is calling synchronously the other. There are risk of times out and cascading failure, so the system is still not reliable. And what happens if the signature of the invoice service change? You can imagine that you will need to change also the order service in order to change this API call. So they are still dependent. Now let's define a bit the reactive principle. So I don't know if you heard about the reactive manifesto. The reactive manifesto, I put the URL here. You can read it. I will explain it quickly here. So a system needs to be responsive. So it needs to respond consistently and in a timely manner. So it's a mix of usability and user experience. It's really important for the customer, for the users. And in order to be responsive, you have to be resilient. So the system must be responsive even if failure occurs. So if the system is responsive, except when there is a failure, we cannot say it's really responsive. So the system must continue to operate, maybe in a degraded mode or maybe with less features, but it must remain available. The system must also remain responsive despite the load, whether it's scaled down or up. It has to be elastic, not just scalable, because scalable is really generally up. It has to be elastic. And finally, everything is built on this foundation that the system should be message-driven. So not that I'm talking about message, not especially about event. Event are a specific kind of messages. So we saw before that synchronous systems are fragile. Responsive systems, responsive application are asynchronous and non-blocking. So it provides better resiliency because you decouple the services, and it also provides better elasticity. Each part of the system is really independent from the other and can scale independently. And then thus you get better responsiveness. Going back to my sample, what happened with the asynchronous communication is the following. So the front end is calling the order service. The order service will create the order and send a message. Okay, I've created an order, and just acknowledge the command from the front end. The invoice service and potentially other services interested will subscribe to this kind of event, to this kind of message, and do what they have to do with it. So it reduces the coupling between them, and it also reduces the contention in the order service, because the order service doesn't have to wait for a response from the invoice service. So less contention means also a better scalability for your service. And your user is happy. But if something going wrong on the invoice service, your user will not be impacted. The order service will send the message, the order created message. This message will be queued somewhere, and we will be able to reconcile the invoice later when the invoice service will be back. So here, clearly, we isolate our services. So we have less risk of timeout, so it's more responsive. We have less risk of cascading failure, so it's more resilient, and more resiliency means more responsiveness. And if the API of the invoice service change, it should not be a problem, because we just send a message and each service is independent and manage its own signature. You just need to understand the message that the order services send. Okay, now let's see how we can do that on AWS. On AWS, there are several messaging services. I'm going to speak about 3, which are serverless. We could also speak about other services, for example, Kinesis or MSK for managed streaming for Kafka. But I will need more time. Here, I will focus on SQS, SNS, and EventBridge. Let's start with SQS. So SQS is a managed queue service, a serverless managed queue service, fully managed. So you don't have to deploy any infrastructure. It will you will only use the API from AWS. It will ensure to decouple some producer from consumers. So what happens is that you put a message in a queue, just a queue. This queue will decouple your producer from the consumer, and those consumer will pull the data, the messages from the queue. An important thing is that messages are stored for up to 14 days. It means that if there is a trouble in a consumer, for example, if for any reason your backend is not available or throw some errors, the message will still be available in the queue until you repair the problem, you redeploy your backend, and you will be able to replay with this message. So it's really the main feature of the SQS queue, the ability to store the message. Regarding the consumer, as of today, you can have AWS Lambda, you can have some containers, you can have some instances. Actually, you can have any compute system that is able to interact with the SDK. So there are 2 different queues. The standard queue, which is this one, which provides a really important throughput. And to provide this throughput, there is a small, let's say, things to consider is that the fact you will have at least once delivery and a best effort delivery, best effort ordering. So it is possible in the case of really heavy load that messages are not completely ordered or maybe delivered several times, but you will get them at least once. So you will need to handle these messages in your consumer. If you need exactly once delivery and if you need to keep the order, we also have the FIFO queue. So in that case, you will keep the order. So for certain types of application, for transaction, for example, it can be important to keep the order. So you can use FIFO. In that case, you will get less throughput, but you will keep the order. So it depends on what you want to achieve. Another interesting feature is that you can do long polling. So instead of polling the queue every few milliseconds or seconds, you can do some long polling. So you poll the queue for 10 seconds, for example, and you retrieve a batch of messages that you can handle in one time. Another interesting feature is the dead letter queue. So if for any reason the message could not be processed successfully by the consumer at the end of the storage time, so at the end of the 14 days, you are able to put this message in another queue. So dead letter queue is another SQS queue actually. That will enable you to troubleshoot why this message could not be processed correctly. And yes, you can interact with this message to see why there is a problem. So this is for SQS. One common pattern that we see and which leverage this storage from SQS is the storage first pattern. So the interest here is really to increase the resilience of the system. So to explain quickly, we have our front end that calls an API, so with API gateway. The API gateway is able to communicate with many services, actually, not only some compute service, not only Lambda. It's also able to communicate with SQS, for example. So here the idea is really to store the content, the data that the front end sent, store it in a queue, so that if your backend is not available at this time, if your Lambda function here is not able to process this message because there is an exception because you update your code and there is a problem, things like that. If for any reason the compute is not available, your data will be safe in the queue and you will be able to process it later. So this is really the main interest of SQS. Now let's talk about SNS, Simple Notification Service. SNS is a fully managed publish and subscribe messaging service. So it allows publisher to send messages to subscriber. So we have what we call an SNS topic, and we have those subscribers who will subscribe to this topic and will receive the message. So messages will be pushed to our subscribers. So here you can see we have AWS Lambda. We can also have SQS. Recently, we also announced Kinesis Data Firehose a few days ago to provide the ability to perform some analytics on the messages. And SNS is also able to send messages to HTTP endpoint for webhooks, for example, or email, SMS, or push notification. So the idea is really to send messages to multiple targets, multiple subscribers. Just like SQS, you are able to provide the FIFO topic. So it works together with the FIFO SQS queue. So if you need some ordering, you can use this feature. But the main interest of SNS, as I said, is really to fan out, so to spread the message to potentially thousands or millions of subscribers. So that really makes sense if you want to send millions of email or push notifications, things like that. And also if you want to push a message to potentially tens or maybe more backend services. An interesting feature with this fan out is the ability to filter the message. So each time you will subscribe a service to a specific topic, you will be able to specify the kind of message you want to receive. So you are able to define filter policies. And in those filter policies, you will be able to compare strings, numbers, things like that, so that you will receive only the messages that are important to you in your backend. And just like SQS too, we have the dead letter queue. So SNS, the SNS topic is not an event store. So you won't be able, just like SQS, to store the message for days. But SNS will instead retry to deliver the message. So with exponential backoff, for example, it can retry up to 23 days. And then the message is lost unless you configure this dead letter queue. And then, just like SQS, you will be able to handle the messages that could not be processed by your subscribers. So as we saw, SNS can be used to notify multiple subscribers, but cannot store messages. Here, what we do is mixing, integrating SNS and SQS. So it's not one or the other. Here we can use both. And the interest here is that our SNS topic will push the messages to multiple destinations, multiple subscribers. Here we have multiple queues. That permits to, if there is any problem with one of the backend, which one of them is not available, the message will be stored in the queue and we'll be able to process it later. So here we really split the message and store it each time. So we leverage both the capabilities of SNS and SQS. Lastly, I will speak about Event Bridge. So Event Bridge is a fully managed serverless event bus to connect application with events. So on the left, we have some event sources, which are able to send events. So it can be AWS services, as you may know, with CloudWatch event, it was the previous name. You can have receive events when something happens in your AWS account. So for example, if you start an EC2 instance, you will receive an event that the instance was started, or things like that. You can create custom events. So for example, with the order service and the invoice service, you could send an event that the order was created. We also have SaaS events, so we have some integration with SaaS applications that are able to push events to AWS too. On the other side, we have several targets, and we have actually more than 20 targets today, as of today. So it can be Lambda, it can be SNS, SQS, but it can also be more complex things like step function, kinesis, batch, and so on and so forth. This is a major interest of Event Bridge, is the ability to push those messages to multiple targets. And in the middle, we have the event bus. So we have different kind of event bus. The default event bus used by AWS to send the AWS events. Custom event bus, if you need to create your own event bus for your applications. And the SaaS event bus for the SaaS events. Then you will define some rules. So those rules will filter the type of events and will define the target where you want to push the messages. So just like SNS, we push messages to the targets. And this filter will allow you to send different kind of events to different targets. Just like the other ones, if for any reason a target is not available, just like SNS, events are not stored, are not an event store. So there is also a retry policy. You can define the number of retry or the maximum age. But at some point, if you are at this maximum, the message can be put in the deadlock queue. So I really recommend to use this in order to handle the strange messages. Another feature that we announced recently is the event archive. So you can store all the events in this archive. You can also have some rules to store only specific messages. And the interest here is that you are able to see what happened. You are also able to replay those archived messages. So it can be useful, for example, to replay historical events after a bug fix in a target, for example, or to test new features with historical production data. Really useful. It's quite recent. And also a really big feature from Event Bridge is the schema registry. So each event has a specific structure, a specific schema, and this registry is a central location where you store those schemas, and it's really easier and faster for your company to find an event. So for example, if someone is interested in your order created event, he can find it in this registry, see the schema, the structure, and then generate some code binding, for example, to use it directly in your application, in your target. And a common pattern with Event Bridge is obviously the event-driven architecture. Here we call it microservice choreography. So it's really, here you can see different colors. So we have different domains. And in each domains, we have several services, several microservices, and each one is communicating with another one through events. So it's really the event-driven architecture or microservice choreography. So to wrap up, to conclude this session, we can see that there are different services and which each one has some specific features, specific capabilities. And it really depends on what you want to achieve in your application. If you need ordering or not, if you need to store the messages. But we saw also that you are not forced to use one or the other. You can mix them. So you could use SNS plus SQS or EventBridge plus SQS, for example. It really depends on what you want to do. So I laid this table for you. I won't spend a lot of time on it, but you have it here with a slide for later on. And to conclude, I would say that we saw that if we want some responsiveness, we need to use message-driven architecture. So we saw the reactive manifesto, and message-driven architecture really drives this resilience and really drives this elasticity. So to do that, you leverage events, asynchronous event, obviously not synchronous one, to improve the responsiveness and reduce the dependencies between the component. We use event routers, just like SNS and EventBridge, so to abstract and to decouple the producer from the consumer. And we can also leverage event stores, so to buffer messages. If, for example, your backend is not available, the message will be stored for X days, and you will be able to play with them later on. So it's really important to leverage this capability. Obviously, you can also use synchronous communication when that makes sense. But yes, in order to provide better resiliency, better elasticity, and better responsiveness, use the message-driven architecture. Just to conclude, a few resources. So if you need to go further, to dive deep, there are some links here. So it's a few sessions from reInvent 2020. Thank you very much. And as I said in the introduction, if you have any question, please reach out to me on Twitter. I will be happy to answer. Thank you.
Thanks to Jerome for this amazing presentation. It was interesting to hear about these features and different ways that Amazon Cloud is providing. And yeah, we all know that right now, one of the most popular approaches is event-driven architecture, and there's plenty of benefits of it. So now we would like to move to the next section. This is again about events and event-driven architecture, a few common traps and how to avoid them. Our next speaker would be Vlad Khononov. He's a software engineer with over 20 years of industry experience, during which he has worked with companies large and small in roles ranging from like webmaster to chief architect. He is a long-time proponent of domain-driven design and evolutionary architecture, and currently helps companies make sense of their business domains, unplug monoliths, and tackle complex architectural challenges. And yeah, that's right. Different approaches work really well together. The microservices architecture, the domain-driven architecture, and the event-driven are actually working fit very well together. Let's give a moment, and just in a minute, we're gonna enable Vladik Khononov, the cloud architect, senior cloud architect from DoiT International from Israel.
Hey, thank you so much for the introduction. You know, the topic I want to discuss with you today is event-driven architecture, and more specifically, this architectural pattern that we usually call an event. And the thing is, events, they're like everywhere nowadays. You know, we have event-driven architecture, we have event sourcing, and of course we have microservices. Many are calling for integrating microservices asynchronously through events as the default integration mechanism. However, this popularity came with a cost. You know, many consider events to be some kind of a secret sauce, as if you can take a monolith, pour some messaging over it, and boom, you've got yourself domain-driven design, microservices, and overall modern software architecture. Of course, that's not true. This pattern is not some kind of magic, but it's just a tool. And as any tool, it can be used to create some great stuff, but it also has a dark side. You're going to pay a hell of a price for misusing or abusing it. And I have experience of doing both. So in the next 40 minutes, I want to share with you some stories about the troubles I got myself into by misusing or abusing messaging. I will tell you how we got out of those troubles, and most importantly, I'm going to share what I had learned the hard way from that experience. Now, these stories are going to be based on my experience at a company called Internovus. The peculiar thing about Internovus is that this company doesn't exist anymore, which means I can say whatever I want. Now, before we get into those horror stories, I want to start with some basics. Let's make sure that we are on the same page about what is software architecture, what are the goals of software architecture, and what exactly are those events that we are talking about in the context of event-driven architecture. The war stories that I'm going to show later are going to be based heavily on this theoretical part. So, what is software architecture? So when pondering this question, usually this quote comes to mind. Architecture is about the important stuff, whatever that is. Now, I doubt someone would argue that software architecture is not important, right? Robust software architecture is crucial for the success not only of the system itself, but in many cases of the whole organization that the system is supposed to serve. For example, at my previous workplace, at that company, Internovus, when we just started, we had to make many architectural decisions. For example, whether we should use self-managed servers or should we go to the cloud. And 8 or 9 years ago, that decision wasn't easy, It wasn't a no-brainer like it is today. Also, we had to decide which databases to choose, languages, frameworks, etc., etc. And of course, we had to align the system's architecture with its business domain, which was quite puzzling for us back then. And all these decisions were hard and risky. A correct one would move the business forward, while a wrong decision could make the system way harder to implement and to maintain, both in the short and the long terms. So architectural decisions are not only important, but they're also hard and complex. Therefore, in my opinion, the goal of architecture is to manage the complexity of a system. And usually we manage this complexity in software systems by decomposing systems into sets of interconnected components, modules. These modules can appear at different levels. They can be methods, classes, namespaces, services, and even whole systems. But at whatever level they are, the underlying idea is the same: Proper modules make it easier to reason about the system as a whole and about each of its components individually. On the architectural level, modularity reduces risk of the design decisions that we are making. It limits the scope of each decision to the scope of its module. For example, let's say you have a component which uses a relational database. Now, for some reason, you decide to migrate the component from a relational database to a different one, say document store. Well, the change in the implementation is going to affect only the component itself and not the rest of the system. Another way to put it is modularity allows us to divide the complexity of a system into two types. The first one is local complexity, a complexity of a specific component. And the easiest way both to demonstrate local complexity and to evaluate it is to ask how hard or how easy would it be for a junior team member to understand what a module of a system is in charge of. For example, in our system, we had a commissions module. All of its public API methods were a coherent set of actions related to calculation of sales agents' commissions. On the other hand, we had a large module that was in charge of managing advertising campaigns, creative materials, billing, and even contracts with third-party companies. Well, it would definitely take a while for someone to comprehend what that second module was doing and how it was implemented. So the second component clearly has a higher local complexity than the first one. The second type of systems complexity is called global complexity. And this one is defined by the level of interconnectedness between the system's components. With low interconnectedness, it is easier to understand what role each component plays in the system. And it's also easier to evolve components, since modification of one module will have lower impact on the rest of the system. Now, on this slide, you can see an example of a system with a relatively low global complexity. There aren't many connections between its modules. And when I say that this one has relatively low global complexity, I mean relatively to this system. Here we have the same number of components, but many more connections and interactions between them. So this one is relatively more complex than this one, the previous system. Here again, the components are much more coupled to each other, and the system overall is much more interconnected. So proper components boundaries reduce complexity of the system and make it more adaptable to future requirements and changes. And that makes the process of defining boundaries a key architectural decision. So if we go back to the question of what is software architecture, in my opinion, Ruth Malan gave a crystal clear answer. She said that system design is inherently about boundaries. What's in, what's out, what spans, and what moves between. It reshapes what is outside just as it shapes what is inside. System design is about drawing boundaries between components. And speaking of what moves between those boundaries, let's talk about the pattern we often use for decoupling components of a system: events. And the idea behind this pattern is fairly simple. An event is a message which is used as a contract for integrating systems. Usually that's what a typical event looks like. It has some metadata and the payload which carries the message itself. Now, according to the contents of that payload, we can categorize events into three types. And I took these definitions from Martin Fowler's article, What Do You Mean by Event-Driven? So the first one is what he calls event notification. Such event is used to notify that something important has happened, and it contains minimal information on the nature of that change. If a subscriber needs more data, it can explicitly query the source system for further information. In some sense, event notification is like a pager. On pager, you would get a message that, hey, some stuff is going on, but if you want to know more details, you have to call that number. That's the idea of event notification. The next type is what Martin Fowler calls event carried state transfer. And here the source system uses events to notify its subscribers about changes in the system's internal state, its data. It can come in two forms, either as a complete snapshot of the modified entity, or the message can specify only the fields that were actually changed. For example, let's say we have this lead entity and it has, let's say, 100 different fields, and if only one of them was modified, well, it may make some sense, to optimize the integrations and only communicates the fields which were actually changed. Anyway, whether we are using this type of events to carry the whole snapshot of an entity or just the changes themselves, all data published by such events is sufficient for the subscribers to hold a local cache and to work with it. They don't have to query the publisher for any additional details, as in the case of event notification. And the final type is the events used in domain-driven design or for event sourcing. Usually we call them domain events. Such events are somewhere between the previous two types. As notification events, they notify that something important has happened in the source system or a service. But they also carry enough information to describe what has actually happened. This data, however, should be modeled as close as possible to the business domain and not some particular state representation, as in the case of events for carrying changes in state. As Marion Duncan Jones says here, domain events should be stateless as regards the entity to which event occurred. In other words, money deposited event holds no data on the account balance. Account balance is the state of the account. On the other hand, money deposited is an event. It described what has happened in the system. So these are the three types of events. Notification event only signals that something has happened. Event carried state transfer is basically a data replication mechanism through events. And finally, domain events are somewhere in between. Now, to demonstrate the differences between the three types, I want to go through this example. Now, this example comes from my friend Ora Egozi, and I think this one captures pretty well the differences between the three types. So let's say we have marriage, and a notification event would be, hey, we have a marriage event, but has no information about who married whom. The event carried state transfer, on the other hand, it would say that, hey, we have personal details changed. We have a new last name for a person. However, we don't know why that last name was changed. We don't know whether it came as a result of a marriage or divorce. Domain event, on the other hand, is modeled as close as possible to the business domain. So here we would have an event saying, hey, that person got married, that's the partner ID, and we have a field specifying whether the person assumed the last name of their partner, true or false. Now, it's crucial to choose the correct type of an event for a specific task. Otherwise, instead of a modern architecture, you will end up with accidental complexity and even the dreaded distributed monolith. To demonstrate it, I want to share some war and horror stories from my experience at the company called Internovus. So, a few words about that company. Our goal was to allow companies that are producing products or services to outsource all their marketing related chores. We would create creative materials, publish and optimize advertising campaigns, collect leads, and finally our own sales agents would make the phone calls and sell the products. So that was pretty complex and wide business domain. And as it usually happens, initially we try to implement this whole system as one huge monolith. Complexity wise, the system had very low global complexity. Hey, we had only one component. But this component's local complexity was huge. Everything was implemented in it. Unsurprisingly, after some time, this design started breaking under its own weight. It became slow, hard to test, and overall unpredictable. So we decided to break this monolith into two subsystems, marketing and CRM. That's what it looked like. Marketing system was in charge of collecting and publishing marketing events. For example, impressions, clicks, submitted leads, etc. And it was kind of stupid, It didn't really do anything with those events apart from publishing them to the subscribers. Those subscribers, on the other hand, they were free to do whatever they want with these events. However, as time passed, we noticed that despite that flexibility, all those subscribers were doing exactly the same thing. They were transforming those marketing events into exactly the same state representation. Now, it's important to point out that this wasn't a mere projection that just transformed the incoming data. No, instead it calculated different business metrics for each event. For example, is this event coming from a new lead or is this an existing customer? If that's an existing customer, how many products did they purchase already, etc., etc. There were many such calculations, and not only that some were really complex, but they also had to change frequently. And when this logic had to change, it had to change simultaneously across all of those subscribers. And of course, it introduced a very strong coupling between all those components. Also, we were quickly hit in the face by unreliability of the network on the left side here. We naively assume that these events they are going to be delivered in the same order as they were published, and they are going to be delivered exactly once, as if this whole system acted as one big logical transaction. Of course, that wasn't always the case. And the moment things didn't go as planned, the same events produced different results for different subscribers. To fix this, we had to employ some infrastructural black magic, which entangled those components even more. Bottom line, we had high local complexity of the components and the global complexity of the whole system skyrocketed. Now we solved this by refactoring the marketing system into an event source system. And that event source system would encapsulate all of that complex and volatile business logic. So instead of publishing mere notification events here, it emitted more elaborate domain events that described what exactly happened in the business domain. And this refactoring lowered both the global complexity of the whole system and the local complexity of its components, because now we were making all those decisions in one place instead of duplicating them in BI and CRM. And speaking of this CRM system, originally we implemented it in a traditional way. It stored the data in a relational database. However, after some time, we understood that this implementation had been limiting us in multiple ways. First, it didn't scale. Second, the relational model limited the insights we were able to get from that data. Some stakeholders from the business needed a more flexible ways of looking at it. Therefore, we refactored that CRM system into an event sourcing and CQRS-based implementation. Our initial CQRS implementation was pretty much by the book. The client would submit a command, its execution would result in new domain events appended to the event store and projected into view models. Finally, the command's results were communicated from the read model back to the user. Those were the so-called one-way commands. But the thing is, there are no commands here. Those are just events masquerading as commands. A system should be able to refuse execution of a command. And of course, it has to communicate back to the user the reason why it was refused. Was there a technical issue or the command is invalid? And if it is invalid, why? How the user can fix it. So in this case, the system's user experience was terrible because of this long feedback loop. To fix this, we refactored the commands to be executed synchronously, and the execution result was delivered immediately to the user. And this change dramatically improved the user experience. The users were getting the results of their actions immediately. Moreover, in some cases, instead of waiting for the changes to propagate across all projections, we just return the updated data as part of common execution result as well. The only limitation was that this updated data can only come from a strongly consistent data store, the event store in this case. And again, that gave us a much better user experience. The users were getting the results of their actions immediately. They didn't have to wait for the projections to reflect the results of their actions. Now, let's talk more in depth about those projections. So, the CRM system published those domain events as its public API, and it expected other systems to leverage that freedom of generating their own projections. At the beginning, it looked awesome, especially when we compared this implementation to our initial relational database-based design. However, after the honeymoon period was over, we realized that, again, 90% of those subscribers were projecting exactly the same model. Again, as in the case of marketing system, this introduced logical coupling. The logic that projected events into workable state was duplicated in all those subscribing components. Not only was it duplicated, but because it held the knowledge of how each domain event affects the state, it was tightly coupled to the CRM's implementation details. The CRM system exposed many different types of events, and all those subscribers had to closely follow the changes in the CRM's implementation. And it changed often. And if a new event type was introduced, they had to reflect it as fast as possible. Because if a new event can affect the value of some projected field, ignoring this event would lead to an inconsistent data. So to sum it up, if we were to evaluate this architecture, it almost literally screams at us, high global complexity, please do something about it, right? So to decouple this mess, we encapsulated the projection logic in the CRM system itself. Instead of exposing hundreds of domain events, it published changes to the projected state through event-queried state transfer. Effectively, the CRM's public API compressed its implementation details, those numerous domain events, into a much more restricted set of public events that just described changes in the state of that projected model. Now, it did raise the local complexity of the CRM system, but it wasn't a big deal. This change dramatically reduced the global complexity of the whole system. It did remove all that coupling that we had here before. The next story is about a betrayal. We had this nice microservices-based system, low global complexity and actually low local complexities of the services themselves. And then, because of some new requirements, we had introduced a new microservice. It processed data from all other services and communicated back some of its decisions. So this solution looked nice initially. But what really happened here is that this new service ended up being an architectural Trojan horse. It introduced lots of implementation coupling, and the global complexity of the system went through the roof. And the solution was to use domain-driven design's anti-corruption layer pattern to separate the integration complexity from the business complexity of the new service. So what this anti-corruption layer did is it captured data from all other services and communicated it in a different model, which was more convenient for these new microservices needs. So this one, the new microservice, would end up implementing just the business logic. But the integration complexity between the service and the rest of the system was encapsulated in this anti-corruption layer. So this anti-corruption layer's local complexity was really low, and all it had to do is to aggregate data and transform it into a different model. The more complex service ended up encapsulating the complexity of the business domain, but it wasn't coupled so much to the rest of the system anymore. So its implementation had to change frequently, but now it had much lower impact on the rest of the system. In other words, by introducing this translation layer here, we reduced the local complexity of this component, and we also reduced the global complexity of that whole system. The story of the next system started pretty similarly to the previous one. Actually, it was our first stab at implementing a microservices-based system. So our approach was simple. We heard this term, microservice, and microservice has that micro part, so it probably means that the smaller the service is, the better the design is going to be. So that's how we design those services, striving for as small code bases as possible. And of course, we integrated those services asynchronously, mainly through publishing and subscribing to domain events. Now, initially, this design did produce low global complexity of the system and low local complexity of the components. However, over time, these services became more and more chatty. More and more connections between the services started adding up, until at some point, almost all of them needed data from all other services to implement their business responsibility. So to provide the required data, we tried putting more of that magic sauce adding more and more events. But as you can see here, the result was that the global complexity of that whole system just skyrocketed. And we ended up with the dreaded distributed monolith. The abuse of the events here was just a symptom of the real problem, invalid decomposition of the system into modules. The solution, of course, was to merge those services in such a way that would lower the global complexity of the system, in a way that would allow us to implement those components with much less interconnections and dependencies between them. And for the last story, I cannot trash talk too much here because I wasn't involved directly in this implementation. So even though I have a lot of things to say here, I'm going to try and consider my words here. About 3 years before the story of Internov was ended, it was merged with another company. And here on this diagram, you can see what I stumbled upon when we did architectural reviews for their systems. So this system would process commands from its users, write changes to a relational database, and then publish some events to a message bus. And the goal of using events here was to build a scalable distributed system. Well, let's see what do we really have here. So first of all, we have transactional coupling between the database and the message bus. Because what will happen if this process will just stop after committing the database transaction, but before publishing the messages to the message bus? Well, the user is going to get an error. Some of the data is going to be written into the relational database, and some of the data is going to be lost because those events are not going to be communicated to their subscribers. The end result is data corruption. Also, for all those subscribers, the order of the events is important, but it's not enforced by the producer. And that's a typical case of temporal coupling. Now, let's see what those subscribers are doing with those events. And the first one is simple. This one just records all the messages in a persistent storage. The second one projects a state representation of that business entity, stores it in an in-memory database, a cache. And the last one forwards the events to BI, but at first enriches those events with the state coming from this service, this cache, the previous subscriber. So effectively, these two subscribers here are temporally coupled to each other. They should be executed in a specific order, or otherwise the analysis model is going to be enriched with an inconsistent state. Of course, such orchestration is not trivial, and in this specific case, it just ended up corrupting the data. The simplest solution to all this mess right here was to implement the outbox pattern. To just leverage the relational database, which was already there, and to expand the original transaction to write the outgoing events into some table, and then have some messaging relay to pick up those events from that table and to asynchronously publish them to a message bus. That eliminated all that transactional coupling that we had there. As for temporal coupling, it was a symptom of bad boundaries. We changed the boundaries of some of these services to reduce the assumptions they're making about the order of execution of these steps. So these were the war stories that I wanted to share. Now let's see what we have learned from this experience. So first, when designing event-driven systems, be pessimistic about everything. Don't naively assume that everything will just work. No, things will fail. And believe me, they are going to fail the most on weekends and national holidays. Trust me on that one. This optimistic consistency I've shown you before is nothing but eventual data corruption. And the term event-driven architecture contains the word driven for a reason. Your whole system depends on the delivery of the events. So make sure that the events are delivered consistently, no matter what. Next, identify private and public events. Some events are implementation details, especially domain events in event source systems. Now, it may be tempting to expose them as your public interface, but on the other hand, you don't want external systems to depend on your implementation details, right? Exposing too many implementation details is a great way to couple your services. So instead, leverage both private and public events. Private events, they can be very detailed domain events, and you can have as many of them as you need. However, when designing your public APIs, your boundaries, compress those private events into a more restricted set of public events. Public events should be modeled with integration needs in mind. They have to be optimized for integration with other components of the system. And the goal you have to keep in mind when designing the public interfaces is reducing the global complexity of the system. Also, we saw that there are 3 different types of events. Use them all. Notification events and event carried state transfer are great for integrating services. And finally, instead of blindly integrating microservices asynchronously through events, evaluate their consistency requirements. You've got 2 services that can settle for eventual consistency. Awesome. Integrate them asynchronously through events. If one of them expects to read the last write of the second one, you have 2 options. First is a simple synchronous call to get the most up-to-date data. If you do need push-based integration, then the source service can raise a notification event and the subscribers will react by getting the more detailed information through a synchronous call. If, on the other hand, both services share a set of methods that assume concurrency control, or in other words, only one of them can be executed at the same time, stop right there. That's transactional coupling. It will be probably much safer to merge these services into a single one. That are the 3 lessons that I have learned from this experience, and it's time to wrap this whole thing up. So, we spoke about software architecture. We said that the goal of software architecture is to manage complexity. We use modularity for dividing complexity of a system into 2 types. Local complexity, complexity of a component, and global complexity, the level of interconnectedness between the system's components. There are 3 types of events. Notification event, which said that, hey, something interesting has happened, but you have to call me explicitly to get more details. We have event carried state transfer for publishing changes in the data, and we have domain events, which notify that something interesting has happened in the business domain. And these 3 lessons summarize experience of what we have learned from those 5 stories of distributed architecture going wrong. Be pessimistic, assume that things will fail, and make sure that your system delivers events no matter what. Use private and public events to limit the public API of your components and evaluate consistency requirements to choose the correct way of integrating your services. And with that, thank you so much for joining me. If I still haven't bored you to death, please give me another chance and follow me on Twitter. Also, few shameless plugs. About a year ago, I wrote a book, What is Domain-Driven Design? It's a guide into this methodology that you can read in an hour or two and get enough knowledge of DDD to start applying it in practice. You can read it on O'Reilly's online learning platform by following this link right here. Also, speaking about Intronovus, I shared our experience of implementing domain-driven design at that company, at Intronovus, in this book, Domain-Driven Design, the First 15 Years. I wrote a chapter for this one, and in that chapter I describe how we implemented domain-driven design from the first day that company was founded, and of course, what mistakes we made and what we have learned from that experience. And with that, thank you again, and let's see if we have any questions.
That was an amazing presentation, Vladik. It will be really interesting to discuss the questions in the Q&A session. Vladik promised to join, and also I saw him communicating in Pine Tool and answering some questions. In general, I really like this presentation because it's kind of bright. It uses we can see really a lot of bottle scars, and that experience that you just have to go through it and learn a lot of lessons. Our next speaker would speak live, continuing the event and actually finishing this session. The topic is delivering from Kafka to WebSockets. So Adam Warski is one of the co-founders of Software Mill, the CTO there, where he codes mainly using Scala and other interesting technologies. Is involved in open source projects such as HTTP, Tapir, Quicklinks, ElasticMQ, and others. He's been a speaker at major conferences such as Java 1, LambdaConf, Devoxx, Scala Days, and so on. Apart from writing closed and open source software in his free time, he also tries to read the internet in various functional programming related subjects. Any ideas or insights usually end up with a blog at softwaremill.com/blog. Ladies and gentlemen, Adam Warski, welcome.
Hello.
How are you doing?
I'm good. How are you?
Very well, thank you. I can hear you just perfectly loud and clear.
That's good. That's the mandatory check.
Perfect. Just please a few words of, like, we can see where you are right now, but can you just share just a few words about how you stepped into these high performance technologies? What drove you to the moment where you are right now?
I've been doing backend programming for most of my professional career. So of course I started, doing web apps, but still on the backend. And this slowly evolved into more complex projects, more complex architectures, and also as the company grew. So our company has 11 years now. So as the company grew, we got more serious clients and more serious projects. So I guess it's kind of natural evolution, I would say, but also interest, of course. These things are very interesting, and handling high traffic, high volume is something you want. These are the problems that you want to have.
So you're like driven by curiosity, right? You always would like to know what's there. What's the next level?
I hope. Yeah, that sounds good. So yeah, let's say so.
Okay, I can see your presentation here. So join the audience. It's prepared already. They're all hungry and starving for this information. So good luck there. I'm adding it now to the screen, and call me if you need anything. Good luck.
Sure. Thank you very much. So hello. Thank you everybody for coming. Good evening, good morning, depending where you are. As introduced, my name is Adam Warski. I come from Warsaw, Poland, and I will be talking about a bit more low-level and more specific architectural problem than before, about the specific problem of delivering messages from a Kafka broker to WebSockets, and then these WebSockets deliver messages to end users. So let's start with a more detailed view of the problem statement. Here on this side, we've got a bunch of users. These are people connecting to web browsers or some other form, but they open a WebSocket connections to our system. So this is the system that we are writing, and these are our end users. So they are opening WebSocket connections, and they are connecting to some edge servers. So these WebSocket nodes, these are edge servers which are exposed on the internet. That's where the end users connect. They open WebSockets, and they expect to receive, well, they are doing something in the system probably, and they expect to receive updates live, in a streaming fashion. So the typical WebSocket usage scenario. So that's the user view, right? And here we've got some microservices, mini services, maybe medium services even. Anyway, what they do is from time to time, they want to send something to the users. So the assumption here is that we want to decouple these microservices from the WebSocket nodes, so that they don't have to communicate directly. They can work asynchronously, and they can be scaled independently, and so on. These microservices, when they want to send a WebSocket message, they will write it to a Kafka topic. So Kafka is a message broker, a streaming data platform. Here we are assuming that our usage of Kafka is kind of a given in our architecture. That's the assumption that we actually want to and have to use this kind of message broker. Maybe it's because we already have a Kafka instance. Maybe we have evaluated various data streaming solutions, and we've come up with the corollary that's actually the best one out there. So we are using Kafka. And so when these services publish messages to the Kafka topic, then these messages have to somehow get transported to the WebSocket nodes, and then these WebSocket nodes distribute these messages to our users. So of course, Kafka it can be deployed in a clustered way. So Kafka takes care of data replication, of fault tolerance. So we are assuming that our Kafka installation is already clustered, replicated, and so on. So we are safe here. And the question, of course, is what about these WebSocket nodes? So we probably have some, non-functional requirements that these WebSocket nodes, they also have to be fault tolerant. So if one dies, another one takes over. They have to scale. So as the number of users increases, maybe we'll have to start multiple WebSocket nodes, right? A WebSocket node can handle maybe 10,000, maybe 50,000 users concurrently, but above that, we probably need 2 of these edge servers or maybe more. So the question is, how do we scale this component? So once we introduce 2 WebSocket nodes, it's not so obvious how to transport these messages that are in the Kafka topic to our WebSocket nodes. So that's the architectural problem that we will try to solve, how to design this connection between these 2 components. And there will be one important design detail of Kafka that we will take into account. So here we have a Kafka topic, but if we zoom into a Kafka topic, you will see that it's actually each topic consists of a number of partitions. Each partition stores a subset of the data in the topic. So when a message is written, it will be written to one of these partitions. Each partition is independently replicated. So if typically, you will have 3 copies or so of each partition across the Kafka cluster. And partitions is also the way Kafka scales. So if you want to put more data onto Kafka, you probably want to create more partitions. However, repartitioning is a hard thing in Kafka, so you typically create, topic with some partitions to spare, so like 100 partitions or so, if you want to scale to these data sizes. And so we have to be aware that the data that we write, the messages that we write to our messages topic will be partitioned across multiple partitions. So before we dive into solutions, just a brief background of who I am and why would I be actually a good person to talk about these kind of things. So as I mentioned, I've been doing quite a lot of backend engineering, 14 years. And now I've been mainly using Scala as a programming language, but on the toolkit side, quite a lot of Kafka and quite a lot of projects. Day to day, I'm a coder, software engineer, and CTO at Software Mill. We do custom software, implementing distributed systems, machine learning, blockchain messaging systems. We also do Scala consulting, Kafka, Cassandra. We write quite a lot of technical articles on our blog. So if you're invited, take a look. There's some Kafka material, some Scala material, but also general on many other topics. If you have any questions, take a look at my Twitter. My DMs are open. You can write me an email or something like that. Okay, so let's look at how we can solve our problem. So the first approximation would be that, well, let's say we have two WebSocket nodes. So maybe everybody, so every WebSocket node can read all of the data from all of the partitions, right? So some of the users are connected to this WebSocket node, some of the users are connected to this WebSocket node, and we just read all data, all messages, and we do some filtering. So each WebSocket node filters the data locally to keep only the relevant messages and send them further to the users. And this probably works if you have one or two nodes, but this solution scales very poorly. So if we add a third or a fourth node, we will actually increase the network traffic a lot, right? Each new node that we add will actually read the whole Kafka topic, and this means that the whole content of the Kafka topic will have to be streamed to this new node that appears, right? So this puts considerable load both on Kafka and on our network infrastructure. So this solution probably doesn't scale that well. It's probably fine if you have one or two edge nodes. So there's a limit to how far you can get with this design. Above that, you probably have to look for other solutions. So how can we improve here? Well, you might be tempted to create some kind of an intelligent router. But before we get to the router, let's look a bit into how Kafka partitions data, divides data between these partitions. So when you write a message, to our messages topic, when you write a message to any Kafka topic, well, it will end up on one of these partitions, right? So the partition assignment can be random, it can be based on the hash of the message, but you can also provide a custom partitioning strategy. So, for example, here we can define a strategy where we extract the ID of the client to whom the message is addressed. So we can extract the ID, and we can, basing on the client ID, determine the partition. So that way we get a deterministic assignment between the client ID and the partition on which the message addressed to a particular client ends up. So then we can actually use that information in our router. So this router component will be quite low level, and it will have to take into account a couple things. So before, actually, one more thing about how partitioning works. So when multiple nodes consume the same topic, so here we have two WebSocket nodes, and they jointly consume the messages topic, right? So if their configuration specifies that they are part of the same consumer group, Kafka will actually make sure that each of these consumer nodes has a unique subset of partitions assigned, right? So Kafka will make sure that all partitions are consumed by some consumer in a consumer group, and that there's no overlap. So this WebSocket node will get some partitions assigned, and this WebSocket node will get some other partitions assigned, right? So they have divided the topic, and jointly they consume everything. So so that's how consumer groups work. So this router, well, what can it do? When a new request arrives, it's like a router load balancer component, something like that, quite low in the network stack. When a new connection request arrives from a user, well, the router can actually see what's the user ID that tries to connect, right? Maybe it's a query parameter in the URL, something like that. So the only thing that the router has to do is actually inspect the HTTP header. So yeah, basing on the client ID, the router can then determine where the messages for that particular client are, right? Because it can run the same hashing algorithm as the partitioner. So now that we know on which partition messages for a particular user are, well, we can see on which WebSocket node consumes messages for that partition, right? And then we can direct the user to connect to the appropriate WebSocket node. Well, this seems to, well, it's a bit complicated, right? The router has to be quite intelligent. It has to tap into the cluster state, how Kafka maps the partitions into WebSocket nodes. So it's definitely not trivial, but it's feasible. But there's one big disadvantage. What happens if we add a new WebSocket node? Well, if we add a new WebSocket node, here the partition assignment will change, right? The new, let's say the third one is the new one. The new WebSocket node will take over some of these partitions as Kafka tries to balance and spread the partition assignment more or less evenly if possible. So this WebSocket node will take over some of these clients that had been previously serviced by other nodes. So this WebSocket node will now serve a whole class of users, well, all users to whom messages are on that partition, right? So now this WebSocket node would have to take over the connections, right? It would have to migrate the connections from the other nodes to this new one, and this isn't really possible, right? The only way to do it is to break these connections and hope the clients will actually re-establish them. So that's not the best user experience that we might provide. So maybe we can do something better. So that's where we can introduce an intermediate component, which would mediate between Kafka and our WebSocket nodes. And this component, the task of this component is to redistribute messages. So here the messages, for the clients, they are more or less, you can assume, in a random order. So we need to segregate them so that they end up on the appropriate WebSocket nodes, right? So we can call it the redistributor component. And there's, of course, we assume that there's a couple of instances of these redistributors for fault tolerance and for scaling maybe as well. And there's two things that we have to consider how to implement. So these redistributors, they have to know which clients are on which WebSocket nodes, right? Because they need to make a decision where to send the message that they are looking at right now. So they need to have the information about the client assignment, on which edge nodes are the clients. So we need this back channel, this dotted line here. So the WebSocket nodes have to somehow transport the information about the client assignment back to the redistributor. So that's one thing to consider. The second thing to consider is how the redistributor pushes messages to the WebSocket nodes themselves. Okay, so let's first look at the back channel. The first approximation here, well, the first possibility here would be to use Kafka to implement the back channel itself. So we already have Kafka in our system, in our cluster, right? We have it set up, we have it clustered, and so on. So if we can reuse it instead of introducing some other form of storage, well, maybe that will actually, simplify and make our operations cheaper. So let's see how we can implement this with Kafka. So we would create a separate topic in Kafka, let's say a client events topic. And every time a client connects to to a WebSocket. So a client comes in here, connects to the WebSocket node. So each time this happens, the WebSocket node writes an event to Kafka that a client has connected to that particular node. Now, each redistributor would have to read that whole topic. So they would have to stream all data coming into this event, these user events topic. And they will have to build an in-memory view of which client is connected to which WebSocket node. So there's a couple of details that we have to discuss. So actually, the first thing is, what about disconnects, right? When can we remove a client from our in-memory view over here? And there's really no good way to do it, right? We can't really rely on the fact that clients will disconnect nicely, because they won't. They will just break connections, or connections will break for other reasons, or whole WebSocket nodes will just disappear. So we can't rely on any disconnect events. So that's why we would probably want to introduce some kind of a heartbeat mechanism. So instead of writing an event only when the connection is initially set up, we probably want to write an event maybe every minute or maybe every 2 minutes. So these WebSocket nodes would write for every client that's connected to them an event that this client is connected to this WebSocket node every minute, right? We can then have so this also naturally defines the retention policy for this topic. So any data older than, let's say, 5 minutes can be safely removed from this topic, right? So that we don't keep a lot of data. The topic would actually be quite small. And it also, over here in our materialized in-memory view, we would actually, we can actually have some timers which expire all state values from our cached in the memory view. So what we described here is in fact something that's quite well known in the Kafka world. So if you look up on blogs on Confluence website about implementing or viewing a database as a log of messages and viewing Kafka as an alternative view of a database, that's exactly this idea implemented in a specific case, right? A database can be viewed as a log of changes that happen, and then we can materialize this, collapse it into an in-memory view. So that's very similar to how event sourcing works as well. So one disadvantage here is that the redistributor would actually have on startup to stream to read the whole content of this topic, well, the last 5 minutes, let's say, or so, as we said, because we delete all the data. So this redistributor would have to read this whole topic, and maybe this could slow startup a bit. Another question is, well, we didn't want to read to create a design where every WebSocket nodes reads everything from our messages topic. So why would redistributors reading everything from the events topic be a good solution now, right? And that's a good question. And the crucial thing here is that we wouldn't have that many events. Well, we still maybe have tens of thousands of users, but still, 10,000 events every minute isn't that much, really, right? That's probably still much less than the number of messages that we are trying to push to our clients. So this topic wouldn't really be big, and materializing the topic in the redistributors probably wouldn't be that big of a problem. It's still the size would still be significantly smaller than the messages topic. So that's one possible solution. Another is to use some form of caching caching subsystem. So we can use memcached, we can use Redis or something like that. So again, here, this part where the WebSocket nodes report on client state is more or less the same. So we still need to use the hard bidding mechanism when the clients are still connected, and we can use like TTL values in Redis so that they get expired if the clients disappear. The main difference is over here, how the redistributors use that data. Well, the redistributors would have to query our Redis cache when they want to forward a message to a WebSocket node. Well, they have to know to which one, right? So they would have to query the Redis cache where is the client located. So the main difference is this arrow, right? The direction of the arrow is reversed comparing to our previous solution. And well, the disadvantage here is that we can end up with a lot of queries to our Redis cache. And so this can be quite a bottleneck. The solution here might be to introduce a second level cache in the redistributor. So we might want to, if we read a value and get back the response, we can actually probably cache it locally for some time, and this way reduce the number of queries that are needed. And this also increases the operational complexity as we have to deploy a Redis cluster, which we didn't have to do before. Okay, so now let's look at some failure scenarios. So what happens when things go bad, right? Well, if there's many components that can fail here, the first one is a Kafka node can fail. So if a Kafka node fails, we are assuming that actually Kafka takes care of it, right? We have assumed that we have a Kafka cluster which is replicated and so on. So we are not worried about this. We are hoping, and well, we can be quite sure that the Kafka clustering will work properly. If a WebSocket node dies, well, nothing really much happens, right? All the client connections, of course, are broken, and the client probably will reconnect to other nodes, but there's nothing that we have to take care of here, really. We have used the hard beating mechanism, so all of the entries in our cache will actually expire properly. And now what happens if a redistributor dies? Well, that's the most complex scenario, right? When a redistributor dies, Kafka will actually notice it, and each redistributor, as I said, all of these redistributors, they would form a single consumer group, so they would jointly consume all of these partitions from the topic, right? But each redistributor would have a unique set of partitions assigned. So Kafka would notice that one of the consumers is gone, and it would trigger a rebalancing of partition assignment. So these partitions would get assigned to some other redistributor, right? So now the question is, from which point in these partitions do we start reading data? So the way Kafka has a checkpointing mechanism, so that we can say which messages have been processed and which have not. However, we don't have checkpoints, so we cannot acknowledge individual messages. We can only acknowledge all messages up to a given offset. And the way it's typically implemented is that we read some data from Kafka, we process it, and the background process asynchronously writes these offsets from time to time, saying that I have processed all messages up to a given point, right? So there is a possibility that this redistributor would actually reprocess some messages that have already been forwarded, and that way we can have some messages that will be sent twice. In other words, we have implemented at least once delivery. We could also get at most once delivery. What we can't do is we can't have exactly once delivery. That's almost impossible in any kind of distributed system. So how can we, now let's look how can we implement forwarding of messages. So again, we can use Kafka here. So we can have a dedicated topic where we keep the segregated messages. How would that topic work? Well, in that topic, each partition would actually be assigned to a unique WebSocket node. So we would have to write a custom partition assignment algorithm. We wouldn't use the one that's used here based on consumer groups, and we wouldn't delegate the task to Kafka to balance that all of the partitions are consumed by some consumer and so on. But we would use we could use a custom partition assignment algorithm which assigns when a new WebSocket node arrives. This WebSocket node will have to pick some partition from these segregated messages topic, and consume data from that partition, right? And then let the redistributor know which partition is it consuming. So this the redistributor would still have to leverage the knowledge of which client is connected to which node, plus the knowledge of which WebSocket node consumes which segregated messages topic, and having that knowledge, it would simply copy data from the partitions assigned to it to the appropriate topic here. So maybe this can even be implemented using Kafka streams, for example. And this way, we get even more decoupling between the redistributors and the WebSocket nodes. So if, for example, a WebSocket node is slow for some reason, it wouldn't impact in any way the redistributor, because these components are completely separate and they are separated by the Kafka brokers. They communicate asynchronously. So that's one solution. Another one is to implement forwarding using, for example, HTTP. We can simply, well, or some other network connection, of course, not necessarily HTTP. But we can, if we have a redistributor here, we can simply connect it to each WebSocket node and open a network connection and send the messages as they come in. Maybe it's, in some streaming fashion, maybe gRPC, maybe even WebSockets, or some other form. So the downside here is that each redistributor has to open connections to each WebSocket node, right? Because these messages here, they are quite random, so you don't really know to which WebSocket node you will be sending them. And there's a bit of coupling between the redistributors and the WebSocket nodes, which I've mentioned before. But this solution is also much simpler. So summing up, we can look at how is really Kafka limiting our design here, right? So ideally, what we would like to do is we would like to say that on a WebSocket node, we want to subscribe to the substream of messages for some client IDs, right? And this isn't possible directly using Kafka because, well, we can't have a partition per client. You can have maybe 100 partitions in Kafka, or maybe 1,000 partitions, but we can't really have 10K or 100K partitions in Kafka. So that's not how Kafka works. The number of partitions in Kafka is limited, and it's a static setup. So, and because these partitions are limited and they form a static set, that's what really determines our design here, and that's what limits our design. That said, there are good reasons why Kafka does it this way. This is implemented this way because of scalability and because of replication. So if you want to scale the amount of data that you store in a Kafka topic, well, you really need to increase the number of partitions, and these partitions have to be roughly independent. So that's at least one way to implement it. So Kafka has good reasons for defining a limited and a static set of partitions, but this also limits the design and makes us introduce this component which mediates between these two parts. So summing up, we have seen three possible solutions to the problem of how can we connect a Kafka topic to some WebSocket nodes which want to consume messages, right? The first one, the simplest one, is where everybody reads everything, but it scales poorly. We have discussed the intelligent router possibility, but it has some fundamental problems, so that's not really a feasible solution most of the time. And we've seen the redistributor approach, where we introduce an intermediate component. The redistributor has some design details on which we have to decide. So we can either use Kafka to implement the back channel, or we can use an in-memory cache to implement the back channel. As for forwarding the messages to the WebSocket nodes, again, we can use Kafka, or we can simply use HTTP or some other network connection. So a couple of links if you would like to explore more. Of course, the Kafka documentation is a good place to read about Kafka. It's very thorough. We also have an ebook on real-time data pipelines and streaming. If you're interested in other queuing and data streaming systems, we have an article which compares a number of implementations of replicated message queues. Kafka is one of them. So we are looking both at performance, so we are doing some benchmarks, but we're also looking at characteristics. So what are the replication guarantees? What are the functionalities? What are the message processing models, and so on? And as I said, if you'd like to get in touch, you can find me on Twitter. So that's all I had. Thank you very much. I think I'm on time. So I guess we'll jump to questions now. I can't hear you, Charlie. I think I'm muted.
Okay, thank you, Adam. Tell me, please, how did it go? How did you feel about this presenting? I'm not sure. Is it your first online presentation, or you already?
Oh no! I've since last year I've done quite a lot of these. So yeah, I guess I've one of my first ones actually on the online at least segment was another Geekle event. It was a Java event.
Okay,
so
that's
I think
it.
it was in May last year or something like that. So yeah.
All right, give me just a minute, please. I have to announce something, and I'm gonna call you back, both you and Vladik.
Okay,
Here.
sure.
We will be having up to 20 minutes for the Q&A session, which should be pretty much enough, and then we are moving to the next session. All right, just a second. Welcome back, everyone, to the GECL Worldwide Software Architecture Summit. These are 2 days and plenty of conversations about how to build infrastructure, how to architecture them, how to protect the code style and structure, how to build modern approaches and use different technologies. I would like to remind you that there is an upcoming event on React.js. We are announcing the React.js Case Study Festival on March 16-17 this year. Either you're considering React.js as a career move or upgrade of your JavaScript knowledge, or have already started as a front-end developer specializing on React.js, the event will help you to think out of the box and master practices. You'll get 2 days and 14 hours in 2 time zones to learn different battle-proven React.js case studies on top companies as AWS, Facebook, Code Academy, Product Hunt, and the others. So just have time to register during a happy hour to get a ticket for $30. Let me quickly post this message to you so that you can see it here on the board. So 1 hour, keep in mind, just 1 hour, you can purchase, you can register during this happy hour and you will get a ticket for just $30 for the upcoming React event. Follow this URL and you'll be happy. I'm posting it also to the YouTube comments chat. So now let's get back to our speakers and we are starting the Q&A session on eventing. Welcome, Adam and Vladik. Hey, how are you going?
Hey. Hello.
So, Adam, I'm so sorry that because of me you had to speak so fast. I'm so sorry.
Oh no, I had my half an hour, so that's the way I speak all the time. So no worries.
Yeah, we included a buffer in the breaks now, so up to 15 minutes is something that we consume, and this time we are just perfectly in time. So we have up to now 20 minutes, maybe a little bit less, to enable our next speaker. So questions. I can see there is not that much activity on YouTube at this moment. However, I've got a few questions for you in terms of events, because actually like event-driven approach is becoming now very popular. So let's describe a few use cases that you would recommend the most to use event-driven architecture, and then probably at least one case when you will not recommend this approach.
always, of course. No, I'm kidding. I guess I would start with something that's maybe a bit unorthodox, but I've been involved in various ways of auditing data, so capturing changes for quite some long time. So, like long time ago, I wrote some Java library for auditing, which took the approach that it audited data after changes. So every time you made a change to a table, it also captured the old version and stored the old version on the side. So that's one approach to data auditing, right? The other one is to use events and event sourcing. So once you have the events as the primary source of truth, apart from other benefits that you get, but you also get an audit trail in your application kind of for free, because all of these changes are represented as events in the event stream. So I think that's an underappreciated side of event streaming, and maybe it's not always the primary reason why you would use events and event streaming. But I think it's also an important characteristic that you do get this audit trail, which might be important for many reasons. Maybe because you want to debug something, right? You can see, you can recover the system state at any point in time. Maybe because of security, because you are obliged to actually store the audit trail of what users do in the system and so on. So that's one characteristic which I think is nice.
Makes sense. Thank you. Let's ask Vladik then to describe one or possible or a few contrasts of using event-driven architecture, where maybe there is a case that you would propose instead.
So the question is, where would I would prefer not to use event-driven architecture?
If you can imagine such a case, yes.
Oh yeah, of course, plenty of them.
Go for it.
So first of all, if we're speaking about event-driven architecture, I guess we're implying communication between components of a system. So if you're not that familiar with the business domain of that system, say you're working in a new company that just started, and you're building a software solution, and the business people, they're not sure about the problem they're solving, let alone the solution. So the boundaries there are going to change, at least in the first few versions, like for sure.
Mm-hmm.
So that would be a very dangerous time, to start decomposing your system and doing event-driven architecture, like communicating asynchronously between those components. If we're speaking about events in the boundary of a single service, which means we're going more towards the direction of event sourcing. So in this case, I would continue on the same notion that Adam started. So when you have event sourcing, you have this audit log, like you're getting it for free. You have this flexible model for generating different insights into your data. But what if you don't need it? Like, usually you can decompose your business domain into the important stuff, what makes money for the business, and what supports the business, which is like, you would prefer to buy it instead of building it yourself. So for those supporting subdomains in the language of DDD, I wouldn't go in that direction in implementing event sourcing.
What would you propose there instead in that case?
So if you're speaking about a supporting subdomain, usually these are quite simple. These are some stupid CRUD interfaces, And, if the problem is simple, use a simple solution, like whatever works. Such subdomains, they're not going to change often. So from the maintenance perspective, you can cut some corners, to be honest, but use the time you save on those supporting subdomains and invest in the best solution possible for core business subdomains, like whatever your business is doing to generate revenue.
Okay. Great, thank you. Then my next question would be would go probably this way. So I'm addressing it to Adam, and it's about Kafka. So this track, the career track, is also a good source for people to understand what is the main reason of using this technology. You've been discussing on how to use it, but also there could be like some people would be interested in just they need to understand the reason of learning this technology, and probably what are the benefits of Kafka, like over the other similar services.
Right. Okay. Well, Kafka can do a lot, and it's probably quite often also overused because it's popular. So people sometimes go with the fashion, but generally saying, I guess Kafka can fill in the role, for example, of a message queue, right? Anytime you want to decouple the two components and make sure that they can work independently, not even necessarily at the same point in time, you need some kind of a message queue. So now there's, of course, a large number of message queue systems available, and Kafka probably may not be the best one for your use case, so you have to actually pick it quite carefully. That's also the point of the mkperf article that I've mentioned, where we try to compare various solutions and various systems. So Kafka's strengths are for sure the data safety. So I think it's quite thoroughly tested that it won't actually lose your data if you have it clustered and so on. So that's, I think Kafka gives you quite high guarantees of that. And still it's quite fast given that the data is replicated. So so these are two characteristics which are like advantages of Kafka. On the disadvantages side, it's quite simple in terms of features, so it doesn't offer that much in terms of how you can actually consume messages. What are the patterns to process these messages, right? One thing I mentioned was that, for example, you can't have individual acknowledgement that this message was processed and this other message should be redelivered after some time. So that's not possible with Kafka. You have to build something on top of it to actually get this functionality, and you get it for free with systems like Rabbit, for example. Okay. Yeah. So that's one use case of Kafka. But Kafka, they market their solutions, and that's essentially what Kafka really is, like a message queue, depending how you configure the consumers. So it's being marketed as a data streaming platform, of course, big data and so on. But I think essentially what you will end up is some form of a queue or a topic. So yeah, that's
okay. Great, thank you, Adam. Let's move to the next question. So, where we are still discussing the events and so on, and getting a little bit deeper into the domain-driven architecture. So, you already mentioned that knowing the business domains is actually crucial to build this domain-driven architecture, and it's one of the main reasons of reacting to the events, right? If we don't know what we are listening to or what is the business logic there, we cannot build the events properly. So let's say we have a brand new project and we somehow distributed these domains and everything, and then we have to upgrade to the next version of a complete service, and we realize that in the company since that time business process have been changed. What would you recommend to rework or which approach would you recommend to use in this case? Maybe from the technological point of view, maybe there is some way to quickly migrate from one solution to another one. Vladik, you go first.
Yeah, so Such changes, they're quite common, especially in startup companies, like in the case of Internovus. Like for 8 years, we were in what we call in Israel a startup mode. Now, what we call a startup mode in Israel, in the rest of the world, is called chaos. So things are changing all the time. Business requirements. There is no point in writing them down, because once you finish writing them, they are going to change. So everything changes. So I would say, before getting to the change itself, make sure that you're working in the boundaries that are going to support such evolution. Of course, you cannot predict each change, everything that can change in the future. However, once you find those boundaries, for example, of subdomains, well, it's safe to assume that a change in a subdomain is not going to affect the rest of the system, like other subdomains. So I would say, first of all, proactively make sure that your boundaries are there to protect you, to make sure that you are not going crazy with some tiny services where each change is going to affect, I don't know, dozens of services and a dozen of other services that you didn't even anticipate. Instead, be prepared for changes, keep boundaries wide where possible, decompose them into smaller ones only when you are sure that this thing is not going to change often, or at least you can anticipate, or you already have experience of a change in, so you know what to expect from the business. And if still something happens, something unexpected, like a black swan that suddenly renders your design unreasonable, then you have to, first of all, you have to adopt the design. You cannot delay it, because the longer you delay it, the higher is going to be the payment for the debt. Now,
fair enough.
Huge changes in enterprise systems, like overnight, big rewrites, they never work. Because first of all, your business people, they're not going to say, hey, okay, so until now we were changing everything every minute, but now we will wait a month for you to finish your refactoring. Not going to happen. Also, if you're doing a big rewrite, that's a hell of a risk. Because come on, if the system is complex, there is a high certainty that you're going to break something, even if you have a perfect test coverage. That's going to happen. So because of all these possible issues, I suggest to make big changes gradual. To start by making small changes, to plan ahead, like how you're going to migrate your implementation, your boundaries, and do it gradually. And if possible, have 2 implementations of the system. So for example, if you have so if you have the same public interface, have 2 implementations that are implementing that interface, and start migrating gradually to the new implementation, and reduce risks, because risks are, if something goes wrong, the blame
you have
is
to limit
on,
it to isolate the risk, right? That's true.
If something goes wrong, there is one group of people that are always going to be blamed, software engineers. But when everything works fine, it's the success of the business. So
Fair enough.
Make changes small and gradual and safe.
Very, very, very nice advice. So yeah, just to summarize it, the thing is in building an infrastructure, try to split it in chunks in such a way that it's based on common sense and it is easy to maintain. And it's not too hard to maintain, because if you go too deep into the details, then there's be too big maintenance cost. And it's just gonna take the time that you don't have. Second thing is try to understand the basic business rules instead of following each step in details. Try to use generic rules that even change in the game, you still have the same cost structure. Like for example, if the traffic rules are changing over the time because they're adding some obstacles, or things, the basic things are still the same. The driver is still sitting in the car, and the traffic lights are still red and green. Okay, there is one question that I would probably address to Adam. It's a question from Blaine. Any difference between choreographer and conductor patterns?
I have no idea. That's probably a question to Vladik. I'm not good in patterns. So I'm not even sure what these patterns are. So sorry. I won't help you here.
Okay.
Sorry. Can you please show the question again?
Yeah. Any difference between choreographer and conductor patterns?
They sound similar, like the words. You can probably more or less guess what. Yeah, but yeah, I'm not familiar with the exact meanings.
So
Okay.
The question is about choreography between services, where services are just reacting to events which are emitted by other services against I forgot the word. Conductor was the word that used here.
Yeah,
choreography and conductor.
Yeah, usually orchestration, I think the word which is more popular for this topic. So orchestration is where you have a service which encapsulates that logic of integrating other components. It orchestrates their interactions so that if the interactions are changing, you're implementing a change in that orchestrator, and not you have to track down those dependencies between the services. Which one is better? Neither of them. It all depends. Sorry.
Okay. All right, then let's finish this conversation with the last part from Adam, and in this case, continuing a little bit the communication between different services, and so from Kafka perspective, from Kafka perspective, as I understand, it works really well with high availability services when you just have to enable plenty of similar connections. Is it correct?
Yeah, well, communicating services using Kafka works well when you need asynchronous communication. So you send something and you don't expect a reply, right? And the consumers will somehow react to that. But there are also cases when you do need synchronous communication, and you can design whole systems with synchronous communication, and this might work well. But you simply know if you try to do synchronous communication with Kafka, you will end up with some horrific design. So that's probably not what you want to do. That's simply not the right tool for the job. So yeah, as far as communicating services goes, if you can do it asynchronously, very well. It has a lot of advantages. It decouples the systems. It makes, for example, error propagation well, errors don't propagate from one subsystem to another, right? If one subsystem dies, it will simply stop consuming the messages for some time, and it won't impact how the sending message, how the sending service works, right? So this asynchronous way of communicating has a lot of advantages, but it's also harder, right? It's simpler to just ask somebody synchronously, give me the product, the user, whatever, and then to try to switch your thinking to the asynchronous one. But yeah, if you want to have independent scaling, and if you want really to have, probably, as you said, in high performance and maybe not in high performance, but high throughput systems, that's where you should probably consider this kind of a message broker or streaming.
All right, thank you. That's a good answer. Our time is over now. So I would like to thank you, first of all, for your presentations. I've been there and listening to them. I took some interesting advantages. I wish I had a little bit more time to discuss even more questions with you. And I hope I'm gonna see you on the next presentations. Thank you both. And
thank you so much.
Yeah, have a good evening. Goodbye.
Bye-bye.
Bye-bye.
So we are now on GCL Worldwide Software Architecture Summit. We just closed the events section. And I wanted to remind you that the happy hour that we've been announcing is going over, finishing it. Now, keep in mind that you should use the question for ticket hashtag, and you can ask your questions with that hashtag. Please do that in your question, and we will bring it to the screen and we will ask it on the presentation. And at the end of today's session, I'm gonna open random.org, and 5 lucky winners will get their tickets to our next events. Okay, there is one more important thing in every infrastructure. This is the channels, the communication channels, right? We already discussed the messages, and now we have to discuss the APIs. And everyone knows there is quite a good discussion around what is better, the REST API powered by Swagger, or that's GraphQL. What's the best choice in each specific solution? And we have here Erik Wilde from Switzerland, from Axway company, is an API expert that works in Axway Catalyst team and is focused on API strategies, API programs, and API platforms. Welcome, Erik.
Hey, Charlie.
Hey, how are you? Very well, thank you. It's you can see how exciting is this event going. I'm just sitting literally here in my chair, just speak from time to time, and all the rest of my time I'm getting useful information. What could be better for a geek?
Yeah, no, it's pretty cool. I was just listening in to the previous session, and it's kind of a good segue, right? So it was a lot about asynchronous communications, but on the other hand, if you want to do synchronous communications, how do you do that, right? And that's what I'm going to talk about. Perfect. So tell me just a few words. Why APIs? Why APIs? That's a good question. Well, in the end, it's just, I think it's the new way how, in particular, at an enterprise level, people think about how they basically build up large, complex ecosystems of communicating components, and they want to provide those capabilities in a way that's reusable and it's easily accessible in large organizations. So you often have in large organizations hundreds or even thousands of APIs that you can use for all kinds of capabilities that you have there. And then the question is, what's a good pattern to do this? Can everybody pick their own? Is there the one true thing that everybody has to do? And that's kind of the topic of my presentation.
All right. I'm still curious, why did you choose APIs as your main job? For example, I chose processes and Scrum Mastership as my main career for some reasons. Why did you choose APIs to focus on now?
That is, we should have some beer the next time we can travel. No, it's really interesting. So I spent a lot of time. So I studied computer science. I studied distributed systems and communication protocols. So I always was interested in how do really large scale information systems work. And so it's not so much about like how you build like one component, but like how do you build things basically at web scale. And if you look at that picture, then different patterns emerge, right? It's more like loose coupling. How do you make possible that everybody can make their own thing, but you can still use it in some environments? And I worked on web architecture for a long time, and then I somehow transitioned into how this is getting used in enterprises, and that is what people nowadays call APIs. When I started, it was called protocols. Now it's called APIs. Who cares?
Nice. Thank you so much. Yeah, it would be really great to have a beer and a really nice conversation over those things. Okay, I'm gonna bring now your screen, the screen that you're sharing to this main screen. Okay, get ready. Tell me when you're ready to bring the screen.
Okay. I think you should see my presentation now.
Here we are. Yeah, perfect. The layout is set. You're good to go. And once you need something, just call me.
Okay, thank you very much. So let's get started. So my presentation is called REST versus GraphQL, making the right choice. And to some extent, like all choices in engineering, I could just finish that and say, what's the right choice? You could just say, it depends, and then you could move on. That's not really very satisfying, so I will do a little bit more than that. But I really want to talk about the fact that think about what you're doing, and then you can make the right choice. Don't assume that one is better than the other just by default. Okay, very briefly about myself, and Charlie already asked, like, why are you doing APIs? It's a good question, but I've been in this space for a while. My personal background is in computer communications, and then I transitioned into this kind of more enterprise level architecture issues. I've been working in the API space for a while. I worked at something called API Academy, which was in CA technologies. For the last little over a year, I've been working for Axway, a software company, and we build API products. And my role there is not so much to talk about our products, which of course are great, but more to talk about how do you use APIs in a good way. And the reason for that is really that a lot of organizations nowadays are always looking for ways how they can build better IT, and building better IT in the sense that it is something where they say, we want to build something that we can change more easily. So a typical problem nowadays is that organizations say, we feel like we can't really change things as fast as we want to change them. So how can we do this? And API play an important role in that picture. I used to speak a lot at events, community events. I spoke a lot to organizations, to leadership teams, to transformation teams. All of this, of course, stopped. All the travels at least stopped about a year ago. Nowadays, I have started making more videos. Check out my YouTube channel. I post a lot of API-related videos. So if you're interested in that, please go over there and check it out. Also, by the way, if you're interested in the slides, they're online. You can find me on Twitter. My link is up here. And if you go and visit my Twitter feed, my last feed actually has a link to the slides. The slides are web-based. So if you want to use the slides later on, you can just follow that link, and then you can check all the things out that I've actually linking from the slides. What am I doing? Apart from just talking about APIs, I'm part of a team that's called the Catalysts. We're a small team within Axway. There's 7 of us. And our role is to talk to organizations and to help them to make good choices when it comes to API strategy, API programs, API platforms. And one question that we hear quite a bit is REST or GraphQL, which one should we choose? And that's what I'm going to talk about today. And because REST is a more established pattern, I want to talk a little bit more about GraphQL initially, so that we all are kind of understanding what choice we have in front of us. And then I want to give you 4 factors that you can look at when you want to decide which one am I going to choose for a software component that I'm building. And in order to put things into context, very briefly, an API crash course. So why APIs? And Charlie asked that question already, and it's a good question to ask. It's really something. APIs has become what I call the connective fabric of modern IT. So large-scale systems nowadays are built in a way that organizations are trying to move away from monolithic and tightly coupled architectures to more loosely coupled architectures. And APIs are the fabric that connects those things, right? It's the way how all these different components talk with each other. And there are other patterns as well. And we just heard in the previous presentation about asynchronous communications, but APIs are the general term basically of doing that. And asynchronous communications is one style of how you can do this. And we'll talk about 2 different styles, which are REST and GraphQL. And when you look at where IT is going nowadays, APIs are really becoming extremely important, because more and more in companies, there's this idea of API first, which means that everything that gets developed as a component must have an API, and this becomes the only way how others can interact with this component. If you build things this way, you end up with components that are easily reusable. If you make them discoverable, you end up with those landscapes of APIs that more things can be built on, and that's exactly what organizations today are trying to accomplish, like to build this infrastructure of components that can be used to build new things. Doing microservices is also in that general context. Microservices then are not just building something that has an API, but also building it in a way that it is individually deployable, so that, if, for example, you can deploy it wherever you like, you can scale it independently and all these kind of things. We're not going to talk about microservices, but microservices are just another example of why APIs are so important, because microservices must have an API. Right? They are, by definition, these self-contained components that only interact with other things through their API. So once again, an API becomes really important. And that means that getting APIs right is an important part of the decision that you have to make if, as an organization, you're going in this general direction. So this is the general gist around APIs. Now let's look at what we're talking about today. As an example of microservices, here is one typical example, and one that actually is taken from what we'll talk about in this presentation, which is the Facebook API. So Facebook has an API, which is the Facebook service that is available, and the Facebook applications that you use on your phone or your tablet or in your web browser are talking to this API. And that's a general pattern, right, that you have with many applications today, that they have a front end, and then this front end talks to the back end, and this happens through an API. Now, what Facebook realized was that their API was not really performing as they wanted it to perform, because they had built it in a way that in order, for example, to show your Facebook feed, the API would be used in many different ways, because the app would ask many different questions, like show me the feed, and now give me all the posts in the feed, and now give me all the likes for each of the posts, and now for each of the likes, give me the picture of the person who liked that thing. So it was a lot of back and forth, which made things slow. And then Facebook thought about how can we improve that. And the reason why it was so slow is really that the social graph that Facebook exposes is really, really big. And when you use your Facebook app, right, you get like a tiny part of that graph, but the initial API was designed in a way that in order to get the kind of the graph that you want to get, you have to have a lot of back and forth, right? Because the graph is so big and you only want a small part of it, so you kind of have to find your way around it. And the problem they had was that this communication was not very effective, and also sometimes you were actually getting more information than you needed, because, for example, a mobile phone would get more information than it actually wanted to display, because by definition, you would just get all the data and then the phone would just discard some of the data. There would have been different ways how you can improve that. One would have been to improve the way how the resources work, so that you can, for example, say, give me the feed, but embed all the like information already, right? So you could try to reduce the number of round trips. Another way of how you could do this would be to say, I build specific backends for the different front ends that I have. So I have an API for my mobile phones, I have an API for my tablets, I have an API for my web app. But that also introduces problems in terms of how you can manage those parallel APIs. And the third example would be to say, what I do instead is to say, I want to query into that graph so that each application can specifically say, I want those parts, and then on the server side, this information gets assembled and sent back. So basically a little bit like a database, right? You make a very specific query, and as a response, you get exactly what you query for. And when you look at those possible solutions, right, they are exploring different styles. And once again, if you're interested in what styles are, here's a little video about it. You can check it out. It's on YouTube. And the two styles that we've seen in the discussion we've had so far, right, is on the one hand, the resource style of REST, which is this pattern that Facebook had. And this pattern means that you have a lot of these requests for resources, and in order to get all the information that you want, you need many of those requests. So that was the performance issue that Facebook was experiencing. Then what they did instead was to say, we're going with a query style. And they specifically built their own query language for that. And it's important to understand that the difference between REST and GraphQL is not just a difference in technologies, it's also a difference in API styles, right? It's a different approach of how you design an API. And both on the REST side and on the query side, there are different technologies you could use. So in the end, when you compare REST and GraphQL, you're kind of comparing apples and oranges, because you're comparing kind of a specific technology with kind of a specific technology, but from a different style. But regardless of that, right, it's a discussion that a lot of people have nowadays. So it's interesting to think about what would that decision look like and what kind of factors would go into this decision. What Facebook did as their solution of solving their problem was they created this new language, GraphQL, which initially was just used by Facebook for their apps communicating with their backend. And then by now it has become a thing of its own. It has been handed over to the Linux Foundation. It now has its own open source place where you can go. There's a whole foundation that has been built up around it. So it has become sort of an industry standard that now exists and that a lot of people find interesting and are considering using. And what it does is really, it mostly just exposes the ability to query into a graph, which is why it's called GraphQL. It's a very, very simple example you can see here. So on the top, you see the request, which is slightly different. It's not quite JSON, but it looks very much like JSON. And at the bottom, you see the response, which actually is JSON. And what you can see here is you have a query that queries for a certain node that has some sub nodes to it, right? So you can also look at a JSON object like a little graph, right? And what you get as a response is a JSON representation of that graph that has the hero node and the 3 name and height and mass nodes attached to it, right? So that is how GraphQL works in theory. And practice, of course, the graphs very often are much more complex. For example, when you look at the Facebook graph, but that's how the language in itself works. Now, one thing that I think is important to know and to appreciate is the fact that Facebook is using GraphQL for its own applications, talking to the Facebook API, which is an internal way of using this API, right? Only Facebook applications use the Facebook API. Facebook has a public API, but Facebook's public API is not using GraphQL. Confusingly, it's called Graph API, but it's a REST API. And I think it is important and interesting to understand that even Facebook, the company that created GraphQL, only uses GraphQL for its internal APIs, and for its externally facing APIs that partners and the public can use, they use REST. So that's just something for your consideration, right? An interesting data point. Now that we've looked into what REST is and you understand a little bit where it comes from and what it has been designed for, let's briefly look at those things that I was promising I would tell you about how to decide whether you should be using REST or GraphQL, right? So, and the question there sometimes also is it just you making this decision, or is it a large organization where you're working and you are developing one component that is sitting next to 100 or 1,000 other components? And that's already the first good thing to think about, right? So our first thing to look at whether you should choose REST or GraphQL is consider your API landscape. So if you are not just developing a single component that has an API that has no context around it, but if instead you're developing a component, let's say in an organization that has other APIs, look at those APIs and look at how they work. And keep in mind that if you have an organization with 100 APIs, it helps when they all work in a similar way, because then developers working in that organization can consume all the 100 APIs in roughly the same way, right? If they all look and feel different, it's harder to use those next to each other because I need to understand each individual one in a different way, so that becomes tiring and inefficient. So it's a good idea to really think about what does your organization do. More and more organizations are establishing API guidelines where they say, this is how we want APIs to look. In a lot of organizations, you also have those guidelines being formulated in the sense that unless there's a good reason to do it in a different way, please do it that way, right? And I think that already tells you a good story of there is kind of a default choice, and unless you're saying that doesn't work for me at all, it's probably a good idea to go with that default choice. And in most cases, just to tell you how things are nowadays working, right? In most cases, that default choice will be REST in most organizations. And the other thing to keep in mind also is how much are you not just building it now and how much effort is that, but also how much will you have to invest when you change the API? How much effort will that be for you? How much effort will that be for existing consumers? And that's also a very important thing to keep in mind, because depending on how many consumers you have, changes may affect a larger or a smaller set of consumers. And that's also an important thing to keep in mind. Okay, let's move on to our second reason, what you can look at, whether you want to choose REST or GraphQL. If you look at APIs, they are exposing a component so that you can interact with that component. Some components mostly expose data, right? So if, for example, I have a customer service, that customer service may just expose customer data. And in that case, GraphQL is working well because, I can represent any kind of data as a graph and then query into that graph and get back that data. So that's kind of a good fit. But there's also many APIs that are more process-oriented. Let's say a shopping API, right? Where you say, I want to buy this. I want you to deliver it to this address. I want to pay using this payment method. Now I want to confirm this payment. I want to confirm the shipping address and all of these kinds of things. So that's more like a process. It's not so much that you just ask for data. Like you send a message, you get a response. You send a message, you get a response, right? And this is a communication flow. This kind of conversational API typically works better in REST, right? Because it's not just working with a graph. It's really this kind of back and forth of messages that work in that specific sequence. And designing those messages then becomes a good way to design an API for that. So for these kind of scenarios, REST tends to be the better choice. Let's look at the third thing we can look at. Third thing you can look at is also consider who you are designing the API for, right? If you design an API, you should always think about the consumers. What would they like better? And that's a very good question to ask. And depending on whether you work in a bank or you work for a startup, right, you have a very different set of consumers. And that should influence your design choice as well, saying that if everybody else is using REST and my developers really are not that interested in the latest and greatest technology, they just want to use their established tool set and they'll be happy, then maybe I'll go with REST. If you're like an edgy small startup and you want to look cool and use the latest technology, right? Well, by all means, create a GraphQL API and use the latest and greatest technology. Both kind of designs will work, right? It's just a different experience for the developer working with them. And depending on who your consumers are, you want to go maybe one way or the other. And the fourth thing that I want to tell you that is an important exercise, I think, avoid taking shortcuts. What do I mean by this? What I mean by this is really treat designing your API as a proper design exercise, meaning don't be lazy. Don't just say, oh, I have my data in JSON anyway because I have some kind of NoSQL data store and I will just expose that data store through a GraphQL API. That is terrible. And that happens a lot. And it's terrible because it means you expose your implementation to your consumers. That is not what an API should do. An API should hide your implementation and should make it available to consumers. You should think about your API outside in. What do my consumers want? And not so much inside out, like what do I have? I'll just give it to them. So really think about your API as a design exercise, taking into account your consumers, the scenario, what would work for them, what works for my landscape, all these kind of things. Because the API, in the end, is the only thing that consumers will see of your software component. So take your time to design it properly and make sure that you design it in a way that works well for your consumers. That is really an important thing to keep in mind, that just because there's tooling available that allows you to generate a GraphQL API from your JSON-oriented database, that doesn't mean that's a good idea to do it, right? So keep that in mind. And in conclusion, I gave you those 4 points that you can use to decide between REST and GraphQL. Keep in mind that I think the one thing that, of course, is kind of a general statement, right? There is no silver bullet. It wouldn't be an honest answer to say REST is better than GraphQL or the other way around. But I think it is important to make this as a conscious choice and be aware of the fact that once an API is out there and you have consumers, it's hard to take it back. So make that choice as a choice that you know will have consequences. What happens nowadays, and that's just my experience in working in that space, right? And GraphQL is being used, but it's mostly being used for private APIs where consumers and providers are in the same organization, right? Such as for backends for user interfaces, where the user interface and the backend are managed by the same organization. And for the vast majority of APIs for partner and public consumption, those are being developed as REST APIs. And you can say this is just because people are lazy and they don't want to adopt the cool new stuff. Maybe that's it. But this is just where we are right now. At least I think that's an interesting data point as well. And really, first and foremost, when you do design APIs, always keep your consumers in mind. And coming to an end, and because I'm German, I want to end with beer. One way of explaining APIs that I've done is explaining it with beer. So if you think of an API, what is an API? An API is a delivery mechanism, right? So you design a software component, you design the value, and that's the beer. The API is nothing but the delivery mechanism. The API is the bottle. The API is the can. It's the way how you provide access to your product to somebody who wants to consume it. So think about the needs of the consumers and the constraints that you introduce by using a particular delivery mechanism, and then make a choice how you are going to deliver your beer to the consumer. And I think if you go through this as a proper design exercise, thinking about what am I trying to get to consumers, what is the best way for them to consume what I'm trying to deliver to them, then I think you have a very good chance of making a good choice. And with that, I'm done. Once again, if you want to look at my slides, you can find them online. They're here, and right, there's also a link in my Twitter feed. If you want to connect with me, please do so. Here's how you can find me on Twitter, on YouTube, on LinkedIn. I'd love to connect with you. I love hearing what people are doing with APIs. It's my job to to learn about how APIs are being used so that I better understand what's going on and I can better help people who have API questions. So thanks a lot for listening. Thanks for this opportunity to talk about APIs, and I hope you found that useful.
Dankeschön, Erik.
Gern geschehen.
You just demonstrated a perfect German skill of being just in time. Perfect.
Right?
Like
Is that on the spot?
He's just in your blood, yeah. Great. It was really, like, I heard a lot of articles. I've been reading them, and sometimes I ask my developers what's the difference. Nobody explained me in that simple way to understand it, the difference between GraphQL and REST API. So thank you.
Always think about
always think about the need. You are right.
No,
that was the idea. Always think, I'm thinking about the beer all the rest time that I'm not talking. So the beer and the needs. I can see that these 2 days and the entire architectural summit, everyone has talking. First of all, that you cannot build a modern application or service without putting the needs, the custom, actually any needs on top of it.
Yeah.
The question why? I'm happy that
because it's fun.
Because it's fun and because it's fine and it serves for beer. Okay, thank you. I hope we will see you on the Q&A session.
Yeah, I'll be back.
All right. Cool. Then we are moving now to our next section. Before that, I would like to remind you that we are now on a Worldwide Software Architecture Summit, and we are talking about architectural approaches. And you are invited, actually, to ask your questions in the comments. Please put the question for ticket hashtag, and we will bring that question online so that our speakers can answer it. Now we are going to the next speech. This is it is a pre-recorded earlier today a session from Mobeen Ahmed, a software architect from Folio 3 from Pakistan. This is a topic on achieving scalability using .NET Core Web API. Keep in mind, .NET still exists and it's a powerful technology, and the .NET Core Web API really can bring some powerful insights. So Mobeen, I've been working in software industry for the last 15 years. He has experience in working on enterprise level applications in different domains. I've worked mostly on backend application and mostly built on Microsoft technologies. So let's see where we are. Let's bring him online just in a second.
So my name is Mobeen. As I told you, I have around 15 years of experience in software development. I've been working in the industry in different companies, different applications, and basically I have a bachelor's degree and a master's degree in computer science. I'm based in Karachi, Pakistan. And I think it's the first time that on VQ we have a representation from Pakistan. So I'm really happy to represent my country here in this platform. So basically, why I choose this topic. In the last 15 years of my development career, I found scalability as one of the pain points that we have, when we are working in an application. And this is the pain point that's been ignored. And this is a pain point that usually comes up later on. So, like for example, it's a problem that builds and builds and builds, and all of a sudden it pops up, and then the whole thing basically crumbles, and the problems start to come in. So, the theme of theme of this presentation will be basically I'll be talking about why we talk about scalability, we can do with cloud and how it can help in scaling. Some of the questions that as an architect or you as a designer of the application that needs to put forward yourself to, and make sure you have the answers to those. Then we'll talk a little bit about load testing and stress testing. What are these? Why are they needed? What's the importance? Then we'll take an example of an application and how it evolves from a basic application to a large application, and what are the considerations that we need to take when we are moving from a small application to a large application. In the last, if time permits, we'll talk about some of the design failures and how we overcome that. As an experience I want to share with you that how we managed to do that. Okay, perfect. So let's jump into it. Why talk about scalability? So usually my talks are basically interactive, but due to COVID and all that, I have to speak a lot, and the audience has to listen a lot. So basically, why we talk about scalability? It's basically the resources that we have, like everything in the world, these are scarce. So we have limited number of resources, and we need ample amount of complete access or complete usage. So in terms of CPU, if we talk about the softwares, that is almost the same story. So we have limited CPUs, we have limited bandwidth, we have a limited number of memory that we can use, and especially time that we need when we are developing a software. So these basically are the things that are scarce. But with some of you might be thinking that CPU and bandwidth and memory, these are not scarce nowadays. Yes, with the entrance of cloud in the arena, these resources have transformed. So they have transformed from computing scarcity to a computing abundance. But still, one thing that comes in our mind and we should be considerate of, that the abundance of resources doesn't mean that we overuse it or we misuse those resources. So resources are available, but we have to make sure that those resources are being utilized properly and in the best possible way. The cloud has made the resources cheaper, and due to that, we overlook in terms of when we are talking about the resourcing or the resources. But the problem is that does having more resources and having cheap resources solve the problem of scalability? In my experience, no, it doesn't. You have to be very vigilant. You have to be quite sure when you are talking about scalability and when you're looking into an application that needs to scale. So it's not just that putting in more resources into the machine or having more memory and CPU will solve your problem. It will solve it for a time being, but then it will come back and haunt you again. So this problem is a genuine problem and a design level issue that we need to be made sure of. So what we need, when do we need to scale? That is a very valid question. That does scaling comes in at the time when we are starting an application? Does the scaling should come in when we are when we have moved to production, or when we have done, like for example, after 6 months into production or after 1 year into the production? So that is the question that comes in my mind, that what's the step? What is the step where we should start thinking about scalability? So to be honest, it totally depends on the scenario that you're doing. So when you are developing an application, as an application developer or a designer, you have to be sure that your application has those capabilities or has those traits that can help it to scale. So in terms of APIs, we need to make sure that the APIs that we design does not have any specific bottlenecks or major bottlenecks that when the time comes for the scalability, we are tied up, or either we are redoing the whole thing, or we are redesigning the whole thing, or we have to scrap the old one and redevelop the whole thing. So we need to make sure. So scalability should be at your back of your mind from the start. And when it comes in, like for example, if we take an example of Facebook, so Facebook, this is basically a graph that I've taken, that initially it started as a university-based application, so for the university students, but then it grew and grew, and now we know how much it has grown. So initially, when Mark would have been developing that application, he wouldn't thought of that this application would come in and become this much bigger of an application. So, but with the passage of time, he understands, and the users and the more consumer that comes in, you need to make sure that your design and your application has the capability to scale or to serve all those users that are coming in into your application. So you have to basically make sure what's the right time to scale, and the design that we need to make sure. So as an architect, before we are talking about the scalability, we need to know that what is the benchmark for our application. Like for example, if I say that you are developing an application, Mubin, and I want to scale it, please scale my application. Now you can't just go in and add another server or increase the machine, increase the RAM, and it will scale. No, this is not the right way. The first thing we need to know is what is the application capable of? How much RPM can the current architecture or the server can hold? How should we expect in terms of load? What should we expect in terms of load? That what is the load that the consumer is thinking, your end customer is planning, or the application, the application, how much users that will come in on that application platform? How will the application behave if the RPMs is increased from a specific threshold? Like for example, you've set up a bar that this is the number of users. If you add 10 or 50 more or less, this is how much we are expecting users per second. But what will happen if the number increased by 10 or by 20 or by 50 or by X number? So how will the application respond? Will it slow down? Will it die out? What will happen at that time? As an architect, as a designer of the application, we need to be quite sure about all this. And what is the response time that is being expected from the application? Like for example, if we are talking about the real-time based application, then what is the response time? And that needs to be a real-time response. But if we are talking about general application, the response time should be acceptable, but it should not be real time. So you have to basically categorize your needs and measures. That is really important when we are developing an application, and these questions should be in the back of an architect all the time when they are starting to design an application or taking in any existing application. So what we need to do is, the first step we need to do, if we have the application or if we have built something up, we need to do the load test. As a developer, as an architect, we need to know what the benchmark is. The purpose of this step is to basically identify and write the performance objectives of your application. It's really important that we know what the objectives are in terms of performance. How we should know how our application behave under the load. I shouldn't say most, but a lot of people don't know what will happen if 20,000 users, concurrent users, access their application. They don't know it. Usually, if we talk about the software industry, that is the services-based industry, they are usually less aware of as compared to the product-based companies. They basically do take care of these, but the product-based companies, they do overlook this problem. So, as an architect, we need to be sure that the load test should be carried out when the application is developed or in development, and step by step. It's not a step that needs to be taken at the last. It's not the step that needs to be taken at the start. It has to be like a cycle that needs to be run over and over again to see how the specific areas of your application is taking in load and how it is behaving. So the scenario, the cycle goes on, like you need to first identify the test scenarios, the areas that need to be tested for load, that will have the most load in it. then you need to prepare some data, some specific data, if you're talking about orders, we need to post some orders, and we have to have some data related to it. Then we need to test those scenarios and execute them, and then monitor the whole aspects of the application, not just the application, all the resources also. What is the response time that we have? What is the throughput? What is the resource utilization in terms of memory, in terms of CPU, in terms of disk I/O, in terms of network? How is the application responding on each aspect of these areas? And the results are then analyzed, and the bottlenecks and the areas which has the problem are then fixed, and then the scenario comes in and tests it again and again and again, and until and unless it goes on to production. And then in production also, this needs to be carried on after some time in and out. Now, once we're done with the load testing, you have a benchmark for you. You have a benchmark that, okay, my application with this CPU, with this memory, this is how it should behave, and this is how it's behaving, and okay, this is my benchmark. But as an architect, you need to look forward to it. And then the next step, what is the next step? What will happen if your application benchmark is 1,000 RPMs? What will happen if the RPM is increased to 2,000, 5,000, 6,000? What will happen? So then the step of stress testing comes in. The stress testing is basically testing beyond the normal operational capacity. So when you have benchmarked or specified that at this level, our application will perform optimally, what will happen if that optimal barrier is breached and you go on and move above that breakpoint? And how will the application, the servers, the whole ecosystem will behave when this happens? We need to be sure, we need to be aware that what the stability of the system when we apply a stress to the application. We need to check the robustness that, for example, the requests are coming through quite fine, but when we apply the stress, the requests die down. And the other thing that usually happens when the load comes in on the server, the availability of the application is gone. The application is inaccessible. People are waiting for 2 minutes for the page to load in. And in terms of heavy load, sometimes the database collapses and no error handling has been done, and the whole system, basically the whole building collapses with this. So from end to end, we need to be sure that what will happen when we apply a stress to it. For example, if we talk about an e-commerce application, e-commerce application has a very big variations usually. Like, for example, during the Christmas time or the Black Friday time, the load on the e-commerce application is extremely, extremely high. But usually in normal days, it's not like that. But if your application or if the e-commerce application crashes at that peak time, the business suffers a lot. So we are not sure at that specific time that will that application sustain that load and work as per the capabilities that are required to it. So this is really important when we talk about designing an application, deploying an application, and delivering an application. Now let me take an example and walk you through that example and how the evolution process goes in when we are scaling an application. So this is an example I've just taken from one of my old projects. We had a customer that requested a B2B e-commerce solution. He told us that he had around 1,000 SKUs at the time. He wanted a mobile application and a web application for that. He was expecting around 50 orders a day. He wanted comments, reviews, things like that. He wanted order tracking, emails to be sent for marketing purposes and order delivery cycles, and to customers, consumers, all of it. Obviously, the product images need to be part of the B2B solution, and he was expecting around 2,000 users accessing the website within a minute. So this was around the base structure that he gave us. So what we initially did was we basically took a simple standard approach that we talk about in .NET Core. We developed a monolithic application. We developed web API controllers. We set up a database on back of it. We use Castrol as the engine for running the web as a web server engine, and basically the core performance and the core usefulness of the .NET Core is for multiple platforms. So we deployed it on Linux and put an Nginx server in front of it, and the application started working fine. Just moving forward, before moving forward, I just want to let you know that Castrol in the latest release of .NET Core, Castrol has really nice features like autoloader configurations in case and custom headers, encoding and decoding. So do look for that. Castrol is really evolving as a web server, so that is really good site to look at. Okay, so let me just come back to the point. So basically, if we talk about the high-level architecture, this is basically how it basically looked. So basically, we had an application server that has the APIs hosted in it, and a normal relational database, and EBS storage that we attach to it for the sharing of data and the shared data that we need. And it was being hosted by mobile tablets and all that. This was working fine. We deployed it on production. The customer was initially happy. He was very satisfied, and the things were going fine. We load tested it. It was working fine. Then this happened. After around, you can say, 1 year, the customer came back and reporting that the application is really, really, really slow, and he has lots of problems. Okay, so we asked him, look, okay, let us review it, what the problem is, and this is what we found. Now he had over 50,000 SKUs in that application, and the number of orders that we saw was around 5,000 orders that he was receiving on that, and the expected users that are coming in a day was around 50,000 to 1 lakh users that were coming in there. And he asked us that he wanted to make this B2B commerce public also. So the web API will remain same, and he'll have a public interface for the public users, general users, to basically also access that website. So we were like literally shocked, and we were thinking that, okay, now we are in trouble. The design that we had was not capable of handling this much traffic, this much data. So what we did was we basically went to the drawing board again, and now we had a base of a web API monolithic application, and now we have to handle all these situations. Now, one was we redesigned the whole thing. The whole thing needs to be redesigned. Like usually that we hear that, okay, we took a wrong decision. The framework that we took was completely useless. We shouldn't have gone for .NET Core Web API. We should have gone for Node, etc., etc., etc. Okay, that can be an excuse, but that is not a real excuse. So we can, every platform, if you're working on Node, if you're working on .NET Core, we can scale it out the way we like at quite a big level. So not at a Facebook level or an Alibaba level, but quite a big level. So the general consumer-based applications with this amount of data can be easily catered in it. So what we did was we looked into the components that we can add in and make our application scalable and usable for this specific user. And in general, we use this as standard for most of our applications. So we thought that we should have a load balancer applied. That is basically a truck of it, that we need to have a load balancer so that we can scale our servers out. So when we talk about, I was talking about that load balancer, the first thing that we added. Then we looked into the caching, the queues that we can use, and some of the services we can move to microservices architecture. And then we also looked, one of the main problem areas was the application architecture, that how the application was written. So for the load balancer, what we had was that since we wanted to scale out, the load balancer is a very key component, a base component for if we are talking about scaling now. And the benefit of load balancer, it also helps in DDoS and in terms of failover, when we had a failover or a high availability, the load balancer basically played a key role in that area. So this was one of the key component architecture for many of our applications that we developed. It basically gives us an edge of auto scaling. So we basically put in, and the auto scaling engine can auto scale our service, and the important task of the application architecture and scaling up and down, that really helps when we talk about load balancer. So when we are talking about load balancer, we need to be sure that which load balancing strategy that we will be using. Should it be round robin, least connections first? It should be least load. We usually use round robin. Sometimes we use least connection. That are the two techniques that we use. Least load is generally not being considered a lot and not being used a lot. Now, the second part is the caching. Caching is really, really important. And when we are talking about monolithic application, you know, it's really the heart and soul of the application. So why I'm saying that? Because look, the database is, if we are talking about any application and data-driven application, database is the heart of every system that we talk about. And the problem is that it is the most hardest part of the body or an application to scale. So when we are scaling a database, we have to do sharding, we have to do partitioning, and we have to do replication. That is really difficult. Strategies has to be made very well planned. In other case, it creates a lot of problems in terms of viewing of data and transmitting of data. So distributed, if we are going into distributed database, the time and cost involved with it, it's a big one. So before jumping into the distributed database or distributed database path, we need to make sure that it is required. So basically, caching is a way to help us reduce that pathway. So it helps us to basically don't go into that path until it's really required. This application has grown so much big that it requires a distributed database. Then you'll have the team, you'll have everything in terms of tools. But if the application is not that big, caching mostly gives us a way to solve all our problems. So with the caching, we can basically reduce the load on our database, and we'll have the relevant access that is to be required on the database. So caching needs to be implemented properly and in a way that it should be manageable and it should be usable. The second one is the queues. Queues are basically very important when we have a long-running process. So basically the benefit of queues is that, for example, if a web API has a request in ASP.NET Core, if we have a web API request and a request lands and we process those requests, is a heavy process. So the delay, the timeout possibility is a very big one. So queues basically help us solve this problem. So we can queue those heavy loaded processes, and we can have a services or Lambda expressions or functions that runs in and run those processes on the back end and transfer that results. The benefits of queues are there is no direct connection with the web API process. So it's basically it's on its own, it's running on its own, and it's independent. The asynchronous communication between processes, so there can be multiple processes, they are asynchronous and can run independently. Application can assign priority to the messages. So basically, you can have priorities assigned to your messaging, so that the first priority message, the highest priority message process first, and the lowest priority gets the second priority. And the cons are it's really hard to maintain it. Once we have the queues, we need to make sure that we need to monitor it. We need to make sure that they're not overloaded with the data. They're consuming properly. So we need to also make sure. So when we're introducing queues, we are also introducing a complexity in the design. But it's a thing that needs to be incorporated if we are building a large application. The next thing is that microservices. This presentation is not focused on this. So what I am focused about is when we are talking about microservices, in a monolithic application, that is basically a two different architectures that we're talking about. But there are components that we need that we can do a microservice based, and the rest of the application can be a monolithic based. So, like for example, if you talk about an e-commerce application, we have orders, we have products, we have shopping carts. All of these are main component, but usually the products are the main area that is mostly being accessed by the user. So we can build a microservice for the products only, and that can scale out independently. And the rest of the thing can be in a monolithic application because that's not being used. So we can design an application in a way that is a combination of both, and we can translate it. One important thing that we need to make sure that when we are working on microservices, usually with microservices, there's a concept that independence in terms of database, independence in terms of service and all that. But we can use the same database, or we can distribute the database into a smaller component if we need. So this can be a possibility. This is a way around the different structures that we can use. So microservices are really important. Now, the most key important part is our application architecture that has the most important parts in the application. So when we are talking about the application architecture, we can't scale if we have a bad design. That is absolutely important. So if your application has a bad design, what's the example of bad design? Let me give you an example. So for example, the API, web API calls in the backend, and the backend has all the business logic placed in a stored procedure, and that is being called by 5-6 different mechanisms. So 5 different areas. So all these 5 different areas are calling that API, and it's going to a database for a stored procedure. Same stored procedure is called by every. Now, even if you scale your servers from 4 to 10, this will still reduce the performance of your application because the design is flawed. So we have to be sure that when we are building an application, we have the right components in the right areas. It's not like it will be a recipe of disaster. Even if you put $100 million into it, it will not scale. It will give you problems, nightmares all the times if the application design are not proper. So that is really important that we need to look at. Slow APIs are more evil than the phase one. So make sure that is generally what happens. So even if you have developed a good front-end single-page application on React, on Angular, on anything else, if the APIs are not working properly, those apps will not work properly. So you have the backend is the heart, and need to make sure that the APIs are being built. Performance. Why are we talking about performance here? So performance and scalability goes hand in hand. So if there is a performance problem, we basically scale out. But look, we have to make sure first that the application is designed to perform optimal, and then we talk about this whole scalability part, that it should scale this. So the performance is also a very key component of scalability, and we need to make sure that this should be there. And if you're talking about .NET Core, we usually have I've identified these 4. There are multiple ones, but due to shorter time, I will give 4 core areas that we need to be sure when we are working. The first one is the proper use of async await. Async await is really, really helpful in designing a good performant application APIs, but you can fall into a trap that will basically give you a big headache, and you will not even know what the problem is. So when we are talking about async await, we need to make sure that we avoid at a maximum the use of async void functions, because the preference of async task and task generates methods are more than the normal. So basically, what I'm talking about is that we have usually 3 types of async method: task, T, and void. So async void methods usually have a different error handling semantics. So when the exception is thrown out from an async task or an async task generate method, the exception is captured and then placed on the task object and returned back to the higher order. With async void, what happens is there is no task object. So the exception is thrown out. So the exception is thrown out as an async void method will be raised directly on your synchronization context that was active when the async void method started. So you don't know where this exception will land in, and you have to then go in and your app domain and handle unhandled exception at that point, and you can handle that, but that is not a good practice to have. So avoid async void as much as possible. Due to this problem, async void is also difficult to test. The unit test, if for example you're testing for exception in the unit test, it will not be catched because of this specific problem. In Microsoft test also, asynchronous testing support for async void methods are not really good. Probably you can use synchronization context and add it to it and then use it, but still it's a big problem and it's not that much useful if you're talking about this. The second one is the async all the way. So what is async all the way? So I read a story once that one of my friends basically told that the world is suspended in space, but was immediately challenged. So basically what happened was basically a lady was sitting with my friend, and the friend told that, look, the world is basically hanging in space, but the lady tells that, no, your claim is not correct, and it's on the back of a giant turtle. So that person, my friend, basically asked him, okay, so where is that giant turtle standing on? So she smiled and then onto another giant turtle, and that turtle goes on and on and on. Similarly, for the async, we need to make sure that we do not block. So we either go from top to bottom or from bottom to up, and don't mix the blocking async code. Basically, what happens is the async all the way. What this means is that we shouldn't mix the synchronization and asynchronization code together, and we have to be careful. The problem is that async is not it's not multi-threaded. It's a single thread that has a thread pool, and it's using that thread pool to basically assign those threads to different jobs and work on it. So we have to be careful when you're using async. We have to make sure that we use async all the way from the top to the database level or database layer level, so that it has a complete effect and has a complete process async, so we get the maximum usefulness of this. Okay, so what is the usefulness of async await? So basically, where should we use it? On the database, async is not that much useful. It doesn't give that much of a performance gain, but we can definitely use it because of the hierarchy. But in web services or in parallel running process of web services, async is must to have. So for example, if you had to make 3 different API calls on the back end from a different web clients to different 3 web clients and get the data and process it, you can do that in parallel and wait for the data and then process it. This will improve the performance a lot, and it will also release a thread for thread pools available for the other requests to be processed. So that is why it's important. The second one that I talked about is string cancellation, string concatenation. We usually talk about this a lot, that we need to make sure strings are immutable. We need to use string builder for that. We need to make sure, but I have practically run this test, and believe me that this will make a difference when you have application grown and at a larger level. So for example, concatenation has a cost. It has a cost. It's a minimum, but it has a cost. So if we are talking about the cost, like for example, this one, I had 2 functions that I wrote, and the one on the top with no components. So this was not, it was basically a plus sign that's been used and concatenation being done from there. And look at the time that it took. It took around 22 seconds, 22.8 seconds to basically execute it. Similarly, I used a string builder for that, and it took me 0.018 to do the same steps. So use string builder. Whenever you are using a string, whenever you are not using a string builder, you are basically costing this much on your response time, and it will grow because you're not using it. So use string builder. It's a really good important aspect. The second one that we usually follow, I've seen developers do, is that they use exceptions to basically maneuver the responses or the execution of the code. That is really a bad practice. Exceptions take too much time to be handled. It's a real fact. So make sure that you properly handle all the cases that you have. Like for example, in this code base, you see that I've used the parseInt and I've used try catch to convert this integer. And in the final result, I've shown the split, otherwise this one. So this is basically a wrong methodology to use. We should use in try parse and use it in the value, and the result should be based in. Now, if we compare the performance of both of them, you see here that the first code that we had, this one, had a performance of 0.045 seconds, and the other one that we, the try parse, the parse one, who had 0.056 milliseconds. So the method started with the try parse was really fast as compared to the method with the exception. So it has 45 milliseconds and then 0.056 milliseconds. So it's a big difference. So make sure you're using the try catch properly. The fourth thing basically that I want to talk about is the proper use of entity framework. So when we are writing code, we usually overlook some of these things. We should not be greedy with the rows. So make sure the number of rows that are being requested by entity framework, it should be the amount of rows that is being needed by the customer or by the business request at that time. It should not be like you take in all the data in and then you process and then you take the 5 rows out of it and then send it back. This is really bad. And when you are working with a large application, it will really hurt you a lot. Similarly, usually the rows one is being solved, but this column problem is a really genuine problem. People do not take care of the greedy column problem. So make sure that you only select those columns that are required and not all of the columns within the table. So that is really important. The third problem that is really important is n+1 select problem. The n+1 select problem, what it means that if you look at this code, we had schools and we selected it as this, and for each school, then we start appending all the data into it. So the problem is that for each schools, we have a list of data and it's calling school.pupil.count. Now the school.pupil.count, due to the lazy loading, every time this is called, it goes in and makes a database call and fetch that information from the database. So for example, if we have 500 school records that we fetch, then we have this pupil.count being called in 500 times. This SQL statement will be executed 500 times. And this is a big problem and really hurts the performance of the application. So if that is the case, try to use include the pupils so that this doesn't happen. So this is also known as n+1 problem. It's not a bug, but it's a smelly code that needs to be written properly. The third one that is very good, and usually we do not follow that, is we know that entity framework detect changes. So usually when you have a bulk import utility written on in entity framework, and if you're using something like code like this, that pupil, get pupil, and you need to add that pupil in this. So now what will happen is the performance of this will slow down gradually one by one, because it's the same object, the pupil same object has been used and it's detecting changes for that. So every change will create a map, and then another one, and another one, and another one. And similarly, if you have 2,000 records, then you have a map of 2,000 that's been built. So every other request will slow it down to another point, and so on. So what's the solution for this one? Is in entity framework, either if you have a bulk data, use add range as one of the options, or you can configure your auto detection disabled. You can disable your auto detection by using the context.configuration.auto detection enabled to false before doing these kinds of steps. This will help you in terms of your application performance and bottlenecks a lot. Now, I've talked about this and I'm over a little bit of time, but I want to show you a design that when we incorporated all those options, how better the design becomes. So now we had a load balancer that we had in place, and then we had an application auto scaling group, that is for the AWS auto scaling group. For the processes like for example, the emails, the marketing emails, and the processing orders, what we did was we used the queues, and we had some Lambda jobs written on top of it to process those queues. For the database level, we didn't distribute the database. In future, what we did was for the database level, we did a read replica for that, and so this one was a transactional one. We had a read replica for the selection of data, and we used that. And then we also incorporated our cache, the Redis cache. We separated that out into the Redis that's performing very well, and use that cache as the main cache for transmitting the data, so that the load on the database is not that much that it dries out. Okay, so that's about it in terms of presentation. I had a couple of stories that I wanted to discuss with you. Basically, this is when we had a REST-based API. We had an API ERP system, and we wanted to build an RESTful API on top of it. And what we did was our teammate Todd was recently informed that when we built a REST API on top of it, it was then being told that this would be used by the mobile application and other teams and things like that. So what we did was the team, what they did was they grained out the performance APIs, and they built the application on top of it. And all the APIs were very fine grained, so there are very specific APIs that they built. The problem was that it was working fine, but when the mobile application developers and other developers started using it, the calls on the server were really a lot. So, for example, for one specific job, they were like making 4, 5, 6 calls to the database to the data. The problem was due to the fine-grained APIs that we had. The calls on the server was really increasing. So we need to make sure. The lesson we learned was when the fine-grained APIs are important, but we need to consider the design of the application also. And if the use case needs a combined or a full reduced characters or more detailed API, we need to build that specifically for that. We shouldn't stop that to be happening, because it will put up a lot of load into the server. The second one was we were building a an application for a Fortune 500 company, a Fortune 100 company, and the API basically was they were providing a digital experience, API experience for the mobile relevant to their future data. And what we did was we basically used their existing layer and built a REST API on top of it to basically send it back the data, to expose the data to it. But the problem was the system design was not up to the mark. We basically faced a high latency in that. And what we then did was we basically used the same strategy that I just told you. We put in the cache, we put in a little bit of performance boosters in it, and we basically went in and developed those rather than redesigning the whole thing, and the performance increased a lot. So the food of thought for this here is that always go for the low-hanging fruit first when we are doing the performance boosting or scaling, and then go for the big ones. So always choose the smaller one first, apply this, look into the performance. If it meets the requirements, then and good. If it doesn't, go for the next step and go for the next big one. Okay, so lastly, the food for thought from my side is, as we have seen that digital experience continues to evolve, and so is the architecture. So when we are talking about the application, the architecture and the architecture practices also evolve with the time. It's not that you have to design an application once and it should remain the way it is. Always strive to improve, always strive for excellence, but excellence is just a myth. So you have to improve and improve and improve, and for as much as you can. So thank you very much. Thank you for your time. You guys can contact me on LinkedIn. This is my email address. I don't have a blog right now, but hopefully soon I'm posting it, developing it for you guys, and sharing it soon with every one of you. So you can reach out to me over my email or LinkedIn. I'll be glad to answer you or help you out in the structure that anyone is possible.
Let's thank to Mobeen, and we're now on the Worldwide Software Architecture Summit, and all our speakers have been finished their parts, so we are now moving to the Q&A session. We can see that it has been a little bit moved forward. I would just like to remind you that there is a subscription model that we are introducing to GCL now. We are moving to a new format. So starting from today, everyone can join our GCL educational platform to get access to recordings, past and upcoming, and so on. You can get a lot of information. And the best thing is that all attendees of the Worldwide Software Architecture Summit will receive 21 days of free access to the platform. Use this chance to get your knowledge. So let's start with the Q&A session, and I would like to bring Erik Wilde back. Hi, Erik. Hey.
I'm back. Hey.
That's amazing. I've got a few exciting questions for you just immediately. There were today, like Erik had another session today on live, and there were so many questions that some of them have, we just go through them right now.
Okay.
Okay. Question number one from Ahmed Sabah. What do you think about designing? And I think it's great. What do you think about designing something like a JSON API, or something else, which would be a combination of both GraphQL and REST?
I think that actually kind of would be a good idea. And to some extent, I mean, I didn't go into this, but like the whole idea of REST versus GraphQL in my mind it's not a good way to phrase it. I just used the words that everybody is using. So you can actually design kind of a RESTful API that has kind of GraphQL as one part of it, right? Because in the end, REST is something that has a certain number of constraints, and GraphQL is just one technology that you can use in a certain way. In the end, GraphQL really is not a protocol even, right? It's just it's a query format, and it's a data model that you query into, and you can use that, basically that query format and that data model in any API design you like. So yes, you could integrate that, and it is something that I've seen, and I think actually doing that might be a good idea, because there are some scenarios where GraphQL is actually quite a good fit when you have a complex graph and you want to give the ability to query into that graph to consumers. And then there's some scenarios where REST is a good fit when you have these more workflow-oriented things where it's more about this conversation of messages flowing back and forth. And it's definitely something that I think could be a reasonable design. I just think the problem there may be with tooling around it. You might have people expecting that an API is either one or the other, and they kind of use tooling that is based around those assumptions. Mm-hmm. So even though the design in itself, just looking at it, actually may make sense, you might get developers that are, like getting a little bit upset and are telling you, pick one of those two, but don't give me both at the same time. So yeah, I think I like the idea, but I think I would be careful before I did that and think through the implications of that, and actually, like show it to people and say, play around with it. How do you like it? How does it work with your tooling?
All right. That's good enough. I guess the next question is actually just going with the flow. It's a question from Mahmoud Gabala. I have seen two styles to integrate GraphQL. First, as an API gateway aggregator in front of RESTful microservices, and second, implement it on backend services to aggregate data from different DBs. So I guess the thing that you've been mentioned before is actually probably the first option. Am I right?
I don't think I specifically said one or the other thing. One of the problems I think that you run into when you let's say, the more things you hide behind a GraphQL API, the more you run into the fact that you have to manage all these failure models that you might have, right? Where certain services that you are using may not be responding, or they may respond too slow. So you have to figure out, what do I do with this when I'm processing that query? So I think as long as you treat that as something where you're saying, basically, I have operationally, I have things good enough under control that I know that if I can run my query, it will very likely, I will get the full results, right? Then I think it's easier and safer to do than saying, I'll actually kind of do distributed query processing in a rather unreliable environment, and then I have to deal with all the possible failure cases that may arise, because then you introduce a lot of operational complexity for yourself. So I would be careful and at least think through the implications of what kinds of services that I am putting into my GraphQL interface, what kind of these services can fail, what will I do about this, and how likely is it for those things to happen. So if you just put them in front of a database, it's probably, on the operational level, it's probably much more reliable than if you put it in front of microservices that might have all kinds of delays and other failure modes that are a little harder to control.
Okay, so in that case, RESTful APIs would be actually much better to put on front of microservices, and then probably GraphQL on front of databases to aggregate data. Okay, it looks reasonable. Then I could imagine the next use case, and fix me if I'm wrong. So let's say we have a BI that has to deal with plenty of BI tools, and it has to deal with plenty of data sets. So we can understand that on the front-end application, would it be Angular or React, they would have to deal with plenty of different data sets that have to change on the go. So when you change your settings in your widget, or a dashboard, or would it be a chart, for example, and you pass that, you manipulate the data and you pass it from one widget to another one, you'd probably need, it would probably be better to use then these graph relations rather than REST. Is it correct?
I don't think I fully understand your scenario, I'm sorry.
Oh, okay. So you have a front end that consists, let's say it's a dashboard with plenty of charts on it.
Okay.
Charts. Each of these charts has its own data set, one or a few data sets that it extracts. And you know that operating, the user interacts with these dashboards, with these charts, and manipulates data in each of them and transfer data sets from one chart to another one on the go.
Okay.
So there's plenty of data manipulation all the time, and this widget has to talk to the database or to a cache or something else to always update the data on the go.
So, I mean, if you have complex data sets, and those data sets may even live in different services, I think that's what you're saying.
Yeah.
I think it would be very good to make sure that you express the relationships between the data sets through URIs, so that, you know, they really become something that is kind of, that works at a global level, so to speak, right? So you can move them around, you can combine them with other data sets that might be in totally different places. So I think in that case, I think the data model behind those kind of things would probably be a little bit more future-proof if you actually thought about using URIs as identifiers. So a little bit, I don't know whether you're like, do you know RDF, like the whole semantic web stuff, right? Where it's also a graph model, but it's more like a graph model that's not supposed to kind of live in just one place, but it's a graph model that by definition kind of can use anything that uses URIs as identifiers. And I think that would be more the design I would go for. And then if you look at this, right, then you have other languages, for example. So RDF comes with its own query language, which is called Sparkle. So maybe for those kind of scenarios, when you would actually talk about like distributed data sets, I think in that case, maybe using a different technology that is built around like really distributed data sets and not a data set in one place might be a better choice.
Okay, thank you. That's it gave me some points to think about. We've got one more question, which comes from Virgil Churches. What about hypermedia API pattern? What is that?
Yay, it's great. So that's actually, and I didn't go into this because we didn't have much time. But so when I talk about REST, I mean hypermedia. I mean, in my mind, I know that is another discussion you can have for a long time, right? But sort of academically speaking, proper REST APIs actually use hypermedia. And in particular, I think for those examples that I was giving, like the process-oriented APIs, right, where it's like, you can do this, and now you can do this, and now you can do this, right? Where do you want to ship it? Where should we deliver it? Which payment option do you choose? Those kind of things, I think, are very well represented in hypermedia APIs, right? And that's really what I actually was referring to. When I say REST, I mostly mean, I think a well-designed REST interface, I think ideally is actually a hypermedia interface.
Okay, very good, very good. Next question. Why, here it is, from Blaine Fredrickson. Question 40, okay. Why is load balancing based on actual load not recommended?
That is probably not a question for me.
Okay, yeah, I've got it just right now in comments.
It's a good question.
Brilliant question. Okay, a few more examples. So again, we are talking about different approaches and different implementations of REST and GraphQL, when it is better and when it is worse, and so on. So we realized that when we have complex relationships between different elements in the system or between different data elements, we would probably prefer GraphQL just because it's wider. And when we need to respond to some states or changes, we would use REST in that case. So let's try to imagine now an infrastructure where we have both REST and GraphQL probably sitting in different parts of the service, but they serve their own purposes. So in that case, where would you put each of them and why?
I mean, I think that's kind of like the first or second question that we have. Like, would you combine REST and GraphQL, right? And I think, yeah, I mean, you could do that, and I think it's something that even may make sense if you have like we discussed, right? You have like scenarios that both have process-oriented parts and both have data-oriented parts. So I think that for me would be the decision that I would make. But again, like I have to repeat myself, right? I think I would have concerns about tooling, right? Making it too complicated for developers. So I would probably say, if I compare those two parts, is it more process oriented or more data oriented, right? What's kind of the bigger part, so to speak, of the API? If I do everything in GraphQL, what are the compromises I have to make? Or if I do everything in REST, what are the compromises I have to make? And then I probably would still go for just one of those and say, it's not like parts of it maybe could be solved better in the other way, but overall, if I want to give developers kind of a more coherent experience where they can use the API using just one technology stack, that's probably worth the trade-off.
All right. However, we know the example of Facebook, right? You said that they are using GraphQL for internal applications when for the different components communication between them. And however, they still use REST for all the external communication, which probably means that using REST API is much simpler because it is more standardized and so on. Or there is another benefit of preferring this way.
There is another benefit which maybe I actually should have put in as a fifth point now that you mention it, so to speak. Okay. It'll be in my next iteration. Another thing is actually because REST and let's say hypermedia, right, has this this way of putting in links, right, where you guide basically an API consumer to possible next steps. It's easier, I think, to understand use cases around the API, right? If you just give people like a giant graph and tell them, do whatever you like, right? It can be really hard to figure out what I can do. So the one thing that I think I didn't even mention it, but on my one slide, there was this example of GraphQL. So GraphQL is this kind of exploratory tool that you can point at GraphQL APIs and explore around in the graph. So that's pretty cool. But if you have a complex graph, it's still, it's hard to understand a complex data model if somebody just gives you the data model and says, like, here it is. And so I think for REST APIs, right, it's something where you have, it's a little bit more prescriptive. It tells you more, here is how the process works, right? You'll find payment links, pick one of those. And then when you get the payment links, you'll find payment confirmation links. And here's what happens when you choose those, right? So it's maybe it's just another side of this more process-oriented thing, right? It's something that allows people to more easily understand how to use that thing, which brings me to that thing, right, where you say, like, if, for example, if the Facebook developers have to use the GraphQL API, right, they use this, that's their job. They do it 40 hours a week, probably 80 hours a week. And so they know it inside out. It's maybe hard to learn, but they know it by heart, right? But if for external APIs, for developers who just want to use your stuff, right, they don't use it for a very long time, and they should understand it quickly so that they say, oh yeah, that's nice, I like it, right? So I think that's also a balance there between how easy is it for me to understand it, to write my first examples around it, right? And or how hard is it for me to even understand what's going on?
Okay, so I can understand now that GraphQL learning curve is much bigger at the very beginning. So if we would like, at some stage we can say that if we really need to use GraphQL, we have to consider this factor first of all, and that any investigation or integration of the structure based on it will have just a bigger lead time inside to get it up and running. Is it correct?
That very much depends on the data model, right? I mean, if you put a super simple data model into GraphQL, it's not that hard to understand. I mean, the GraphQL language itself is actually not that complicated, right? But if the schema that you expose is complicated, right? So, I mean, some people actually say you should have one GraphQL API for a large organization where everything that the organization has is exposed in that one API, which theoretically is possible. But imagine how complicated that model would be, right? The schema representing all of Google, right? So, I mean, even though technically you could make it work, it would be a nightmare to understand what kind of query you have to write to get that part of the Google graph that you're interested in. Right? So the complexity is not so much in GraphQL itself, but in the schema. So if you apply GraphQL to a simple data model, it's actually not that hard to understand, right? But if you have a huge data model, then the complexity of the data model becomes the challenge, and that can be considerable. In particular, right, if you have a really large organization.
All right, thanks. That's quite fair, because even our brain is using actually multiple different APIs, so to say, to communicate to different body interfaces, let's say, if we present it in that way. All right. Moving forward, you've been talking about tooling, and I'm asking now this question because we are now on Software Architecture Summit. So let's imagine we are a group of architects, and we understand that we have now to build and to create an architecture for a solution that will be used for the next few years, right? Let's say we build an enterprise solution, and we understand that the next modernization cycle, or for this architecture, will be at least in a few years from now. So we have to consider some trends and so on. So how would you propose to go this way, where maybe there is already a set of tooling, especially like that influence on the API selection in the end?
Go about when you want to do GraphQL, or picking one?
Just picking one. So how would you understand creating the architecture now? Which API would you consider based on tooling, on tool set that you picked for it? Let's say you picked Node.js, and then you would probably be married to Swagger.
I see what you're saying. I would be very careful. So when you look at the major vendors, right, as far as I can tell, the only major vendor who's really putting cycles into GraphQL is IBM, right? IBM is really trying to position GraphQL as something that makes sense in enterprise contexts. And it's complicated, right? It's security. So for example, security issues, right? Like in typical APIs, you often have like first lines of defense where you inspect the content of API traffic, and you can do some rough security checks, right? That is much easier to do in REST, where you have your payload pretty well defined in a schema. In GraphQL, right, you have to do query analysis. It's pretty hard. And right, so and it's this kind of stuff where it's like all of this is possible, but building tooling around that becomes it's a challenge. And I would say the maturity of that tooling is right now in a pretty early stage. Again, from all the vendors that I've seen, only IBM, I think, is really investing pretty heavily into this. All the other vendors that from what I can see, I mean, they tell you they support GraphQL, but in the end, I mean, mostly what they do is they can secure the endpoint, right? I mean, of course, maybe you have to use HTTPS and some kind of authentication and so forth, but securing the traffic, understanding, what kind of data is going through, is this query some kind of attack, that tries to bring down a server by posting like a ridiculously complicated query that will just stop my database, right? Like that kind of stuff is hard to do. And I think nobody else is really working in it other than IBM. So I would definitely be kind of concerned a little bit about the maturity of the tooling and the support of the tooling in different kind of technology stacks or vendor stacks that I may want to use.
Okay, thank you. My next question is related to actually even graph databases. Again, it's all about tooling. So there are some graph databases like Cypher, I guess, Neo4j, something like that. And for example, I never worked with them. I heard about them, but never worked with them. So in that case, this is a part of tooling that's probably requiring some specific API. What would be the reason of using them in that case? What would be the advantage?
The graph databases?
The graph databases and probably, again, GraphQL around them. Is it required that much, or it's not like mandatory combined?
No, not really. I mean, in some cases, you might see scenarios where the query basically. So depending on what you do, right? So, but in many cases, at least, your query resolver that sits in the back end, right? The query resolver will have components that say, okay, this part of the query goes here, this part of the query goes there, this part of the query goes there. So you will have some kind of process that does some kind of distributed query processing. What is sitting behind this, like those distributed parts, whether these are traditional databases or graph databases, or maybe not a database at all, maybe it's some process system doing that, that you don't know that, right? So it could be graph databases. I'm sure that, of course, when you look at large data-centric scenarios like Facebook, right? I have no idea, to be honest, what kind of graph model Facebook is using. I'm sure they have something homegrown. I don't think they run on Neo4j or something like this, right? It probably exceeds the scale of anything you can buy or get what they're doing. But yeah, I could see some scenarios where you might want to put one of these graph databases basically to power your GraphQL API. But again, like the important part for me would be to say what you definitely always should do is to say, even if I do this, right, I have one level where I have my GraphQL API, and then I have the schema that defines what people can query, right? So that's the API level. And then I have underneath maybe a graph database that has a schema or has a certain data model being managed in that graph database. But that really should be different, right? What you should not do, what I think would be a bad idea, would be to say, I basically directly expose, I design that API as a direct query into my database, right? That is, yeah, exactly, right? That would be a big design smell. It's like, yeah, you probably don't want to do that. So, yeah. So yeah, I think in some scenarios you might see those. Probably, the larger your graphs get, but it's not the case that all GraphQL scenarios have huge graphs, right? Sometimes it actually may be moderately sized graphs where people just say, well, the best way to represent that is just to give a GraphQL API for that. So, and then you're fine basically using any kind of database technology that, as long as it scales for you.
Okay. One more example. Let's think about this. Imagine that you have a data analysis layer on one side. So it's working with plenty of different data. There are quite complex data relationships between it. So the backend relies on the data. And then there's a front-end component, let's say a mobile app, for example, that you use to get statistics, right? So it's just a BI application that sends queries and so on. But those are quite strict. So in that case, would it be a benefit to use a REST API between this front-end component and the backend that gives that sends some requests? However, use GraphQL on the backend side in order to connect different data analysis components and all the stuff. Would it make sense in that architectural approach? So you have an internal ecosystem that's dealing with data, and then you have one or a few external channels, so to say. Would that be mobile app or front-end web?
Yeah. So in a way, I think what you're saying is that external interface is kind of more constrained, right? And yeah, that totally makes sense, because right then it's easier to secure, it's easier to analyze, it's easier to restrict what people can do, it's easier to prevent certain kinds of attacks from happening. So yeah, I think that would make sense. And when you were saying that, I was wondering, I have no idea whether they're doing it, but I could imagine at least that even Facebook maybe do that, where they say, our internal thing is GraphQL, and the externally facing APIs are actually served also through our GraphQL backend, but the external people can only use the REST APIs that we expose, which are more constrained in what people can do. So we can more easily make sure that, they don't do any harm and they don't exceed certain limits and all these kind of things. So I don't know whether they do it, but probably would not be a terrible idea to do it like this, right? There would be other ways to do it. But yeah, I think the pattern is not, it's definitely, I think it's a pattern that could make sense in many cases, yes.
All right. Okay, let's probably finish with the last question here. So my understanding now is that in some, and again, it's an assumption for you to validate or reject it. So as I understand, if we have our backend ecosystem, probably it would be a cloud-based one with plenty of microservices and the other things, even like no-code things, the services that we don't need to put any code there just to configure them. So would GraphQL API, again, serving internally for that infrastructure, would it make it a little bit more flexible in terms of just swapping those services one to each other? Would it make it more flexible in comparison to the REST API, or vice versa?
That's a tough one.
Thank you.
So personally, I mean, we spoke about that before I started my presentation, right? So my background is in web architecture, and I'm a believer in decentralized architecture, saying that, it's like ideally you want to keep things kind of as isolated as you can and kind of pull them together on demand.
Yeah, but as much as possible.
Yeah, and GraphQL is a little bit different from that, right? It's that idea that you have that resolver that gives you that convenient one access thing, and then it just does magic for you. And so I don't think that I probably would prefer that way of doing things, and I really haven't seen that done. And I mean, of course, it's also a question always of the maturity of the technology, right? So maybe it's a great idea, and the tooling will evolve, and we'll see these kind of things. But for now, I would be concerned that there's more coordination overhead, so let's say you develop a new service, right? If you have REST APIs, you just develop it, you deploy it, you put it maybe in some catalog and say, look, here it is, right? And then everybody can use it. If you use GraphQL, right, you would need to put it into the resolver that resolves the queries against the overall model, right? And you would need to make sure that all these resolvers and this set of resolvers will grow and grow and grow. It kind of becomes your new enterprise service bus, so to speak, right? This one place where, like, whenever you change something, this is the one place where stuff needs to be changed, right? And those things tend to become bottlenecks that slow down things. So it looks like a good idea at the start, and then over time you realize that maybe it wasn't such a great idea after all. So that would be my concern with that. So I think I probably wouldn't be a fan of that idea, but it probably can be. I mean, technically it probably works, right? But I think you might run into similar problems like these other things where you put in a centralized piece of infrastructure where everybody has to use that one piece of infrastructure. And that tends to become more problematic over time and over size of an organization.
Thank you. Okay, now I really understand a big concern of that. So if we want to build a centralized infrastructure for some reason, we can pick GraphQL then. However, keeping in mind that putting any next microservice there or component or whatever it is, extending the infrastructure, might increase the complexity of GraphQL really dramatically, not only linearly, but probably in like a geometrical scale, right?
And process-wise, right? So it's the kind of stuff you see in organizations where, well, there's one team doing it, right? And if you do it, you have to go through approval process. There need to be tests that are run, right? There's the deployment process that has to happen. So you run through all these pipelines that the more changes you want to make, the harder it gets to actually run through that in a shorter amount of time. And that's kind of like we're trying to get away from these things, right? Where we introduce these patterns that slow us down. We try to make things faster these days.
True story. Okay, so we've got probably the main reason, the main factor. So it's always coming from the reason, right? There's always the why in the center, and only then the what and how. So, and understanding the why part, the reason part, is crucial is a key to building the architecture, and actually in the end choosing the appropriate tooling, the appropriate methodologies, and the appropriate APIs as well. All right. Would you like to just say something to those who are looking for this session, and especially those who are just growing up their career, and probably the ones who are thinking about becoming an API expert, not only like backend or frontend, but focusing more on APIs? Let's go that way.
Well, that's a tough ask. I think most importantly, what I think is sometimes getting lost a little bit is this idea, and I have videos around that, like an API is a promise, an API is a language, right? So when you do these APIs, I think it's super important that these things exist. So I think it's really something where we will see like this space will grow and grow and grow. I'm totally sure of that. But what you always have to keep in mind, I think, what you're designing essentially is a language, right? It's a communication mechanism for people communicating, for components communicating, but in the end, people, right? The people writing it, the people writing code, consuming it. So think about those people. Also think about how these relationships will change over time, and how well what you're doing actually can work over time, and also how it can scale. Right? I think that really is the important part. Don't just kind of look at APIs as kind of a mechanical thing. For me personally, right, the fascinating part is the more I get into the API space, the less time I spend with the technology, and the more time I spend with understanding how it's influenced by organizational issues, by business goals, right? Because all these things are very much influenced in the end by how those APIs get designed and get used within organizations. In particular, right, when it's not just about let's build it and then throw it away after half a year, but like if we build this API, it has to be operational for the next 5 years at least, right? So that's something that I think is really hard. So take APIs seriously as a communication mechanism, not just as a technical thing. Right. And if you look beyond the technology, I think then you have a good perspective, and that, at least for me, also is just super interesting, because it makes you understand that in the end, all the technology, and you said that before, right? All the technology that we do has to be for some purpose.
Yeah.
And understanding how well we actually serve that purpose, right, I think is an important exercise when we do any of the technology things. And I think because APIs are always about communications, I think this is what makes them so interesting, at least for me.
True story. Communication is the key. And interaction, well, there are always two levels. There is something inside the black box that performs the operation, and there is something that connects different black boxes. So exactly. You do either one or another one.
Yeah, but nowadays, right, the black boxes, they always need to talk to somebody else, right? You like the age of just making a black box and being happy about that existing, that age is over, right? It always needs to talk to other black boxes. Otherwise, it's worthless.
Yeah, that's true. Plenty of black boxes arrive almost every day, and building a single inclusive space for them, communication rules for them is just amazing. It's like the traffic rules, right? You have you've got the traffic rules, and you've got different transportations there. You've got bikes, I don't know, motorbikes. You would get gas cars and electric cars. Then you would got you would get autopilots one and manually driven and something with the horses, but they all follow the same street traffic rules. Okay, thank you, Erik, so much. I was happy to talk to you. I really enjoyed this discussion. We are running over our time, so thanks a lot.
Thank you. It was a lot of fun, really, and I mean that. It was really nice. Thank you.
Thank you too. It was Erik Wilde, and now we would like to remind you this is a Worldwide Software Architecture Summit. We've finished all our sessions. We're finished with all our conversations and topics. So now the very, very last part of it is the giveaway randomizer. Let me just do a quick thing. I have to share the screen with you and show you the list of randomized users. Let me bring it to the screen. So here we are. My very bad, I have to edit it. Okay, random.org. Here we are. Fine. So today we've got a lot of people asking their questions. What we did is each name is replicated as many times as a question followed by the question for ticket hashtag was repeated. Sometimes you would see 2 or 3 occurrences of the same name. Yesterday, when I've been performing the same, there was a person that has asked like 4 or 5 different questions. So that person has got 2 tickets, even with the randomizer. You can see the screen, you can see the names, and let me randomize. 3, 2, 1. Woohoo! Here we are. These 5 names are the lucky winners. This is Mixima Explore, then Julia Damjanovic, then this Mixima Explore one time again, then Prabhu, Pavel, and that's it. So we've got again a person who has won 2 tickets. Let me publish them in the chat as well. These are the winners. All right, ladies and gentlemen. I was happy to moderate this conversation. I was happy to hear from plenty of smart people. It's always interesting to talk to them, to listen to their approaches. Architecture is a key. Whatever you struggle working on a project, whatever you would like to change and so on, it comes from the architecture. The problems you face right now, they were somewhere there in the architecture at the very beginning. That's why it is so important to explore it. That's why it's so important to understand it. And that's why it becomes so crucial nowadays, especially the architecture that can be scalable and can be changed over the time with the maturity of your product. Now, we finish this amazing summit. There will be plenty of new events somewhere soon. Please stay tuned to our updates. And thank you. See you later. Bye-bye.
Hello there.
Hey, so it's time to give you all many thanks for joining us today, for your support, for being with us, for your feedback. And actually, we look forward to getting your feedback more and more after this event. Thank you so much, dear friends, and thank you to all our moderators, both local and Adrian, who joined us from New Zealand. It was really great. Also, I'd like to give many thanks to our program board team who helped us a lot to prepare for this event, and our speakers. You were all amazing and great. Thank you so much. And last but not least, I'd like to give many thanks to the person who usually behind the screen and behind the stage. Welcome our technical specialist, Nick. So please, a couple of words.
Thank you very much. I also want to say a big shout out to our team, to Geekle, to all the speakers, to program committee, of course, and of course to you, all our attendees, and especially everyone who is watching this right now live, the people who are watching the very end of our conference. This was both challenge and pleasure for me to guide, to help our moderators, to try to get everything in order. And yeah, I hope there is nothing too severe happened. It was really a first experience to have both recordings of our event and also trying to get live streams for different time zones. I'm really happy with the result, and I hope you will come to more events. I have more chances to help more speakers, connect with all you, and give valuable knowledge. So yeah.
And last word. So, dear friends, thank you for your feedback, and we are really waiting for your feedback to help us become better. Besides, if you missed anything, any speech by chance, no worries. You will get the recordings in a couple of days. Thank you so much, and we are waiting for you for our upcoming events. Thank you.
Bye.
Bye.